yesterday in this program, Ask the Theorist, Shiraz Minwala pointed out that there are in fact very few talks about strings in this string meeting. So I'm very happy to chair a session where the topic is a string, and I'm even more happy to have to introduce Ofer Aharony from the Weizmann Institute, who will tell us about effective strings. So Ofer.
Thanks. So I'd like to start by thanking the organizers for all the hard work that they did in putting this conference together in these difficult times. And indeed, people often ask why strings conferences have so few talks that are actually about strings, and this talk will try to fix that. I mean, so this talk will be all about strings, and in particular, it will be about strings of the type that appear in the real world. I mean, so just like these strings that hold up this beautiful bridge in Sao Paulo, although of course I'll focus on somewhat smaller strings so that the quantum effects will be more interesting. So strings appear in many different places in physics and in nature, and we have many different types of strings. We can have solitonic strings. There are classical solutions, one of the famous ones being the string in the 3+1 dimensional abelian Higgs model. We can have confining strings in many non-abelian gauge theories in 2, 3, or 4 space-time dimensions, and also in abelian gauge theories in 2 or 3 space-time dimensions. We can have domain walls in 2+1 dimensional theories that behave like dynamical strings. We can have cosmic strings that fill the whole universe. And of course, last but not least, we could also have fundamental strings in string theory, from which we build string perturbation theory. And these categories are not mutually exclusive. As I'll remind you later, confining strings can in some cases also be fundamental strings. Domain walls and cosmic strings can be solitonic strings, and so on. So we have all these different types of strings in physics. And in this talk, my main topic will be the universal features that are shared by all of these many different types of strings. And these universal features are captured by what I'll call the long string effective action, which captures the low energy fluctuations of long strings. So in this talk, I will only discuss stable strings that have some finite tension T. So as an example, you can consider confining strings in the Yang-Mills theories. If we don't have any dynamical quarks in the fundamental representation, then these strings are stable. And so that will be a typical example that I'll discuss. And generally, for strings to be stable, they need to be charged under some one-form symmetry. And so that will be the typical case. For instance, in the abelian Higgs model, the string is charged under a continuous one-form symmetry, while confining strings in Yang-Mills theories are usually charged under some discrete one-form symmetries that guarantee their stability. Now, as I said, I'll focus on the universal aspects of these strings, which arise when they're long and close to being straight, in the sense that the radius of curvature of the worldsheet should be much larger than the string scale, which is set by the scale of the string tension. And this effective theory is called the effective string theory, or the long string effective action. Now, this topic has a very long history, and I won't have time here to give references to all the papers I listed here. So references to developments before 2013 can be found in this review paper that I wrote then with Zohar Komolgotsky, and I listed here some of the names of the main contributors in those times, and I will try to give explicit reference to later developments. So let's start with the simplest case. Let's consider that we just have some straight infinite string in some d-dimensional quantum field theory. Again, it could be a solitonic string, a confining string, or any other type of string. And this string and this configuration breaks the Poincare group to a product of the two-dimensional Poincare group times the SOD-2 rotation in the transverse directions around the string. So many different generators of the Poincare group are spontaneously broken in this type of configuration. And you may expect to have many different Nabu-Goldstone bosons, but it turns out, as is often the case when there are space-time symmetries, that many of these Nabu-Goldstone bosons are not independent of each other. And in fact, it turns out that there are only d-2 Nabu-Goldstone bosons in this configuration, so only d-2 massless fields along the string worldsheet, which can be thought of as the Nabu-Goldstone bosons corresponding to the translation symmetries in the transverse directions that are broken by the position of the string. Namely, if you consider fluctuations of these Nabu-Goldstone bosons, then they just describe fluctuations of the string in the transverse direction. So these massless modes are always there for any long string. And generically, unless the string breaks any extra symmetries, these would be the only massless fields on the worldsheet. And we expect all other fields, if we don't have any other scale in the theory, we expect all of them to have scales of the order of the scale set by the string tension. And in particular, if we have some solitonic string, we expect the width of the string also to be at this scale. And so also the masses of any internal excitations of the worldsheet should also be at this scale. Now, in many interesting cases, such as confining Young-Mills theory, the bulk theory has some mass gap, M gap. And then if we consider the full low energy effective action in the presence of a string below the scales of the bulk mass gap and also below the scale of the string tension, then really the only light fields in that case are these D-2 massless Nabu-Goldstone bosons. So in this case, we should have a low energy effective action that contains only those fields and which is completely consistent and unitary by itself. So in this context, the effective action only contains those fields. It's analogous to the Carol-Lagrangian when the pions are the only massless fields. And as usual, it has some derivative expansion. And what we'll argue is that the first few terms in this expansion are universal. Now, how do we describe this effective action? So it's natural to choose some coordinates along the string worldsheet. So I'll choose some coordinates sigma along the string worldsheet. And then one way to describe this effective action is to use the embedding of the string into our d-dimensional spacetime. So we can describe by x mu sigma the position of the point sigma along the string. And that provides the embedding of the string into spacetime. And then we should write down some effective action in terms of this embedding. Now, we have no preferred choice of coordinates on the string worldsheet, so this action should have diffeomorphism invariance in the sigma variables. And if we have a relativistic field theory, we should have Poincare invariance in the x mu variables. So that would be a global symmetry of this theory. Now, of course, the theory as written here could describe any configuration of the string, but we expect it to be valid only in long string configurations whose curvature is small, as I mentioned. Now, what can we do with this long string effective action? So there are various interesting observables that we can compute for it. One example is that we can consider the low energy scattering of Nabu-Goldstone bosons. So we can take a long string, scatter Nabu-Goldstone bosons from the two sides of the string, and we can compute their scattering amplitude at low energies using this long string effective action. And as I'll discuss later, we can also use the S-matrix bootstrap to constrain that. Another interesting observable that we can compute from the effective action is the energy levels of long strings. So in some cases, we can just constrain a string to have a large length L. For instance, we can consider an open string stretched between D branes. This arises in confining gauge theories. If you have two Wilson lines, then the string stretched between them is some open string of length L. Or we can consider our spacetime to have some large circle and consider a string wrapped on a circle, and then it would also have a naturally long length L. So in those cases, we can expand the energy levels of all the states of that string in a Taylor series in 1 over the length. So the leading term, of course, is just the classical energy of that string, the tension times the length. And then we have a Taylor expansion in 1 over TL squared. So there's a term order 1 over L and various higher order terms. And in principle, given the effective action on the long string, we can compute all these energy levels order by order in this expansion. And what I'll argue is that the first 4 terms in this expansion are all completely universal, independent of the properties of what the string is made of, and only higher order terms are non-universal. So they come from various Wilson coefficients of this effective string action. In particular, if we consider an open string, say between 2 Wilson lines, then the ground state energy of that corresponds to the potential between an external quark and an anti-quark in confining theories. So that's one type of observable we can compute using this effective string theory. And the nice thing about these energy levels is that they're easy to compute in lattice simulations of various strongly interacting theories. So we can match the energy levels that we can compute from this effective string action, say, to lattice simulations of Young-Mills theory, and into this way test this formalism and compute the effective action. In the next few minutes, I'll describe 3 different ways in which we can analyze this long string effective action. Depending on how we treat the diffeomorphism symmetries, I'll first discuss what happens if we don't gauge fix the symmetry. Then I'll describe what's called the static gauge, and I'll end up with a discussion of the orthogonal gauge. So at the classical level, we don't have to gauge fix. We can just work with the full ungauge fixed action. And then we need to look for actions we can write down, which will be diffeomorphism invariant in the sigma A variables, and which will have Poincare invariance in the x mu variables. So we want to write down the most general action that has these properties. And it turns out that in the context of the derivative expansion, well, in general, it's natural to write these actions using various geometric properties of the embedding of the string into spacetime. And in the context of the derivative expansion, it's actually enough to use just 2 of these geometric properties. One obvious one is the induced metric, dAx mu dBx mu, which is the metric induced on the string worldsheet from the spacetime flat metric. So this is a natural object, and we can construct the intrinsic curvature RAB, which is made from this induced metric. And we can also consider the extrinsic curvature, which is basically just the second derivative of these coordinates x mu. And then from that, we can construct various other geometric invariants. Now, usually when we have effective actions, we classify them just in some derivative expansions. However, in the case of this long string effective action, that already the ground state of a long string has some non-zero derivatives. So if the string is stretched in the x1 direction, then the derivative of x1 is non-zero. So that's actually not the natural expansion in this case, but rather it turns out that it's natural to classify the terms in the effective action by what we call the weight. So we assign to any first derivative of x, we assign to it weight 0. Of course, x's always appear with some number of derivatives because the action is translationally invariant in x. So all the terms will have at least one derivative acting on every x. And then we assign to dx weight 0, and we assign an additional weight 1 to any extra derivative that acts on that. So d squared x would have weight 1, for instance. So in this classification, the induced metric on the worldsheet has weight 0, while the extrinsic curvature has weight equal to 1. And then we can classify what are all the terms we can write down with a given weight in this effective action. So starting from weight 0, there we can only use the metric on the worldsheet with no extra derivatives to construct invariant terms. And it's easy to see that there's only one diffeomorphism invariant term that can be written down with weight 0, which is nothing but the Nabu-Goto action, which is just the area, the induced area of the string worldsheet. And as I said, I'll assume that the string has non-zero tension, such that this will provide for us the leading term in a good derivative expansion. So this action has as a solution flat strings, but of course it has also many other solutions. And the leading order equations that follow from this leading order action are just that box of x mu vanishes. So this will always be the leading order term in any effective string action. Now, at weight 2, we can have 2 extra derivatives on top of that. And it turns out that there are 2 independent terms that one can write down. One of them is just square root h times r, namely just the Einstein-Hilbert term in 1 + 1 dimensions using the induced metric. And the other term is this extrinsic curvature squared. Now, as is well known, in 1 + 1 dimensions, the first term is just a topological invariant. So the fluctuations of the string do not affect it at all. So that will not play any role in the long string effective action. The second term is often called the rigidity terms, but it turns out that this term is actually proportional to the leading order equations of motion, box x mu equals to 0. So we can always eliminate it by a field redefinition and shift it to be a higher order term in the effective action. So it turns out that in this case, because of the special properties of 1 + 1 dimensional gravity, there are actually no non-trivial terms appearing at the leading order w equals 2, unlike most effective actions for Nabu-Goto bosons. And the non-trivial corrections only start at order w equals 4. So at that order, w equals 4, we can write down various terms. For instance, we can have the curvature squared or k to the 4th. It turns out that in 4 space-time dimensions or higher, we have 2 independent terms that we can write down that can be written in this schematic way, while in 3 dimensions, these 2 terms are proportional to each other, so that there's only one independent coefficient. And of course, as we then go to higher and higher orders, we have more and more coefficients as we go to higher orders. So this is just a classical analysis of the possible allowed terms. We know that if we want to analyze the theory quantum mechanically, we do have to do some gauge fixing and various other procedures. So the first question I want to ask is, does this remain true also quantum mechanically? Is it still true that the leading order corrections vanish? So to do that, I'll analyze 2 possible gauge fixings, and I'll start with what's called the static gauge. So if we have a long string, which is mostly stretched along the time and x1 directions, then it's natural to gauge fix to the 2 worldsheet coordinates to just be equal to x0 and x1. And this is what's called the static gauge. And so in this gauge, x1 and x0 become trivial, and the only remaining degrees of freedom are the d-2 transverse fluctuations of the string, these xi of sigma, which are just the Nabu-Goto bosons. So in this gauge, there's no remaining gauge freedom. We completely fix the diffeomorphism symmetry, and there's also no non-trivial Jacobian. So we write down an effective action just for these physical fields. So this is analogous to a unitarity gauge, where we only have the physical fields. And this action should obviously be invariant under the Poincare symmetry and the global symmetry of rotating all these scalar fields. So the advantage of this formalism is that it only contains the physical fields, but the disadvantage is that Lorentz invariance is not manifest in this gauge choice. In fact, it's non-linearly realized. So we have to carefully check whether our effective theory is indeed invariant under the full Lorentz or Poincare group, similar to what we have to do in light cone gauge in fundamental string theory. Now we can again classify all the allowed terms by their weight. At weight 0, in this formalism, you can write down just polynomials in these two combinations of the basic fields. And if you check which combinations are Lorentz invariant, then it turns out that again, there's just one invariant combination, which again is just the Nabu-Goto action written in this specific gauge choice where it takes this form. Now in this gauge choice, the Nabu-Goto action itself, so already the leading order term turns out to be an interacting theory. When we expand this in a power series in derivatives, we have dx to the 4th, dx to the 6th terms, and so on. So this does give us an interacting theory already at the leading order, again, analogous to the leading order terms in the Cairo-Lagrangian for pion physics. So this is the leading order term. If we go on to weight 2, then it turns out that at weight 2, so with 2 extra derivatives, there are actually no terms that we can write down that are exactly Lorentz invariant. But there is one term that we can write down whose Lorentz transformation is proportional to the equations of motion. So that's this term that I explicitly wrote down here. Now, usually, if we have terms whose variation is proportional to the equations of motion, that means that we can change the transformation order by order such that these terms will become invariant under the new transformation. So you may think that this term is allowed, but it turns out that when you try to do that, then you actually have to modify the Lorentz algebra so that the theory at the quantum level is actually not Lorentz invariant, meaning that this term is actually not allowed. And the conclusion ends up in this gauge that, again, all the allowed terms start at weight 4, just like we found in the analysis without any gauge fixing. Now, the situation when you actually do quantum computations in this gauge is actually more subtle than that, because to do any quantum computations, since this is an interacting theory in this gauge, we have to regularize. And most regularizations that we use, such as a cutoff or a zeta function, explicitly break the Lorentz symmetry. So in those cases, when we do computations, we often find that we do have to add this term to our effective action in order to balance the Lorentz breaking by the regularization. So usually you would find that you have to add this term with a very specific coefficient in order for the Lorentz symmetry to be restored. So in that context, our effective action would have a term like this, but the important thing is that it's not an arbitrary coefficient, but it's just fixed given your regularization. And in some regularizations, like dimensional regularization, it's actually not present. So the important thing is that, again, we don't have any free coefficients at this w equals 2 order, and the non-universal terms start at order w equals 4. Now, doing computations in the static gauge is conceptually straightforward. If we want, we can compute any scattering amplitudes of these Nabu-Goto bosons and energy levels and so on. But in practice, they turn out to be quite complicated because of all the interactions that we have here already coming from the leading order Nabu-Goto action. So for this reason, it's nice to consider also other gaugings, and in particular, another natural gauge fixing of the diffeomorphism symmetry is to go to the orthogonal gauge, in which we gauge fix the two diffeomorphisms such that the induced metric is exactly proportional to the identity matrix. So we can always do that using the two diffeomorphisms. And this is similar to conformal gauge in fundamental string theory, but of course it's not identical because in that context we have an elementary metric field on the worldsheet and we have while invariants and so on, while here we're just using diffeomorphisms and we only have this induced metric. Now this gauge choice has many advantages. One is that in this gauge choice, the leading order Nabu-Goto action turns out to be just a free action. So this is just the leading order w equals 0 term. Another advantage is that the full Poincare symmetry here is manifest. And a third advantage is that this gauge fixing does not completely fix the diffeomorphism symmetry, but as is famous from conformal gauge in string theory, we still have left over a conformal symmetry on our worldsheet, which means that the effective action in this gauge choice has to be conformally invariant, which gives us very strong constraints on the action. So we have all these nice advantages. Of course, the disadvantage of this gauge is that it has some non-physical degrees of freedom. And in particular, also the gauge fixing here turns out to lead to rather complicated ghosts. And the Fadeev-Popov action leads to rather complicated constraints on the physical states. So that's the price that you have to pay for all of these advantages that we have. Now, if you actually try to compute the BRST operator corresponding to this gauge fixing in the orthogonal gauge, it turns out to be very complicated. However, already 30 years ago, Olchinski and Strominger conjectured that maybe you can quantize the effective string in this gauge by just imposing Virasoro constraints on the physical states, just saying that they're annihilated by the Ln operators, just like we do for fundamental strings in the conformal gauge. Now, there's actually no direct derivation of this procedure, but if you want, you can derive it by adding some auxiliary fields to our metric beyond the x mu variables. And then if you make some assumptions about how you can write down the action using that auxiliary field and integrate it out, you can show that you do get these Virasoro constraints in that formalism. And there are various consistency checks that show that this is indeed a consistent procedure to analyze the effective string action. So I'll assume this procedure in the rest of this talk. So assuming that, we have to just write down some effective action with these x mu variables that should be conformally invariant and impose these physical state conditions on top of that. So which actions can we write down? Naively, if we want to write down a conformal action just using the x mu variables, then there's nothing we can write down because any higher derivative terms that we write down, of course, would not be conformally invariant. They would not even have the right scaling dimensions. However, here we have to remember that we're trying to write down just an action that's valid for effective strings, so it should only be valid for long string configurations. And in long string configurations, there's always a non-zero value to this combination d plus x mu, d minus x mu, which has some expectation value in any long string configuration. So that means that in the effective action, we can allow also negative powers of this combination as z. And in particular, the first term you can write down over a2, which is conformally invariant, turns out to be this specific combination. So you can check that if you allow these negative powers, then this term is conformally invariant, so it can appear in the effective long string action. And on top of that, we can also write down various higher order terms. So this is a term of way 2. It has 2 extra derivatives, and then you can have various higher order terms. And such negative powers of this z variable can arise if you integrate out various other fields on the worldsheet. So if you have some massive fields on the worldsheet and you integrate out, you naturally get effective actions of this type. So this is the general form of the effective action in this gauge. Now, as is well known, again, from conformal gauge, if we want to impose the Virasoro conditions, then that's only consistent for c equals 26, because only then the corresponding BRST operator squares to 0. Well, naively, it looks like this effective action that we're writing down has a central charge equal to d, because that's what we get just from this first term in the effective action. However, it turns out, as was found already by Polchinski and Straminger, that if you actually compute the central charge of this theory, then this beta term also contributes, even though it seems to be a higher order term. But if you actually compute the central charge, say by looking at the 2-point function in the presence and expanding around some long string configuration, then you find that this beta also contributes linearly to the central charge. And in fact, requiring that the central charge is equal to 26 exactly fixes this first term beta to be equal to d minus 26 divided by 12. And all the higher order terms do not contribute to the central charge. So just like in all the other formalisms, this leading way 2 term is completely determined and universal. However, here it takes some non-zero value, which turns out to be exactly proportional to d minus 26. So in this way, the nice roll of 26 dimensions shows up in any effective string action that you would write down for any long string in nature or in other types of physics. Now, the higher order terms, of course, are not fixed, and they match with a w bigger than 4 terms in the other approaches. So to summarize the construction of the effective string actions, we have various different approaches, and all of them indicate that we have universal terms at w equals 0 and w equals 2, and then the non-universal terms start at w equals 4. So if you translate to the energy levels, then that corresponds to this very high order of 1 over L to the 7th and the energy levels of closed strings. And in the S matrix, that corresponds to S to the 4th. So all the lower order terms are completely universal and determined just by the effective action that I wrote down. And you can check that in all these different approaches, if you compute the energy levels and scattering amplitudes, you get exactly the same answer. And in particular, if you compute the scattering amplitude of the Nabu-Goldstone boson, then the leading order term, as is obvious from this orthogonal gauge approach, since the first term is free, then the leading order interactions come from this first term, and they're proportional to d minus 26. So if you just consider on any long string in the universe, the scattering of the Nabu-Goldstone actions, you would find the special role of 26 dimensions there. So some tests of this effective action formalism that you can do, in some cases, we can just compute the effective action of a long string. For instance, if we have a solitonic string, we can just compute it in perturbation theory. Or if we have a holographic confining string in a weakly curved background, then we can just compute it using the worldsheet action, which is weakly coupled. And of course, the effective actions that we get all agree with this general formalism. And we can also compare the energy levels of long strings that we compute from this effective action to lattice simulations of various theories, and in particular, to simulations of confining strings in 3-dimensional and 4-dimensional Young-Mills theories. And there is indeed a precise matching with the expectations to the order with which they can be computed numerically, which these days is quite a large precision. Now, if we want to go further, so we basically said all that can be said using just the symmetries, but so far we haven't used unitarity. So one way to get extra constraints on the effective action is to use unitarity, as we heard in the first week of the conference, using the S matrix bootstrap. And this was analyzed in particular in this context in these 2 papers. So it turns out that even if you consider just the unitarity of the 2-to-2 scattering of these Navier-Goldstone bosons, then that already provides bounds on the leading non-universal coefficients of these weight 4 terms that I described. So in the 3-dimensional case, where there's only one coefficient, you can obtain a lower bound on it analytically from these considerations, while in 4 or higher dimensions, you can obtain lower bounds on it that are shown in this plot taken from this paper of Igor and Guerrier. Now, there are various generalizations of this effective string action. The generalization to open strings, which can have Neumann or Dirichlet boundary conditions, depending on the case, is straightforward, except that in that case, you can also have extra terms appearing as boundary terms in this effective action. If you have Neumann boundary conditions, like you would have, say, for massive quarks coupled to confining strings, then the leading boundary term that's allowed is just a mass term for these quarks, which is obviously allowed. And it turns out that on top of that, for either boundary condition, the leading non-universal terms that are allowed turn out to be at order 1 over L to the 4th. So that's their contribution to the energy levels in that case. And again, we can classify all of the allowed terms and match them, again, with lattice simulations of open strings. Another generalization we can do is to cases where we have additional broken symmetries, like supersymmetries. So of course, whenever we have additional broken symmetries, we would have extra massless fields on the string worldsheet, and we have to generalize the effective action to include them as well. In particular, for instance, if you consider the confining string in the n=1 supersymmetric Young-Mills theory, that breaks supersymmetry completely. So that has 4 Goldstinos on the worldsheet, and this effective action was considered in this paper. If you take the confining string in 2D Young-Mills theory, then in that case, we actually don't have any Navier-Goldstone bosons, but then you do have a Goldstino because it breaks supersymmetry. So there you have an effective action containing only the Goldstino. In many cases, we can also have strings that preserve part of the supersymmetry. So these are called BPS strings, and they exist, for instance, with those amounts of supersymmetry. And of course, in those cases, the whole effective action on the worldsheet is supersymmetric. Namely, we have an effective action that realizes linearly some of the supercharges and non-linearly some of the other supercharges. And in most of these cases, the full effective action has not yet been analyzed. So it would be interesting to analyze the effective action also in those cases. So I described some objects we can compute using the effective action. Let me describe also some additional ones. You can use the effective action to compute the width of long strings. So here I'm not talking about the intrinsic width of some string solution, but rather about the quantum width coming from the fluctuations of these Navier-Goldstone bosons. So if we have some open string of length L, then the fluctuations give it a width of length L of width log L, as we would measure, for instance, from the expectation value of x squared. So that we can use the effective string action to measure and compare it also to simulations. We can use the effective action to compute the expectation values of large Wilson loops for confining strings. And another very interesting application is that we can use this effective action to compute the spectrum of high spin states. Say in confining strings, these would be glue balls and mesons. And in fact, that is one of the historical origins of string theory, when people noticed that the spectrum of high spin states resembles the spectrum of rotating strings. So for open strings, if the string has a high spin, then it's naturally long, and you can use this long string effective action to control it. For closed string, it's actually more subtle, because closed strings in 3 or 4 space-time dimensions, if they rotate, then the classical solution looks like a folded string in this way, and then the effective action actually breaks down at the position of the folds. So we have to put some extra information to compute the energy levels of those strings. But if you're in 5 dimensions or higher, then you can have non-zero angular momentum in 2 different planes, and then the classical solution is non-singular. So in those circumstances, you can compute the energy levels of these rotating strings just from the effective string theory. And for instance, this is the ground state of the rotating string with angular momenta J1 and J2 as computed by Hellerman and Swanson. And again, you see the nice appearance of 26 dimensions in this computation. Of course, the long string effective action cannot be used for many other things. In particular, we obviously cannot use it to compute the spectrum of short string states, say the light mesons and glue balls in some confining gauge theory. Also, in many theories, we have a Hagedorn temperature, which we can identify by the radius of a Euclidean circle, where a string wrapped on that circle would become massless and then tachyonic, but that typically happens at a length which is of the order of the scale set by the string tension, which is beyond the range of validity of this effective string action. So these are examples of some things which we cannot use the effective string action to compute. So I'd like to use, so up to now, everything that I described was more or less rigorous. And I'd like to use the remaining 10 or so minutes to discuss some things that we can say about what happens if we try to go beyond the low energy effective action and try to say more things about the theory living on the worldsheet theory of these various different types of strings. So generally, if we have one of these strings, it can be again a solitonic string or a confining string, then we expect that around the scale set by the string tension, there should be some various additional modes, both in the bulk and on the string worldsheet, that will also be present, say some internal fluctuations of the string. And of course, those will also couple to the Navier-Goldstone bosons. So we expect our effective string action written just in terms of the Navier-Goldstone boson to break down at this scale of the square root of the string tension. However, it turns out that there are some specific types of strings where we have a limit where these strings completely decouple from the bulk fields. And in particular, this is famously the case for confining strings in large n-gauge theories, where as I showed in the large n-at-hoof limit, these confining strings completely decouple from all the bulk fields. And what that means is that in this decoupling limit, the 1 + 1 dimensional theory on the string worldsheet, including all the extra fields, so not just the Navier-Goldstone bosons, but any fields that we have living on this 1-dimensional string worldsheet, should make sense at all energy scales, not just as a low energy effective action, but since it decouples from the bulk physics, this theory should be a consistent unitary theory in its own right at all energy scales. In particular, we expect that in such cases, it should also be possible to think of the worldsheet as a fundamental string, such that when we quantize it, it will give rise to the full bulk physics perturbatively in 1/n. And of course, we have various examples of that in holographic confining backgrounds, where we have some full string theory background with some fundamental string, but then these backgrounds are confining such that if we look at long string configurations of those fundamental strings, then the only light modes are the Navier-Goldstone bosons, and we recover the effective actions that I described in the first part of my talk. But we expect that in any large n-gauge theory, the worldsheet theory should be well defined by itself, and perhaps also in other circumstances where the string decouples from the bulk. So we have this 1 + 1 dimensional worldsheet theory, which should make sense, but in general, there's no reason why this should be a weakly coupled theory. We a priori say in confining strings, we have no small parameter that would make this theory weakly coupled. It is weakly coupled, as I mentioned, in some holographic confining backgrounds where we can have a limit where the background is weakly curved and then the worldsheet theory is weakly coupled. But generally, we do not expect this to be the case. And also on general grounds, we do not expect this worldsheet theory to be just some bosonic string or even an NSR superstring, but it seems that we usually need some more general formalism of string theory that can incorporate also Ramon backgrounds. So for instance, perhaps the pure spinor formalism is needed in these cases. So what can we do in these circumstances where we expect to have a strongly coupled theory on the string worldsheet? So I'll describe two types of approaches that we can take to trying to solve this problem. Of course, it hasn't been solved yet, but we can either try to take a bottom-up approach or a top-down approach, and I'll describe each of these in turn. So specifically, if we consider the confining strings of large n Yang-Mills theories in, say, 3 or 4 dimensions in the large n limit, then we expect to have some well-defined worldsheet theory describing them, but there's no reason why it should be weakly coupled because those theories have no small parameters. So a priori, it seems very difficult to try to imagine writing down the Lagrangian for those theories. And the best hope would be if for some reason this worldsheet theory happens to be some integrable theory. Now, I don't know of any reason why the worldsheet theory in these cases should be integrable, but quite surprisingly, it was found in these papers that these strings actually do turn out to be very well approximated by some integrable models on the string worldsheet. So if we have some integrable model on the string worldsheet, then of course we can compute the string spectrum exactly, not just in the 1/L expansion, but we can compute the energy levels and the scattering amplitudes of the Navier-Goldstone bosons exactly at all orders in 1/L. And then we can compare the results from these integrable theories to say lattice simulations of Yang-Mills theories. And these people found that these two completely different computations actually match very well, although not completely exactly, but they match to within the level of a few percent. So what they found is that for 3-dimensional confining strings, the string worldsheet theory is actually well approximated by just taking the bosonic Nambu-Goto action. So just this action that appeared already several times in this talk. So as I mentioned, in general, this action is some interacting theory, which is not integrable. Of course, in 26 dimensions, we know that it is integrable because in the orthogonal gauge, it's equivalent to a free theory. And it turns out that also in the special case of 3 space-time dimensions, where we just have one scalar field x, then also in that case, this theory turns out to be integrable, which means that we can exactly compute the energy levels of this theory, even down to a very small values of L, where we would expect the effective theory to break down. So we can compute these energy levels, compare them to the energy levels that we find, say, from lattice simulations of Yang-Mills theories. And it turns out that these two computations actually match very nicely. But the reason for that is still not known.
5 minutes, Ofer.
thank you, that really perfect. Now, in the four-dimensional case, again, they found that you can match the energy levels to some integral model, where the integral model in this case contains, in addition to the two Nambu-Goldstone bosons that we have in this case, it contains one extra massive worldsheet field, A of sigma, which is a pseudo-scalar field, which couples to this specific combination of the Nambu-Goldstone bosons. So there's some specific parity odd combination of the Nambu-Goldstone bosons that you can write down and couple it to A. And it turns out that this theory happens to be integrable for some specific value of this coupling QA that's in front of this term. And then there's some extra parameter in this theory corresponding to the mass of this pseudoscalar field. And it turns out that for some specific mass of this field, the spectrum that you get matches the confining string spectrum of four-dimensional Yang-Mills theory very well, including in particular, you can find on the lattice modes that correspond to excitations of this pseudoscalar field. Now, as I mentioned, the reasons for this approximate integrability are not yet clear, but it raises the obvious conjecture that maybe we can somehow systematically expand the QCD string action around these integrable theories, perhaps by adding some additional fields or interactions, and it would be very interesting to understand if such an expansion makes sense or not. So that would be a bottom-up approach. We can also try to take a top-down approach to constructing the QCD string. So our expectation from holography is that the QCD string, like the strings that we found to describe other gauge theories, should have some holographic description in which the worldsheet theory should have some extra field phi of sigma that can be thought of as the radial direction of the space in which this string moves in. Now, if we have long strings, then they will naturally sit near the minimal value of this coordinate phi. And if we expand around those configurations, this field phi is massive, and we can integrate it out and reproduce the effective string action. But if conversely, we try to look at configurations at large values of this field phi, there we know that at high energies, these field theories are asymptotically free. So in that regime, we should reconstruct the free gauge theory, and in particular, the worldsheets in this, the Feynman diagrams, or the Feynman worldsheets should become just fishnet Feynman diagrams of our gauge theory, and the worldsheet actions should become topological, where the states are just described by some string bits. So the strings in that regime should just be described as some bound states of gluons. And of course, it would be very interesting to construct such an action that interpolates between these two different limits. From this point of view, the natural way to try to construct such a string action would be to start from a string dual for a free gauge theory. And at least for the case of n equals 4 super Yang-Mills theory, some versions of that string dual were suggested already in the past, and we'll have another talk about that by Matthias Gabaldia later this week. So if we can generalize these constructions for a string dual of the free pure Yang-Mills theory, then and then deform that by the gauge coupling, then that would give us a first principles construction of the QCD string action. But of course, that we don't yet know exactly how to perform that construction. Another way to construct a top-down version of the QCD string would be to start from some string theory whose holographic dual is known, and which we can deform such that in a limit we can get to the three-dimensional or four-dimensional pure Yang-Mills theory. The fact that such deformations exist, and as I'll review in a minute, shows us that the QCD string definitely can be viewed as a limit of the standard fundamental string when we just perform some deformations of it, at least if we don't encounter any phase transitions when we perform these deformations, which we don't know how to prove. As an example, we can start from the n equals 4 super Yang-Mills theory and just add masses to all the scalars and fermions. And then if we take the limit where those masses go to infinity while taking the 't Hooft coupling to 0, and keeping fixed the low energy QCD scale, which is this combination, then that limit should give us the four-dimensional QCD string. Of course, doing that in practice is very difficult because we need to first understand the precise string dual of mass deformations of n equals 4, which are very complicated backgrounds as found by Polchinski and Strasser. And then we also have to take those configurations and take this high curvature limit of Yang-Mills squared n going to 0. But in principle, this is a well-defined question in string theory that we should be able to answer. And similarly, we can use Witten's construction of 3D Yang-Mills theory as a limit of the n equals 4 super Yang-Mills theory on a circle when we take antiperiodic boundary conditions for the fermions. So also there, we can take some limit of this construction, which gives us the three-dimensional Yang-Mills theory. So there should be some limit of this string theory that gives us the 3D QCD string. But again, the full string background describing this n equals 4 super Yang-Mills theory on a circle is a rather complicated background for which we don't have an exact worldsheet construction, and definitely we don't understand it in this limit. So that's still an open problem. So let me summarize. So in this talk, I argued that the effective action of any long string that we can find in nature or in any part of physics has several universal terms that control many of its low energy properties. And in particular, some of these terms nicely exhibit the special role of 26 dimensions. If we have large and confining strings, then I argue that there should be some description of the worldsheet at all energy scales, not just in this lower energy effective action, but this is yet to be found. And it's interesting to ask whether there are also any other examples of, say, non-confining strings where there would be some similar limit where they decouple from the bulk and where we would have an all-scale description of the string worldsheet. It's also interesting to ask, can we learn from other cases where we do understand the full string theory dual of some gauge theories in cases where the worldsheet action is topological? So for instance, we do understand that for 2D QCD or for the string dual of Chern-Simons theory. So in those cases, the worldsheet theory is topological, but we do understand the precise matching from the gauge theory to the string theory. So maybe these cases can also be used to teach us about the full worldsheet action for these confining strings. So there are many interesting open questions, and we'll have some more discussion of those in a few hours, led by Dubovsky and Klebanov. And I should emphasize that most of that discussion will be before the football game, before Spain and Croatia. So also football fans are welcome to attend the discussion. So thank you all for listening.
Thank you very much, Ofer. And now we have 10 minutes for questions. Please go ahead. Who wants to ask? Please raise your hand.
So I see that she raised his hand. So
okay, so go ahead.
Hi, Ofer. I have a couple of questions. First is the one I raised in the chat. So about the D equals 3 string, where if you assume integrability, when you say you can determine the spectrum for all I assume you mean the string wrapped around the circle. That's compactified.
Right.
But if you just consider a short string, is there any way to argue that you can get the exact result, or is that supposed to be determined by integrability?
Yes, I think if you assume that that is the full string worldsheet action, then I think then you can quantize that for a string of any length. And yes, so I think that with that, of course, we know that that assumption is not true. I mean, we know that that is not the correct description at short scales. But if you assume that, I think you can try to.
What I'm worried about is that usually the integrability is about the asymptotic asymmetrics of the ensembles and bosons. Now, if you have the folding point of the spinning string in 2 + 1D, is that really determined by this integrability assumption? Is there some freedom there?
Right. Yeah. So that is a good question. So I'm not sure if this integral model can really deal also with this case of folded strings. I mean, maybe Sergei can answer if he's thought about that. So that's a good question. Yeah. So I'm not sure.
Right. That's why I was asking, because it's not intuitively not obvious to me that the short string spectrum can be determined by that assumption.
Right. No. So I agree. Yes.
So another question about the confining string is that is there any no-go result that says the holographic confining background has to have R flux?
Yeah, that's a good question. I think there almost is. I mean, so in flat space, there is this famous theorem by Kutasov and Seiberg that if you have a string theory with no tachyons, then it has to have degeneracy between bosons and fermions. So if you're looking at the QCD string, which doesn't have that degeneracy, then of course you cannot have just a bosonic string, and that theorem holds also for NSR strings. Now that theorem, it was proven in the case of flat space, if you have, say, R4 cross something, but I think, although it hasn't been done rigorously, I think you can generalize it also to warped backgrounds, like confining string backgrounds. So I believe that one can prove that the standard bosonic and NSR formalisms cannot describe a theory that doesn't have both Fermi degeneracy, but that hasn't been rigorously proven. I mean, so maybe we can leave it to the discussion to see what other people think about that, but I believe it's true, but it certainly hasn't been rigorously proven.
Thank you.
Okay, Daniel Harlow.
Hi, Ofer. I was just wondering, so you made a comment about something that's puzzled me for a long time, which was when it is that by quantizing the string, you can also sort of recover the bulk theory as well. So can you say a little bit more about that? How do you, I mean, you just said just because the string makes sense to high energies, that's enough. But is that really true? Can you
right. So of course it's not. Yeah. So sorry, I did not mean to imply that it's enough. So of course, one requirement is that the string worldsheet theory will decouple from the bulk and will be valid at all energy scales. But the other requirement, of course, is that you should have some recoupling limit with which to set up string perturbation theory. So you should have. I mean, so as we know, in these contexts, I mean, you do have within the worldsheet action, you do have some parameter that controls string perturbation theory, and there has to be some limit of your theory where that parameter is small. So in large and confining theories, we know that the parameter would be 1/n, so such a limit does exist. But in general, I think you need these two requirements, that you have an action that's valid at all energies, and you can take a limit where the coupling constant between different strings that governs the genus expansion goes to 0. So if that's true, I believe it should be possible to set up string perturbation theory.
Okay, Rajesh.
Hi, Ofer. Thanks for a wonderful talk. My question was about these, when d is not equal to 26, when you're away, when you have this additional term that you wrote with inverse power z, is there some sense in which this and these terms which contribute the 26 minus d to the central charge, is there a sense in which they can be understood as some effectively a Liouville-like mode or something like that?
Well, I think the answer is yes and no. I mean, so you can always introduce a Liouville mode to the metric, which would be this. I mean, as I said, you fix in this gauge the metric to be proportional to e to the phi delta v. So you can always, so that phi is some combination of the Navier-Stokes bosons, but you can sort of. But if you have also additional modes on the worldsheet, then it would be determined also by these other modes. So in general, you could imagine that you have this extra Liouville mode, and then when you integrate out, you generate this field, and that's in fact the point of view that was taken by Polczynski and Strominger in the original paper. But usually, if you consider the effective action on the string, then say for the holographic strings that you understand, you see that you have many modes on the worldsheet. I mean, not just a single mode. So there would be some combination of all these massive fields that would serve like a Liouville mode. But you also have additional modes. And in those cases, the effective action would come from integrating out all of these fields. So I'm not sure if in general there would be some special mode that plays the role of the Liouville field and which really guarantees this term. But well, okay, there is one context where that would be true, which is the point of view taken by, I think, Kellerman et al. In their paper, which is that if you do include this extra metric variable, then, or more precisely, if you consider the conformal anomaly on the string worldsheet, then in that context, there is a special role that's played by this Liouville mode. And in that context, you can view this extra term as the thing that cancels the conformal anomaly on the worldsheet. And in that context, it is natural to write it using this effective Liouville variable. So in that context, it would come from that. But in general, if you're looking at the action at higher energies, I don't think there would be any special role played by the Liouville fields. I mean, in general, you would have also many other fields on the worldsheet at the same energy scales.
So
okay,
sorry,
node IAS.
Okay, we can.
Yeah, we can continue the discussion session, of course.
Yeah.
So in your discussion of theories where the effective string action goes up to high energies, I just wondered what you'd say about the Polyakov model in 3 dimensions, where the confining scale is enormously small. So the string theory, it would seem, is valid way above the confining scale, but your criteria for weak coupling isn't satisfied.
Right. Yeah, that's an interesting example that I haven't shown much about. In that example, actually, the whole effective string action sort of breaks down in the sense that you don't start from the string tension as the leading term, but at high energies, this other rigidity term plays the main role, and it's asymptotically free, so that you can get an action that's valid at all energy scales. But yeah, I haven't really thought about whether that action can be used to define a fully consistent string theory. I mean, as you said, if there's no weak coupling parameter, then I don't have any reason to think that that would be possible. But it's it's an interesting question. I don't know.
What was the statement you made about the rigidity term?
I just mentioned that in the context of low energy effective actions, I mentioned that the rigidity terms can always be eliminated if you expand around a long string with the tension as the leading term. Then that rigidity term doesn't play any role. But in what Polyakov did, I mean, he considered actually a high energy expansion of the string. And in that context, it is legitimate to keep this rigidity term. And indeed, one can write down an effective action where the full worldsheet action, which just includes this coupling, which is asymptotically free. So I was just clarifying a possible confusion between the appearance of the rigidity term in Polyakov's formalism and the fact that it does not appear in low energy effective string actions.
Thanh Son.
Hi, Ofer. I wonder if there is effective action for long rotating strings with massless quarks at the end.
Yeah, that's a very good question. So I mean, if the quarks are not dynamic, if the quarks are not dynamical, and so you don't include quark loops or anything, then yes, then you can write down. Then in fact you just use the same effective string action, and you just have to add some boundary terms on top. So this is one of the generalizations that I mentioned. So for that case, we do have an effective string action. Of course, in an actual theory of quarks, you would also need to take into account dynamical quarks. But if you have some limit where the quark loops are suppressed, then yes, then and in particular, that is why this effective string theory matches with high spin mesons in QCD. I mean, where we do have light quarks at the ends, and the effective string action can be used for that case. That's sort of the maybe even the most obvious place to use it. Yes.
Can I continue? Yeah, maybe I can ask you privately some more questions.
Okay, sure. Or in the discussion session, I'd be happy to discuss all these issues further.
Ofer, I would like to make a very short comment. What is missing in my eyes from your discussion is how is it related to nature? And so when, in particular, if you're talking about the confining string, then there is a lot of input that you can learn from the structure of the spectra of resonances, decay width, scattering amplitudes, and that should be an input to the construction of this effective long string theory.
Definitely.
Okay, so if there are no more questions, let's thank Ofer again. And the next speaker for this morning session is Thanh Son from Chicago University, and he will talk about some new developments in fractional quantum Hall effect. Please.
Okay, so can you see my slides?
Yeah.
First of all, I would like to thank the organizer for giving me the opportunity to give this talk at the string conference. I'm going to tell you about some new developments in the physics of the fractional quantum Hall effect. The fractional quantum Hall effect is a very rich phenomenon that keeps giving new insight, new surprises in condensed matter physics. But due to the lack of time, we are going to see only, we are going to look at only very narrow and very few aspects of this problem. First, I will formulate the problem of the quantum Hall physics in a way that makes connection to the formalism of field theory. And then I'm going to mention two relatively new developments in fractional quantum Hall physics. First is the nature of the so-called nu equal 5/2 state, and then about the nature of the excitation called the magnetoroton. Since it is a string theory conference, string 2021, it's good to start the talk by mentioning what unites all physicists. We are all searching for the theory of everything, including condensed matter physicists. In particular, here you see an article in PNAS in 1999 of Laughlin and David Pine on the theory of everything. And they try to find a theory of everything. And here is their version of the theory of everything from this article. You see here, it is just Hamiltonian describing a collection of nuclei and electrons interacting with the Coulomb potential, which describes quite a large number of physical systems with good accuracy that we encounter in condensed matter physics. So the story in quantum Hall physics can start with this type of theory of everything. We start with, it's even a simpler theory. It's a theory of two-dimensional particles, electrons, interacting with external magnetic field, here E, here A, and Coulomb interaction. Between themselves, the electrons interact through a Coulomb interaction. So the usual things that is said with this Hamiltonian is that if we quantize this system, ignoring the interaction for a moment, then we see Landau levels of the electrons. In 2 dimensions, the Landau level are discrete. The distance between the lowest Landau level in the next is B divided by M, where B is the magnetic field and M is the mass. what makes the problem interesting is that we can take the limit of the mass going to 0. In this case, the lowest Landau level is singled out because the distance separating it with the next Landau level is b divided by m goes to infinity. So if you want to if one deals with less electrons than the degeneracy of the lowest Landau level, we have a very non-trivial problem of trying to diagonalize a Hamiltonian, which is basically the projection of the potential energy on the lowest Landau level. And here the non-triviality of the problem is manifest. The coupling constant E squared plays no role as cannot play the role of the expansion parameter because it is the overall factor multiplying the Hamiltonian. We can write this theory slightly more field theoretical form by using the second quantized language form, second quantized formalism. The action of the theory is written here in terms of a field psi, which is the electron, and this electron coupled to A0 and AI through themselves with the some two-body interaction. And here I also include for theoretical simplification a magnetic moment coupling of the electron with a magnetic field B. We are interested in the physics in B, background field B not equal to 0. What we know is that if G, this G factor of the electron is equal to 2, the Schrodinger equation has 0 mode. It has 0 mode not only in the background of constant electric field, but in any magnetic field. And the number of 0 modes is equal to the number of magnetic flux quanta going through our system. And now these 0 modes are the modes that survive if we take the limit m goes to 0. The mass goes to 0. It seems that this action becomes singular in the limit m goes to 0, but in fact, it doesn't. Part of the physics remains finite. The lowest Landau levels have 0 energy all the time, and their dynamics is determined by the energy scale of V, not of 1 over m. And so the problem of quantum Hall effect can be formulated as trying to find out what is the behavior of, for example, the partition function of the theory in the limit m goes to 0 in the presence of a magnetic field. What is Z as a function of A0 and AI goes to when we take m goes to 0. Provided that we are working in the vicinity of some finite magnetic field configuration. Let me introduce one notion that is the filling factor, nu, which is the number of electrons divided by the number of states on the lowest Landau level. And that number is assumed to be less than 1 in this talk. So for gap state, the effective field theory describing the physics below the energy gap typically is a Chern-Simons type theory. For example, in the most famous of fractional quantum Hall state, nu equal 1/3. This Lagrangian is the Chern-Simons, describing a Chern-Simons action of a dynamical of a gauge field little a that is coupled to an external gauge field capital A. So if we naively integrate out this small a field, we get the Chern-Simons term. ADA, A is the external magnetic field with the fractional coefficient, and that describes, as one can check, the fractional quantum, the fractional value of the Hall conductivity. One can also put the system in background metric, and there is a coupling of the electromagnetism with the curvature of space that is proportional to the shift. That's a so-called shift of the quantum Hall state. So the physics of a gap state, at least for energy below the gap, is described by typically by topological field theory. A more difficult set of questions are related to gapless state or states with a small gap a gap which is much less than the natural energy scale of the problem. For example, this state would appear in a filling factor nu equal 1/2 or nu equal 1/4, or in general for state with 1 divided by 2n. But in practice, these are only nu equal 1/2 and nu equal 1/4 that one can realize this state in nature. Near half filling, nu equal 1/2, there is an extra symmetry that allows us to get additional insight into the problem. And now we know that the effective theory describing a half-fill Landau level has the form of a theory of a so-called Dirac composite fermion. Such a composite fermion has different quantum number than the original electrons. In particular, in the Lagrangian of that Dirac composite fermion, there is no direct coupling to electromagnetism. The composite fermion is neutral. It's coupled to a dynamical gauge field, and through that dynamical gauge field, it's coupled to our external gauge field. The transition from electron to the Dirac composite fermion is some kind of particle vortex duality. Through it, we map the density of this new composite fermion with the density of magnetic fluxes in the original theory. And vice versa, the density of the electron is related to the strength of the magnetic field that is coupled to the composite fermions. This map has a feature that it maps a half-fill Landau level of the electron to a Fermi liquid of the composite fermion, and that one can use it to explain certain features of the quantum Hall effect at or near half filling. In some sense, the physics of fractional quantum Hall effect near half filling is an experimental realization of some field theoretic duality. So there are many talks, many previous works that has been written on these topics, which I'm not going to go through all the fine detail, in particular how one can make sense of the fractional quantization of the Chern-Simons coefficient here. One of the topics that has been attracting a lot of attention lately is the nature of the nu equal 5/2 state. It is the only even denominator gapped quantum Hall states that has been observed. And it is basically a half-fill Landau level. We fill two Landau levels of spin up and spin down electrons, and then add up to it the half-filled first Landau level of one component of spin. The most well-known candidate for that quantum Hall state was proposed by Moore and Reed. It's called the Pfaffian state. Later on, an alternative candidate has been discovered, the so-called anti-Pfaffian state, which is simply the particle Hall conjugate of the Pfaffian state. On the lowest Landau level, one can make a particle Hall conjugation, replacing a field state, a field orbital with the empty orbital and vice versa, and construct the anti-Pfaffian state. From the point of view of the theory of the composite fermions, these states arises as BCS pair state of the composite fermion. So here how they are realized. A simplest pairing between the composite fermions has this tensor structure. Roughly speaking, it's an S-wave pairing between fermions. And it turn out to correspond not to a Pfaffian state, neither to the anti-Pfaffian state, but to a new state, which has been called the pH Pfaffian state. pH because that state is particle Hall symmetric. The familiar Pfaffian and anti-Pfaffian state correspond to a more complicated D-wave pairing between the composite fermions. Numerical simulation so far seems to favor anti-Pfaffian state, or a smaller set of simulation favor Pfaffian state. But recent experiment done in Weizmann's Institute seems to prefer the pH Pfaffian state. The tension between the result of the numerics, which has certain limitations. For example, it does not include disorders or mixing between Landau levels, and experiments have not been completely resolved. And it would be interesting to find out what is the real quantum Hall states that is realized in nature. So let me go to the second topic, which is the so-called Magnetoroton. Consider a gapped fractional quantum Hall state like the nu equal 1/3 state, and one can ask what is the lowest neutral excitation. Why we are interested in a neutral instead of charged excitation? That's because we are living in a finite magnetic field. A neutral excitation can have finite momentum, and we can talk about the dispersion relation of that excitation. That excitation has been studied, this question has been posed and studied variationally by Gerwin, McDonald, and Platzmann, and subsequent works. And it has been found that there is a branch of modes, typically with a dispersion relation with a minimum at non-zero Q, that has been called the Magnetoroton. So here I'm showing the original variational result of Gerwin, McDonald, and Platzmann for nu equal 1/3 state, and a later result for nu equal 7/3 state, which is 1/3 state in a higher Landau level. One can ask the question, what is the operator that creates a Magnetoroton? It's a quasi-particle, which should be created by acting a certain operator on the ground state. We can look at the in which correlation function this Magnetoroton appears. In particular, it appears in the density correlation function, rho rho, as a function of omega in Q. That's a pole at omega equal delta. But it turned out that the residue at that pole goes to 0 very quickly as Q goes to 0, a fact that has been known already to Gerwin, McDonald, and Platzmann. In particular, the power here is Q to the 4th, which is quite interesting because gauge invariants require only Q squared. We will now see that this fact that this correlation function is Q to the 4th is a consequence of a higher rank conservation law. So let's write down the law of conservation of particle momentum, particle number, and momentum. So for particle number, d rho over dt rho dot is equal to divergence of the current. And the conservation of momentum has this form. Here, one thing that is important is that for the system of electrons, the momentum density is equal to the mass of the electrons times the U1 current. This fact allows us to take to simplify the conservation law in the limit of lowest Landau level, which is m goes to 0. In the case m goes to 0, this law becomes just a balance of force between basically the pressure and the divergence of the stress tensor and the Lorentz force. And that can be used to solve the Lorentz force, solve the current in terms of the divergence of the stress tensor. J is just a first derivative of T. So here I have suppressed all the indices. And when I put this equation back into the conservation for rho, we get rho dot plus some structure involving second derivative of the stress tensor to be equal to 0. This is what sometimes is now called a higher rank conservation law, equation of conservation that involves first derivative in time, but second derivative in space. And so here we see right away why the current correlation, density correlation has to be equal to Q to the 4th. At finite omega, basically rho is second derivative of something, which is q squared. Rho should be equal to q to the 4th. That can be formalized further by coupling the system to the metric, in addition to coupling to the electric field, to the potential, electric scalar potential A0. And one can show that the lowest Landau level limit physics is invariant under a certain volume preserving diffeomorphism that leaves the B field unchanged, but changes the metric and the A0 field. Here I've written down the linearized version of that transformation. The transformation of the metric is nothing but linearized diff, where the diff coefficient correspond to volume preserving two-dimensional diff parameterized by one scalar function lambda, and A0 is transformed under this as a U1 gauge potential. So the Ward-Takahashi identity, the Ward-Takahashi identity is the high-rank conservation law. Okay, so we now know that this operator that creates the magnetoroton is probably not optimally, is not really the density, because rho does not create the magnetoroton very efficiently at q goes to 0. The density-density correlation function has a residue at the magnetoroton, but the residue goes to 0. The momentum of this magnetoroton goes to 0. The operator that creates this q equal to 0 magnetorotons turn out to be a stress tensor. So here we have a very interesting situation in which the lowest state in the system is created by acting a component of stress tensor, namely the TZZ and TZ bar Z bar on the vacuum. So the spin of the magnetoroton is either 2 or -2. And one can ask which one of these create the magnetorotons. That question has been studied numerically by in this paper. And for example, nu equal 1/3 state, they found a strong suppression of spin -2 state as compared to spin 2. So this line here, our spin 2 spectral density, and round point barely visible here correspond to spin -2 mode. So in nu equal 1/3 state, the magnetoroton has spin 2, not -2. And one can write down certain sum rules that motivate or make this fact understandable. One can introduce the spectral density of the holomorphic or anti-holomorphic component of the stress tensor and derive a sum rule that relates a certain integral of the difference between them with topological properties of the quantum Hall state called the shift. And if the integral is dominated by a single mode, we know that when the shift is bigger than 0, we have this mode has to have spin 2, and if the s less than 1, this mode has to have spin -2. And that is what have been found in the case of nu equal 1/3 state numerically. One can use polarized Raman scattering in principle to determine the spin of the magnetoroton. One just need to shine photons with one circular polarization on the system and observe photons. If this photon is observed with a different polarization, then it means that part of the spin of the electron has been transferred to the excitation in the quantum Hall state. And in this way, one can determine the spin of the magnetoroton. Now, if we go back to the nu equal 5/2 state, the arguments based on our sum rule suggest that in the Pfaffian state, the shape of which is known to be 3, the magnetoroton has to have spin 2, and anti-Pfaffian state spin has to be -2. The case of pH Pfaffian state is special because the shape is equal to 1, so both the magnetoroton can have both spin 2 and -2. And I hope that this can be used in experiments involving polarized Raman scattering to probe the state that is realized, that we have now, the new equal 5/2 state. So let me skip these topics and go to my conclusion. So the fractional quantum Hall effect is an important theoretical problem. In this talk, we have discussed two sub-problems. One is the nature of the new equal 5/2 state, and the other is the nature of and the spin of the magnetoroton at q = 0. In particular, I have highlighted the fact that polarized Raman scattering can be used, one should be able to use it to distinguish different quantum Hall state, in particular different candidates to the 5/2 state. Thank you very much for your attention.
Thanks a lot. Okay, questions? There is a question from Tifel. Go ahead. From TIFR, there is somebody that wants to ask.
That's me, sorry, Shiraz.
Hi, Shiraz.
Hi, Kobe. So thanks a lot for the talk. I'm asking a question that may be completely ignorant. You explained to us that for the new equals half state and for the new equals 1/3 state, the analysis of that state was simplified by taking this limit m goes to 0 with that kept just the lowest Landau level and sent the rest off to infinity. I presume you can't do the same for the new equals 5/2 state. So does that complicate the analysis of that state? And how do you do the analysis there? Sorry for the elementary level of the question.
Most of the theoretical treatment of the 5/2 state is actually done in that limit. So one can be bothered by the fact that there are Landau levels, two field Landau level, and the next Landau level is half field. But these two field Landau levels are basically inert. They decouple, and all the interesting physics happen on the next to lowest Landau level. So this limit is still sensible. M goes to 0 for new equal 5/2 state, and that is where all the numerics, most of the numerics has been done.
Thank you. Could I ask a follow-up, Kobe?
Go ahead.
Okay. Is the particle hole symmetry still a symmetry in this state? I mean, given that the lower levels are filled with electrons and not with sort of holes?
Since these states decouple, particle hole symmetry is still a good symmetry of the 5/2 state. In the limit that is certainly a little bit far from what happened in real experiments.
Okay, node IAS.
Yeah, I was wondering whether besides this spin 2 particle, there are also higher spin particles.
In the composite fermion theory, there are infinite number of these higher spin particles, at least for the state whose filling factor has the form n divided by 2n plus 1. These states have spin starting from 2, 2, 3, 4, and etc. These are not easily excited by photons, because with photon we can only transfer in Raman scattering spin 2, but in principle they should exist.
Okay, Gregor Mew.
So I had two questions. One is the particle hole symmetric Pfaffian state has non-abelian excitations, right?
Yes.
And the other is you talked about this calligraphic S, and you mentioned it was the shift. It was a topological quantity. Is there a way of saying what that topological quantity is in terms of the Chern-Simons theory? or some other mathematical characterization of this topological quantity?
So this can be defined by putting the quantum Hall state on a sphere. When we put the system on the sphere, the relationship between the number of electrons and the number of flux quanta, this linear relation between them has an offset, and that offset is actually proportional to the Euler characteristics of the manifold on which the quantum Hall state lives, and that's how one can define the shift. So, for example, in the Laplace 1/3 state, the offset is equal to 3, and so that's how one defines the shape of the Laplace state to be 3.
So how did you calculate the shift for the various kinds of Pfaffian states?
One can just put them on a sphere. So, for example, the Pfaffian state, instead of writing Zi minus Zj, one use so-called U and V coordinates on the sphere.
Yeah.
Are there any more questions? Okay, so if not, let's thank Thanh again. Thank you. And I guess there is a breakdown.
Hi, Pedro. Is it possible to try that the slides will go for the discussion?
Sure, yeah, good idea, yeah. Well, let's do it, yeah.
Well, I'm not the first there, but if nobody...
It doesn't matter, no, it's better.
If everybody else is confident that it will work for them. Yeah, let's... what do I do? So I should be able to share the screen, right? Okay.
Yeah, you should. And he's making now the people of the second section co-hosts. Yeah.
So do you see the slides?
I see the slides.
And do they?
Perfect. Let's see if I see your pointer. I don't see your mouse.
Here?
Now I see your mouse. Yeah.
Okay, good. Okay.
Maybe we could test Igor and or John or Horacio. Let's see if they are already on.
I need another minute.
Oh, no problem. I think Horacio Casini is not yet online, I think. Igor was online, I remember. Anyway, I'll be right back. Nathan can help you, I guess. Hi, John.
Hi, Pedro. Okay, I'm going to try now to share my screen.
Very good. We can see the full screen, everything. I don't know if you want to share just the PDF.
How's that?
It's perfect. We can see both the screen and your pointer on the upper left.
Okay, great.
And yeah. It's perfect. Thanks. Okay, since I'm not seeing.
Dashi, do you want to try to share screen? You're now co-host also.
No, but
sorry. So I'm supposed to be chair next session.
Yeah, but you can check your.
But I don't need to share screen.
Okay, that's true.
Yeah.
I forgot.
Hello. Yeah. So shall I just start the session just the time? 11:20.
Yeah.
Okay. Yeah. I'll
just. There's no announcement.
Nathan, do you want me to put the page on with the break?
Sure.
Okay. Then if people, okay. So I'll go get a coffee and I'll be right back.
Yeah. Horacio, if you want, we can share screen now. If you want to try your share screen.
Hi there. Okay.
Hi, Horacio. So if
Hi
you
there.
just press share screen, it should get rid of this one. But if not, I'll get rid of it. Should ask you if you want to stop the other person.
So I'm sharing screen now.
Okay, very good.
Okay.
Yeah.
There?
Yeah, perfect.
Okay.
Mouse. Thanks, Horacio.
Good evening, Takayanagi-san.
Good evening.
Very late at night.
Quite late at
night.
Yes, 11 p.m. Hello, Horacio.
Hi, Tadashi.
Yeah. We have 5 minutes.
Yeah. Still.
Hi, Horacio.
Hi there.
Nice to see you. Nathan, sorry, did Igor test his screen share?
I haven't seen Igor yet.
Okay. Let me check.
If you want, you can write to him and see.
Horacio,
yeah.
Do you share screen?
Yes, sure. There, you can see it.
Yeah, I can see that. Point out. Yeah, box. Okay, so just time. So let's start this next session. The first speaker is Horacio Casini from Bariloche. He will tell us about generalized symmetries, algebras, and entropies. Please start.
Okay, thank you. Thank you to you all for having me today. This is a talk about a recent work done with Marina Huerta, Javier Magán, and Diego Pontello. This is a brief plan of the talk. I start by describing a simple and unified perspective on generalized symmetries and completeness. Though this approach may be more abstract than the usual description, we think it simplifies the terminology in some sense and clarifies certain issues, and it may lead to generalizations. In particular, the approach starts from a question unrelated to symmetries. It's a question about the structure of the net of operator algebras attached to regions in quantum field theory. And the answer to this question is that failure in simple properties, simple axioms of the net of algebras, additivity and duality, lead to the fact that it can be multiple algebras from the same region, and this can be interpreted in terms of generalized symmetries. It also clarifies the fact that symmetries always come in dual pairs. In the second part of my talk, I will use this fact that you have multiple algebras from the same region in order to describe how to define entropic order parameters. These are entropic quantities that you can define and measure the statistics of non-local operators or topological operators. This entropic order parameter satisfies a quite intriguing relation that we call the certainty relation that relates the statistics of dual entropic order parameters. And at the end, I will describe the expected behavior of these order parameters and some heuristics. So let me start describing operator algebras and causal regions. Let us take some set A of operators in Hilbert space. We can define then the commutant, that is a set of operators that commute with all operators in A. And there is a very nice theorem by von Neumann that tells that for a von Neumann algebra, that is general algebra in finite dimensional case, and von Neumann algebra for infinite dimensions, an algebra is a set of operators that is equal to the double commutant. And you have a further structure, the intersection of algebras are algebras, and you can also define the generated algebra of two, just taking the union and completing it by the double commutant. For region in space-time, you can define very similar things. You can define, for example, you take a region, you take the causal complement, that is just the set of points of space-time which are spatially separated from W. In this case, for example, this diamond, this double prime is the causal complement, and we define a causal region as a region which is equal to the double causal complement as this diamond shape is set here. And there is also the intersection of two causal regions is a causal region, and you can define also the generated causal region of two by taking the union and completing it. So there is a parallel thing here, and then in a quantum field theory has a preferred set of algebras described by the degrees of freedom associated to regions. And then one can ask what are the minimal relations that satisfy algebras and regions in a quantum field theory. And these are the two minimal relations. One is that if you have a region that is included in other region, it must be the case that the algebras of operator attached to this region are also included. This is called isotony. And causality for a relativistic theory is just the fact that an operator attached to a region R has to commute with all operators that attach to the complementary region R prime. So one can think what can be enhancing this axiom, and the maximal harmony between algebras and regions, the maximal possible relation that can satisfy, is given by these three axioms. So the first one is called Hug duality, and is an enhancement of causality, where you say that the algebra of a region is not just included in the commutant of the outside part, but is equal to that. It's a kind of completeness. requirement. The second is additivity. It tells you that the algebra of the union of two regions is generated by the algebra of the two regions, and this is quite natural in quantum field theory because you generate the operators in a region by operators in smaller regions or field operators in very small volts. And the third is intersection property, that is somehow the dual of additivity. And in fact, it can be obtained, it can be proved if you assume duality and additivity altogether. So I will not talk much about intersection property. We call a theory that satisfies all these things a complete theory. For example, the free scalar field is a complete theory in this sense. And it's also, it has been put as a tentative postulate in Huck's book 20 years ago, 30 years ago. It doesn't hold for any theory, and we will see examples of that. So a complete theory is an assignation of algebras and regions that respect all operations, the inclusion, the union, intersection, and the complement. So one can think what happens to theories that are not complete, what can happen. And for that, we can define, given a region, for example, topologically non-trivial region R, we can define an additive algebra to that, just as the union, the generated algebra of all the algebras of balls included in R. This defines a net, that is the additive net, and is the minimal possible assignation of algebras for R, for a given region, because this algebra must contain all the algebras of ball included in R. So if this is the minimal one, the maximal one would correspond to the commutant of the minimal one or corresponding to the complementary region. So this is a maximal algebra compatible with causality because it has to, this algebra has to commute with the additive operators in the complement. So the question is whether these two algebras are equal or not. If they are not equal, it must be the case that the maximal algebra is equal to the additive algebra of the same region time plus or generated with some other operators A. And the same for the commutant region. For the complementary region, the maximal algebra should be the additive algebra there plus some other operator. These A and B operators are dual non-local operators. Non-local in the sense that are not locally generated by operators in the same region. And this is identified in the usual terminology as a topological operator. It's an operator that lives in the region R in the sense that it commutes with local operators outside, but it is still some non-locality. In this situation where A and B is non-empty sets, you cannot choose the net to satisfy simultaneously additivity and duality. So as the maximal algebras are algebras, it means that these operators A form classes of operators which close under products. So they must satisfy some kind of fusion rules, and the same for operators B. And in general, these fusion rules may be more complicated, but in some particular cases, they are fusion rules of representations or conjugacy classes of groups, so they are related to groups. And this leads to the identification with generalized symmetries, as described in this paper, for example. So it happens that the type of allowed symmetry algebras or the fusion rules will depend on the topology of the regions and the dimension, and very little is known about this problem. So to summarize this thing, our proposal is that completeness corresponds to additivity and duality of the net of algebras, and it is related to the non-existence of generalized symmetries. It is the same thing. In particular, generalized symmetries are then related to the fact that there is more than one possible physical algebra that can be attached to the same region. And another consequence is that generalized symmetries always appear in dual pairs. And this is a consequence of the von Neumann theorem, of the double commutant theorem. And this is completely independent of the type of symmetry, the dimension of the space-time, or the topology of the region. So, for example, magnetic and electric completeness are the same thing. It cannot be, you cannot have magnetic completeness and not electric completeness. And the idea is very simple, is the fact that if you have the additive algebra is included in the maximal algebra of a region, so, and these are different, if you take the commutant, then the additive algebra of R prime has to be included and not be equal to the maximal algebra of R prime. It's better that these are not equal, otherwise taking the commutant again, it will imply that these two are equal. So if this is not equal, is a strict inclusion, this might be a strict inclusion. And for the same reason, the dual non-local operators cannot commute to each other. So these A's and B's operators cannot commute all to each other. So an example is given by global symmetries. And in this case, the non-trivial non-local operators appears in the case where the regions have non-trivial homotopy groups pi 0 or pi d minus 2, the complementary regions. For example, you have two balls here, so they are disconnected regions. In order to see that, you can form, you can take a theory F with a global symmetry and take the quotient with the group symmetry. So you have the orbifold, that is just the operators that are neutral and the symmetry. And then you can take, for example, a charge operator in the region R1 in one ball and the anti-charge operator in the other ball. The product of these two will be a neutral operator. It will belong to the orbifold, but it cannot be decomposed additively as a product of operators in the two regions. So it's a non-local operator. These are called intertwiners and are labeled by representations of the group. And in the complementary region, the non-local operator is given by the twists that are operators that implement the symmetry group, but only in this ball, only in one of these balls. So if you have a non-abelian symmetry, you can form a neutral operator just taking the sum of these twists over the conjugacy classes, so are labeled by conjugacy classes of the group. So if you start, for example, from the additive algebra of the two balls without charge anti-charge operators and take the commutant will contain the twist operator on top of the additive elements outside. And if you start from the outside part without with only local operators, you take the commutant, it will contain the intertwiner. So we obtain this structure that I shown before. Another example is the case of regions with non-trivial pi 1 or pi d minus 3. So this, for example, in 4 dimensions, the topology of a torus, you have a non-local operator that looks like a loop inside, and the complementary region will also have some kind of loop operator. In this case, for dimensions greater than 3, one can show abstractly that the possible fusion rules on local operator is always correspond to abelian groups, the abelian one abelian group and the dual abelian group, and the commutation relations are fixed. Here, the commutation relation, this number is just the character of a representation B applied to the element A. An example of this is given by gauge theories. One can think, well, the Wilson loops are non-local operators, naturally line operators here. But as is well known, not all Wilson loops are really non-local operators, because if you have a charge of the same charge field operator of the same representation, you can form Wilson lines, and with these Wilson lines you can break the Wilson loop as an additive operator in the region. And the same happens for non-abelian gauge fields, because you always have these Wilson lines corresponding to the curvature tensor. So the adjoint representation and all the representations generated by the adjoint can be broken, are additive operators. And at the end, the only thing that you get as a non-local operators are correspond to representations of the center of the group. The dual operators are the top loops. So then let me start describing this idea of entropic order parameters. With these entropic order parameters, we want to produce an entropic quantity that measures the statistics of topological or non-local operators. We have seen that we have two algebras at least for the same region, and with that we will produce two states for the same algebra, and with these two states for the same algebra we can compute the relative entropy. So how is that given two algebras we produce two states for the same algebra? Well, that is done by the introduction of a conditional expectation. The conditional expectation is just a map of an algebra to a subalgebra, in this case the maximal algebra to the additive algebra. It's a particular map that keeps the small algebra invariant. And the use here of this conditional expectation is just to lift a state from the subalgebra, for example, the vacuum state in the subalgebra, just composing it with the conditional expectation, we form a state in the big algebra, in the maximal algebra. In quantum field theory, these conditional expectations that we are interested in are just produced by the non-local operators themselves. For example, here I have a charge-anti-charge operator, and averaging by the action of the twist operator, I can kill the non-local operator, and the result belongs to the small algebra, the additive algebra. And then we can then define an entropic order parameter, which is just the relative entropy in the maximal algebra between, for example, the vacuum state, and the vacuum state goes with the conditional expectation. So the relative entropy is known to measure the distinguishability between two states, and the difference between these two states is precisely the expectation values of non-local operators. Here we have vacuum expectation values, and for the other state it's just zero, this expectation value, because the conditional expectation eliminates them. So it is a measure of the statistics of expectation values of non-local operators, but it doesn't depend on the particular non-local operator, because there are infinitely many that I can take that belong to the same class. It doesn't depend on that, but depend on the geometry. So it somehow measures the best one, the one of greater expectation value. It's only a function of the geometry and the vacuum state. If one do not want to talk about entropic quantities, one can also see that you can produce standard non-local operators that are determined exclusively by the geometry and the vacuum itself. So for example, one can think if you have a torus in 4 dimensions, you can produce a standard Wilson loop operator attached to this torus. So in this situation, we have this complementarity diagram. This is a maximal algebra of the region R, and there is a conditional expectation that goes to the additive algebra. And in the complementary region, you have the maximal algebra, and there is a complementary or dual conditional expectation that goes from this to the additive algebra in R prime. And these conditional expectations are completely fixed and uniquely defined in the continuum quantum field theory, so you don't have to worry about how to define them. And then there is, in the vertical direction, the relation is just simply that commutant algebra. The commutant of this is this, and the commutant of this is this. In this situation, we have that for a pure global state, as the vacuum, for example, we have the entropic certainty relation. And this is a relation between the entropic order parameter for the region R and the corresponding one for the region complementary, the R prime. The sum of these two relative entropies is equal to a number that is fixed. It doesn't depend on the geometries of the region or the particular state that I take in. And this number is a logarithm of an index of the inclusion of the algebra that was described by mathematicians. In the particular cases of a symmetry group that is a group, there is just the logarithm of the size of the group. So this relates the statistics of dual order parameters. We describe it first in this paper in the case of global symmetries, and Javier Magán and Diego Pontello then extended it to arbitrary finite dimensional systems. And these two works describe this more in the type 3 algebras that appear in quantum field theory. So why is this called entropic certainty relation? The reason is that it is very much related to uncertainty relation for operators. You have this relation, and as the entropy is always positive, the relative entropy are positive quantity, means that both of these order parameters are bounded above by log G in this case.
But for 4 minutes for your talk.
Sorry?
4 minutes.
Okay. So, but they cannot be saturated at the same time, right? Because you have to satisfy this. And this is related to the fact that the operators A, non-local operators A, and non-local operators B do not commute to each other. This same relation gives a handle on computations, because if you know the expectation value of non-local operators A and B, you can reduce to the entropies to these algebras of non-local operators and produce upper and lower bounds to your relative entropy order parameter. So these are some uses that you can think of these. For example, in this case, I take some arbitrary region here, A, and the almost complementary region B. And then for this case of global symmetries, you can see that the relative entropy order parameter is just the difference of mutual informations in the theory with charges minus the one in the theory without charges. And in the massive case, and when the regions are very near to each other, it just give you a purely topological number proportional to the number of boundaries. You can also use it as an order parameter for phases of gauge fields. For example, in the infrared, for large loops with a small width, you have for example, for the Higgs phase, the relative entropy of the Wilson loops goes to a constant law, and the Toff loops goes to an area law, and the opposite is supposed to happen for confining theories. For the conformal case, you always get the perimeter law. So in this sense, in our case, we cannot renormalize as usually done the perimeter law to a constant in this case, but in this case, it happens. We cannot arbitrarily renormalize operators here because they have to satisfy an algebra. So this is just an heuristic on how this area versus constant law appear in this setup. Suppose you have a ring, orange ring here, you want to find how the relative entropy behaves. And in the outside part, you can place many of these black rings crossing the inside. And then if your black non-local operators have a constant law and they are decoupled to each other, you can easily compute the relative entropy in the black algebra, and it gives you some number approaching saturation minus some small deviation that grows with the number exponentially in the number of black rings you have there. And as you can place an area worth of these black rings, it means that using the certainty relation that the relative entropy in the orange ring has to decay with an area law. So let me do some final remarks. One of the things that our work highlights is the importance of wide loops as opposed to line operators that are usually described in the literature. So, and the reason is that the wide loops are dual to thin loops, so they have related order parameters. And the second is that if you want to study the normalization group flow of these symmetries or understanding what happens with the symmetries and normalization group, you want to study regions under scaling, and this changes the size of the region, so partial infrared. These are like projects for the future, how to relate the ultraviolet and infrared. This is important for theories with asymptotically free theories and for proving confinement. We don't have a handle yet on how to manage these things to understand better in terms of entropic terms. And another important thing is the classification of the possible fusion rules for different topologies of regions and different dimensions. Very little is known about that. And of course, we want to compute all the parameters for nonability theories and for holographic theories. Thank you.
Thank you very much. Very beautiful talk. It's time for question. So I'd like to Miguel Montero.
Yeah, thanks for the nice talk. So I have a question about the part where you argued that completeness of the spectrum is equivalent to absence of global symmetries. So absence of global symmetries, do you mean usual global symmetries or non-invertible global symmetries? So would you also include those? And relatedly, I would also like to know to what extent these arguments would apply also to low energy effective quantum field theories, which might be complete to quantum gravity as opposed to quantum field theory.
Okay. Let me start from the second one. So I said that the dual symmetries come always together, right? And then the question, I think that your question is whether this somehow survives the normalization group, in the sense that you can have at the infrared, for example, some symmetry and the other one is only seen at the ultraviolet, something like that. Well, we don't think that happened. The reason is that if you have the certainty relation, for example, and you have this, in the case, for example, you have charges that are very massive, this will go to 0, and then the other one is saturated. When the other one is saturated, it means that the non-local operators have expectation value 1. It means that they act trivially in the Hilbert space and can be thought as constant, as a unit. So both disappear, from our point of view, disappear at the same time or appear at the same time. But it's important to not to be confused exactly this point. This point here is that you cannot use line operators. Otherwise, you will always have small expectation values and you can think, well, there is something there. But if you use, for example, in the infrared, wide enough loops, you will see that your loop operators are going to 1 or either to 0, for example, if the theory disappears, and then both of the algebras disappear at the same time in that sense. And your first question, I think I'm less able to answer correctly what you say, in the sense that I think what you say is that, well, let me repeat what I said here. Let me repeat what I said here. Let me say, where is it? That this fact that the symmetries come in dual pairs is completely independent of the type of symmetry, dimension, and topology. So it doesn't depend on what extra operators you have, this that you have called, what you have called this non-invertible or something like that.
Yeah,
right?
I just mean topological operators. I just mean topological operators that can have a non-trivial fusion algebra, but they don't have a group law.
Okay, it doesn't matter. It doesn't matter. So of course, in that case, one has to work out what are the dual, let's say, fusion algebras or something like that. But it cannot be the case that one is there and the other doesn't have any operators or doesn't have any.
So I'm asking because there are examples where you can have an incomplete spectrum and no ordinary global symmetries, but you can still have these other guys. So that's the example I was asking about.
Yeah, well, I know that people discuss these things. I think they should. it would be nice to revise these things under this perspective, because people usually say these problems that you mentioned, perhaps in topological theories or something like that. And these topological theories have to be thought perhaps in a different setup, because topological, strictly topological theories do not have operators attached to regions, right? I'm thinking here in theories that have some operators attached to regions. So perhaps if you can put a little cutoff and say your operators have some typical mass or something like that, then you regain all this that I'm saying here.
Okay, so next, Zohar.
Thanks. Nice talk. Thank you. I had a small technical question about the slide where you spoke about regions with non-zero pi 1.
Yeah, well, okay.
Yeah.
So
if you can just quickly, yeah, it's the next slide, I think.
Yeah.
Yeah. Here you mentioned that the operators form an abelian group, but I don't understand why this is true. In general, the space of lines doesn't form an abelian group whatsoever.
Well,
in the space of topological lines doesn't form any sort of group.
Okay, I'm saying this only for the case of a single like torus. If you are thinking in regions which are not to each other or something like that, then it might be more complicated, and we haven't worked it out. If you are thinking about that, if your question is about that.
Even on a single torus, there could be a highly non-trivial R matrix. So I don't completely. Maybe we should discuss it later because I don't.
No. Okay, but here I'm thinking only on the generalized symmetries, not on the full algebra of this. Because, for example, you can have maybe you are talking about Wilson loops can have fusion rules of non-abelian fields, but here it's always abelian, because it's only the part that is non-local, that it cannot be destroyed in the sense of it's a product of Wilson lines, for example, because of this.
Okay,
right?
I understand. Thank you.
Yeah. Okay.
So time is running out, but could you ask a very quick question? That's Node IAS.
Hi, hello. This is Shu Han. Can you go back to the earlier slide on completeness and how to think about it as a generalization of modular invariance? Yeah.
Okay. This commentary is because in 2 dimensions CFT, for example, from this paper, you can see that for two intervals, the entropy of the two intervals is equal to the entropy of the complementary two intervals in a circle, for example, if there is modular invariance. So modular invariance is naturally associated to this property of the entropies, and the entropies are equal for commutant algebras. It's important. It's not equal for complementary regions. It's equal for commutant algebras. So it means that in that case you have a Haack duality for two intervals. So modular invariance is in this sense, and also in more direct sense. In this paper by Feng Shu, for example, you can see that it's related to a Haack duality for more than one interval.
But I'm confused by the connection to no generalized symmetries that you wrote above. 2D modular invariant CFT can certainly have global symmetry, right? So what do you mean by no generalized symmetries at all?
Well, I'm thinking that the symmetries are exactly, it's a generalization of the idea. The symmetries are given by this existence of non-local operators. For example, in 2 dimensions, you can have non-local operators for two intervals, right? And then this is what modular invariance is somehow prohibiting. So it's okay. In that sense, I'm taking all these cases. I'm calling generalized symmetries. All these cases I'm calling generalized symmetry. It can be many different things in different dimensions and etc. But in the cases that have been studied, for example, for these torus things. It coincides with the usual generalized symmetries for gauge theories.
Thank you.
So Daniel, only short question.
Well, okay, I'll just say very fast. I think that this approach doesn't sufficiently distinguish between gauge and global symmetries. So just for example, let's talk about a free scalar field with the symmetry phi goes to minus phi. Is this a gauge symmetry or a global symmetry? I think that it's a different theory depending which of those decisions we choose. But I think that you're just describing those as two different algebras, two different choices of algebra in the same theory. So in fact, you had it in the slides, right? Like you said you had a global symmetry, phi goes to minus phi, but then you wanted to restrict to neutral states and introduce twist operators. But I would have just said when you're doing that, you're gauging the symmetry.
Well, there is only one important difference in this case of global symmetries with respect to the others that one can think, is the fact that in the case of global symmetries, if you have this theory, the orbifold, you can always produce another theory which doesn't have algebra region problems and which has the same expectation values for the operators, the neutral operators. This is was proved in the DHR analysis, have many years. So you start from the orbifold and you reconstruct the theory without changing the expectation values of the neutral state operator.
Yeah, but so we would call that the inheritance property of gauging a discrete global symmetry. So I would say that is the theory where you gauge the symmetry. It's a different theory.
No, well, from F you can obtain O, and from O you can obtain F. Right?
Yeah, but if you go to another topology, it'll be very clear because you'll have loops. The question is, what loops can you have on cycles that are not contractible? And then you're really going to have to be pinned down on this.
Yeah. I don't understand what is the point, really.
I think you should be, I mean, I think the formalism should clearly distinguish between a gauge and a global symmetry. Let me just maybe make it as a comment. I don't think it should be up to you how you interpret it.
All this formalism is all for, let's say, generalized, as people call it, generalized global symmetries, There is nothing.
Yeah, but for global symmetries, we don't restrict to singlets. So when you're restricting to singlets, you're kind of gauging the symmetry.
Yeah, but
I'm sorry, I promised Tadashi this would be fast. So I think we should go on.
I suggest
yeah, we should go on, I think.
Yeah. Okay, so let us thank Horacio again.
Okay.
Please, John, please share your screen. Okay, so next speaker is John McGreevy from UCSD. He'll tell us about mean string field theory, Landau-Ginzburg theory from one-form symmetries. Please start.
Okay, thanks, Dashi. Can you hear me?
Yes.
Okay, great. So this is a talk about work with Nabil Iqbal, some of which we just posted. And it's part of a larger program whose goal is to enlarge the Landau paradigm. So by the Landau paradigm, what I mean is the idea, the sort of principle, that phases of matter should be classified by how they represent their symmetries, in particular by what symmetries they spontaneously break. And furthermore, that at critical points, the critical degrees of freedom should be the fluctuations of the order parameter that breaks those symmetries. And I guess there's a sort of corollary of this, that Gapless excitations or degeneracy that's stable, that exists in a phase, should arise as Goldstone modes for spontaneously broken symmetries. And there's a sort of weaponization of this point of view, which is Landau-Ginzburg theory, which is useful for finding representative states, for studying excitations above those ground states, for understanding the gross phase diagram of such theories, and it even quantitatively describes phase transitions in high enough dimensions. Okay, so there are some apparent exceptions to this grand viewpoint on the world, among which I'll mention two. The first is topological order, by which I mean some stable ground state degeneracy that depends on the topology of space. Examples include the deconfined phase of discrete gauge theory and fractional quantum Hall states. And another class of examples is just any other deconfined states of gauge theory, such as the Coulomb phase of electricity and magnetism, by which we are seeing each other. And so, in fact, both of these apparent counterexamples can be incorporated into a suitably enlarged Landau paradigm by generalizing our notion of symmetry. Our goal of this talk will be to understand how to correspondingly generalize Landau-Ginzburg theory, at least in the simplest case. So the generalization of symmetry I have in mind is higher form symmetries. It's sort of maybe the simplest possible generalization. And actually, I'm only going to talk about one form symmetries in this talk. So let me remind you what this is. A zero form symmetry, if it's continuous, is associated with a conserved current. You can integrate that over a codimension 1 slice of space-time, which we usually think of as a time slice, and to get a conserved charge. And the statement that charge is conserved is usefully regarded as saying that charged particle world lines piercing that, it counts the number of charged particle world lines piercing that constant time slice, and they can't end. They can only end on charged operators, which are point-like and create and annihilate these particles. And the operator that creates and annihilates these particles is charged under that symmetry. It transforms like this, where alpha is a closed zero form. A one form symmetry is just the same, except the current is a two form. A two form is something that you can integrate over a codimension 2 slice of space-time to get a number. And if it's conserved, then that number doesn't depend on deformations of that surface. And a good way to think about that is this black thing is a codimension 2 thing, and it counts the number of string worldsheets that it pierces. And so the statement of conservation says that these string worldsheets can't end, except on charged operators. And now a charged operator is a thing that creates a string and transforms like this under the global one form symmetry, where gamma is a closed one form. Okay, so some physics contexts where such a symmetry arises are ordinary E&M, where if in the absence of magnetic monopoles, the magnetic flux lines can't end. The charged line operator is the 't Hooft line. Many gauge theories without fundamental matter enjoy a one-form center symmetry, discrete center symmetry, under which the charged line operator is the Wilson line. And the ordinary 3D Ising model has a one-form symmetry, a Z2 one-form symmetry, which reflects the integrity of the domain walls between the regions of upspins and downspins. And the line operator is the disorder operator. Okay, so anything we can do with ordinary symmetries, we can do with generalized symmetries. In particular, they can be spontaneously broken. What it means for a one-form symmetry to be spontaneously broken is the following. Well, okay, so it's not spontaneously broken if correlation functions of charged operators are short-ranged, meaning that they decay when the charged object grows. The charged object here is a loop. The right way to think about its size is the area of the minimal surface bounded by C. So the symmetry is unbroken if there is an area law for the charged loop operator, and in contrast, it's broken if there's a perimeter law. And the perimeter law we should really think of as a constant, as we saw in the previous talk, because usually we can get rid of this perimeter law by local counter terms along the operator. And so this just means that there's some large loop operator that has an expectation value. And so this has been a very fruitful idea. In particular, it can be used to understand topological order, indeed as spontaneous symmetry breaking. And this is actually a pretty tautological statement, because topological order means that there are ground states which are distinguished from each other, which to get from one to the other, we act not by any local operator, but rather by some non-local operator, which is exactly the representation on the Hilbert space of some higher form symmetry with some suitable 't Hooft anomaly. Okay, and in the case of a U1 one-form symmetry, if it's spontaneously broken, it produces a Goldstone boson, which indeed we can think of the photon as being, the masslessness of the photon as being protected by such a concept. So this statement we'll see very explicitly in just a minute, and it's been useful for a number of other things which I won't say anything about. So before concluding this brief introduction, I need to say something about the robustness of higher form symmetry. So you might think that it's kind of a weird idea to imagine that microscopically there are closed strings that can't end. It's like a string theory without d-branes. And so to make us feel better about that, I need to point out a very important difference between one-form symmetries, and indeed any higher form symmetry, and zero-form symmetries, which is that we're used to the idea that the consequences of emergent symmetries, which are in the high energy literature are called accidental, that the consequences are only approximate. For example, if you explicitly break a continuous zero-form symmetry that's spontaneously broken, it gives a corresponding mass to the Goldstone boson. And so you can ask, a question that I'm sure anyone would have when encountering this for the first time is, so does this mean that I just said that the photon is a Goldstone boson for the symmetry that enforces the fact that magnetic flux lines don't end. So in the presence of even very heavy magnetic monopoles, this symmetry is explicitly broken. And so does that mean that there's a mass for the photon in the presence of even arbitrarily heavy monopoles? And the answer to this question is no. which I think is a pretty striking fact, and it can be understood from various points of view, which I won't explain right now. So the point of this slide is that higher form symmetries are actually, when they're present, even approximately, they exist. There's actually a phase where they're present. Okay, so the goal of this talk can be explained very simply, and in terms of the method of the missing box. So as I mentioned, Landau-Ginzburg theory is sort of our 0th order tool for understanding symmetry breaking phases and their neighbors in the phase diagram. And so let's ask, so 0 form symmetry is to this Landau-Ginzburg mean field theory as 1 form symmetry is to what? So our goal is to fill in this missing box. And to do that, let me give a brief reminder, a sort of Wilsonian reminder on what I mean by Landau-Ginzburg theory. And so here, the key idea is to introduce a field that transforms linearly under the symmetry. Let's think about the case of a U1 0 form symmetry. And so we'll introduce this order parameter field, and we should regard it as a coarse-grained object. This is an effective long wavelength description valid below some scale. And the principle, the idea that we can understand the phase just in terms of the symmetry degrees of freedom, says that the effective action for this field should be local. That is, there's no other gapless modes that we have to integrate out. And we should just add all local symmetric terms, symmetric under this 0 form symmetry, organized in a derivative expansion, where the higher order terms are suppressed by powers of this short distance beyond which the theory breaks down. So from this logic, we arrive at the familiar action. And one way to make contact with a particular microscopic Hamiltonian is by the variational principle. So the idea is to make an ansatz for the ground state in the form of a product over points in space, where the state at each point in space is determined by the value of the field there. And taking the expectation value of whatever Hamiltonian you like, microscopic Hamiltonian, in such a state produces a functional, which is of the form of the Hamiltonian that you would get from this action with specific coefficients. So that's a good way to think about where these coefficients are determined if you want to actually determine them. Okay, so let's embrace our naivete and work purely by analogy. And let's think about what ingredients we need to construct an analog of that for 1 form symmetries. So the field in the 0 form case was a function from the space of points to a linear representation of G, which transforms in this way, where, as I said, alpha is a closed 0 form. The analog of that is now, so instead of the space of points, we have to think about the space of loops. And the field is a functional from the space of loops to some linear representation of G. It transforms like this, where now gamma is a closed 1 form. To write kinetic terms, we need a derivative that in the ordinary case, it compares the value of the field at nearby points in spacetime. And the analog of that is this area derivative introduced by Migdal and Polyakov, which compares the field at nearby loops. And nearby loops differ by some little chunk of loop in some particular plane attached at some point on the given loop. In order to write an action, we need to integrate, in the ordinary case, integrate over the space of points. The analog of that is integrating over the space of loops, which this is just the path, like the path integral for a charged particle, and it would be fine-tuning not to include some exponential dependence on the mass here. Okay, and then finally, given a global symmetry, a useful maneuver is to couple it to background fields in a gauge invariant way. So I should emphasize here, I'm not gauging the symmetry, I'm just coupling to background fields. To do that, we need to promote the ordinary derivative to a covariant derivative that transforms linearly just like the field. And so the analog of that for 1 form symmetries, the background field is a 2 form. And there's a very nice, very natural generalization of the area derivative, which is a combination of the area derivative and a coupling to this 2 form, which I believe was first written down by Suzhong. Okay, so with these ingredients, we can follow the principle and just write down all terms consistent with basic principles in an expansion in powers of these area derivative. And so we can write terms that are completely local in loop space. So this part of the action is essentially a ordinary field theory in loop space. There can be terms involving some potential with various powers of the string field, and we can write a kinetic term like this. And but a surprise, perhaps, is that there's another large class of terms which also preserve the 1 form symmetry, but which are not local in loop space. They rather, for any collection of loops, the sum of which adds up to the original loop in the sense of integration domains, a term like this, where the strings recombine, also respects the 1 form symmetry. And so this action is natural under the following assumptions. It's invariant under the one-form symmetry. It's local in ordinary spacetime. So I said this term is not local in loop space, but it is local in ordinary space because the center of this, there's only a single integral over the center of mass of these loops. The center of mass position of loop 1 determines that of loop 2 and 3. I demand invariance under ordinary rotation and translation invariance just to make it look nice. And then finally, I demand a certain translation invariance in loop space so that the dependence on the loop in the action is essentially only through the field. So these coefficients can't have some arbitrary dependence on the loop. And that follows from a certain translation invariance in loop space. Okay, so I should make some disclaimers at this point. I've said the word string field various times. I should emphasize that the theory I'm talking about is not at all UV complete. There's no gravity involved, and we expect no connection to the real string field theory. We're trying to do something much less difficult. These are effective strings. I should say that a gauged version of this model where the one-form symmetry was gauged, where there wasn't actually a one-form symmetry, and without this recombination term was studied long ago by Sujong as a description of a Higgs mechanism for two forms, and then a bit later as an attempt to give a dual description of superfluids in 3+1 dimensions. So the question that we'd like to answer then is what does this model describe? And I think a plausible goal is to use it to develop a picture of the phase diagram for any system that has such a one-form symmetry, or at least for a large simple class of such systems. Okay, so beginning classically, we can write the equations of motion. Think of this as a picture of an equation. The way you should think of this equation is as a recursion relation. Given the value of the string field on some loop, it determines the value of the string field on a slightly larger loop, like this. And clearly, such a recursion relation requires an initial condition starting from small loops. And the initial condition says that small loops can shrink to nothing. There's some non-zero amplitude for that to happen. And that's consistent with the symmetries because a small contractible loop is neutral under the one-form symmetry. And this will nicely match to gauge theory in the broken phase, as we'll see. So, okay, so let's begin with in the regime where the potential looks like this, where the coefficient of the quadratic term is positive. So it makes the field want to be small. The field being 0 is not consistent with the boundary condition. And so to do better, let's make an ansatz that the dependence on the field, the dependence of the field on the loop is only through the area of the minimal area surface bounded by that loop. And this turns out to be a very good ansatz because the equations of motion at large area have a self-consistent solution of this form. Corrections are suppressed by inverse powers of the area. And so this is an area law. This indeed does describe the unbroken phase, where there's an area law for the order parameter with a string tension that goes like the square root of this parameter. So let's ask what happens when we make that parameter negative. That produces a phase where the strings want to condense. And we can ask about fluctuations about such a ground state. The fluctuations which change the magnitude of the field are clearly gapped because that requires going up this hill. But the fluctuations that only change the phase involve motions in the bottom of this well. It's less obvious. So let's make a general ansatz for variations of the phase. This term is special because it's geometric. It depends only on the loop and not on any other data. And if we plug this back into the action using standard world line techniques like in Matt Strasslow's thesis, the action that we find is Maxwell theory for this geometric mode. So F here is the field strength of dA, this A, and all of the other modes are massive. And so looking at the form of this term, it's exactly of the form of a slowly varying space-time dependent one-form symmetry transformation. It's exactly a Goldstone boson for the one-form symmetry. Voila. Okay, so another nice thing to notice is that the gauge coupling, the coefficient of this term, is determined by the stiffness, meaning the magnitude of the order parameter breaking the one-form symmetry, and all the other modes are massive. Okay, so we've made contact with some familiar things. Now we can ask what is this theory good for? And one important purpose for ordinary Landau-Ginzburg theory is in service of a topological theory of the topological defects in the broken phase. So for example, if you spontaneously broke a zero-form symmetry, there's a codimension 2 defect in spacetime in the core of which the order parameter vanishes and around which its phase winds, a vortex. So let's ask about analogs of that in this case. So one way to think about that is to choose some subspace of spacetime. Think about, for example, a Q-1 sphere surrounding a codimension Q locus in flat space X, and imagine that on that locus, the order parameter is non-zero. That defines a map from the loop space of X to U1. The target is the phase of the order parameter. And the loop space, by the loop space of S, I just mean the space of maps from the circle into X. And so defects linked with X are then labeled by homotopy classes of such maps. And in the special case where X is simply connected, such as for a sphere, then these homotopy classes of such maps are just pi2 of X. And so from this, we can conclude that in the case of a U1 one-form symmetry, the analog of the topological theory of defects says that there's only one kind of defect, which is a codimension 3, which is exactly the magnetic monocle. And there's only one kind of texture, which is the non-zero flux. Okay, so in that list of physical examples of one-form symmetries that I gave, most of them were discrete. To study discrete one-form symmetries with this theory, we can simply explicitly break the U1 one-form symmetry down to a ZP subgroup by adding a term like this, which is some pth power of the order parameter field. And in the broken phase, this action takes a form like this, minimizing which requires that the gauge field is flat and that its holonomy is a pth root of unity. A useful way to think about this term here is it's the path integral for a charged particle coupled to this gauge field A. And a collection of charged particles can have a phase which is a superfluid. And this Lagrange multiplier B that imposes the flatness of this gauge field is just the dual d-2 form, dual to that superfluid order parameter. And so this produces exactly an effective description of ZP gauge theory, as we might expect, based on the idea that topological order is spontaneous breaking of one-form symmetries. Okay, so now something you might be nervous about, and certainly I was for a long time, is that I've written this theory where the action is a path integral with all these crazy derivatives. Is it really well defined? And so one way that we've made ourselves feel better about that is defining it on the lattice. And so one way to do that is to find the analog of this variational perspective. So let's think about a simple example of a system with a one-form symmetry, namely ZP gauge theory, the perturbed toric code. And let's think about the case where p equals 2 for simplicity so that we can make the Hilbert space by putting a qubit on each link of some cell complex. And let's say if that qubit has spin down, we'll say that the corresponding link is covered with a segment of string. In that language, the Hamiltonian has 3 terms. It's very simple. The first term imposes that those strings are closed, and we really impose that really strongly because we want there to be a one-form symmetry. The second term allows the strings to hop around a plaquette, and the third term says that those strings can have a tension. In the limit when the tension is 0, all the terms commute, and the ground state is a uniform superposition of closed loops. And if we turn on this tension, eventually, if we make it big enough, there's a transition from this topological ordered phase to a confined phase. So now what's the analog of this product state ansatz for one-form symmetries? It seems to be a state where the wave function of a single connected loop, psi of little c, determines the wave function of the arbitrary collection of loops. So something like this. And indeed, if we evaluate the expectation value of the toric code Hamiltonian or anything related to it in such a state, we find a functional that's a lattice version of this mean.
Joe, 5 minutes for your talk.
Great, thanks. A lattice version of this mean string field theory Hamiltonian. So in the remaining 5 minutes, let me make some comments about phase transitions, slightly more speculative. So if we were to ignore this recombination term, for example, if there were some additional psi goes to minus I symmetry that forbade it for some reason, then we predict a continuous mean field transition at r equals 0, where the tension goes like r minus rc to the x. This defines the critical exponent, and our value of the critical exponent is the most mean fieldy of critical exponents, which is quite different from the value seen in numerical simulations, for example, in 3 dimensions with Z2 symmetry. A way to make ourselves feel better about that is that dimensional analysis says that the upper critical dimension, where the side of the 4th term becomes marginal, is 8 space-time dimensions. So this is quite far below the upper critical dimension. It's interesting to note that this value of 8 for the upper critical dimension of a theory with one-form symmetries was predicted by Parisi based on the analog of Szymanczyk's argument in the ordinary case, estimating the fractal dimension of random surfaces. Okay, but why should we ignore this recombination term? And I think the most surprising and interesting outcome of our analysis so far is that there is a term which respects the symmetries for a theory of one-form symmetries, there's a term with respect to the symmetries, which is cubic in the order parameter. And this strongly suggests that the generic transition should be first order. This, if true, provides an appealing explanation for a whole lot of observations in numerical simulations looking for continuous transitions, continuous deconfinement transitions in gauge theory in higher dimensions. Okay, so however, 4 dimensions is special. 4 dimensions is special because that's in that dimension, the string field is dimensionless. So in the same way that in 2 dimensions, the order parameter field for a zero-form symmetry is dimensionless, and this leads to Kostelos-Thalos physics. In 4 dimensions, the string field is dimensionless. And so this leads to a possibility of a Kostelos-Thalos-like transition where the dimension of the field of the operator breaking the U1 symmetry down to ZP, its dimension depends on the coupling, which in turn is determined by our tuning parameter. And its dimension can pass through 4. It can go from irrelevant to relevant at some critical value of the coupling. If this operator is irrelevant, it means that even though microscopically the potential is corrugated, the low energy physics doesn't see the corrugation, and so there'll be some phase with a photon anyway. And indeed, such a phase is seen in 3+1 dimensional ZP lattice gauge theory for large enough P. The phase diagram looks something like this. This is P. This is our tuning parameter, which determines the gauge coupling. And for large enough P, there's an intermediate phase with a photon separated by Kostelos-Thalos transitions from the topological ordered phase and the confined phase. So final comments. There's a lot more to understand about this theory. It's not quite under control, but likely can be put under control. And the main thing that we don't understand is the theory of renormalization. So I just said something about dimensions of loop operators, but we need to understand that a bit better. And one reason that we'd like to is perhaps we can find new RG fixed points in this way, which we wouldn't find using ordinary field theory. I didn't actually add quite the most general terms to this Hamiltonian because I didn't write any topological terms or WCW terms. By thinking about such terms, we can describe one-form symmetry-protected topological phases, and we can realize more general gauge theories as the broken phase. And then an important motivation besides the ones I've said for this line of thought, I think, is to try to develop a better understanding of what is the gauge theory. I think it's clear that a definition in terms of some redundancy is inadequate. And here so by starting with a theory that has the right symmetries, we've recovered some universal properties of gauge theory, sort of going in the opposite direction from what Polyakov and Migdal and Mikiko and these guys were trying to do in the 80s. And so finally, the question remains whether this suitably enlarged Landau paradigm, including all possible generalizations of the notion of symmetry and their anomalies, can indeed be used to understand all phases of matter as a consequence of symmetry. Okay, so that's the end. Thanks to the organizers for this great meeting, and thanks to you for listening.
Thank you very much for very beautiful talk. It's time for questions. Sheen.
Hi, John. So I have a couple of questions. So first, how does the theoretic expansion of the effective string that Ofer was talking about this morning relate to your expansion of the mean string field? Are they in one-to-one correspondence?
That's a great question. I don't know the answer yet. Yeah. So I should emphasize we've really only done very primitive things of deriving sort of the leading terms in the effective action in the various phases. And I think indeed there should be such a correspondence, right? It's just a different set of variables for writing the same thing.
I have another small question about this broken phase where you wrote the string field is a constant. Do you actually mean it is a constant on the entire loop phase?
You mean the unbroken phase? Here.
The broken phase.
Here, the broken phase.
It to be.
Right. Sorry. I'm sorry. Yes, I amazingly, I still confuse these words broken and unbroken. Right. Yes. No, I definitely don't mean that it's a constant. Indeed, we studied the analog of this ansatz for that the area law ansatz in this phase as well, and there's some sort of simple ODE that we can solve to match to the boundary condition. Yeah. So there's some boundary condition for short loops, which and there's some flow and it's only for long loops that it behaves this way. Indeed.
I see. Right,
the solution is more complicated though. Yeah.
So Ofer, please ask question.
Hi, John. This is very nice. Do you know if there's a generalization of this that would be relevant for supersymmetric theories that have one-form symmetries? And is the effective action more constrained in that case?
Oh, cool. Yeah, we haven't thought about that. Yeah, I don't know. That's a great question. I've been thinking a little bit about yeah, fermionic generalizations of higher form symmetries, but I should just say I don't know. Yeah, good question.
So next, Node IS. Could you ask a question?
Yes, so I have a bunch of questions. First of all, is your action approximate or is it exact? In other words, in a standard Landau-Ginzburg theory, we know it's an approximation and we have some rule that controls the higher order corrections. Do you have such rule here? What are you expanding in?
Well, so yeah, I mean, I'm really following exactly the analogy with the zero form case. So the rule in the zero form case is there's some short distance that controls, where this description breaks down, and the dots here have inverse powers of that energy scale. So I'm imagining exactly the same thing here. These dots are all other possible terms that you can write, again suppressed by some short distance scale.
Okay, so my question really splits in whether we are in the gapless case. I don't even know where the microphone is. So can you hear me?
Yeah.
My question really splits whether we are in a gapless phase or a gapped phase. In a gapped phase, I don't see where you can expand in because there's nothing at long distances. And in the gapless phase, as you showed, it goes over to your photon. And then I know how to describe it. But then I think if you include both the photon and the loop, you overcount. So it's not clear to me, more generally, it's not clear to me what you're expanding in and when it is justified.
Oh, Nadi, I'm confused about why you don't have the same confusion in the zero form case. So here too, there's a massless phase and a massive phase. And in the massive
because in the massless phase, the symmetry acts non-linearly on phi, and phi is the field in the low energy field theory. But then I do not need to add another order parameter, which is the exponential of phi, as a separate field. I have only one field and I'm expanding as you wrote on this slide. The analogous thing in the one-form symmetry when it's gapless is that you write Maxwell theory. I think you do not need to introduce also other operators.
I'm not introducing any other operators. I think the analogy is pretty precise. So in the zero form case, there's here. So in the zero form case, there's this field phi, the linear variable, which transforms like this under the zero form case, and phi in the broken phase is e to the I, let's say var phi, the thing that transforms non-linearly, and this is the Goldstone. Right. So similarly, I have this string field, which transforms like this, and in the broken phase, it's e to the I integral of a, and that's the Goldstone. So it's the counting of variables is the same, except that in my Landau-Ginzburg theory, I have a whole lot of other variables which at low energies just get a mass. They get a mass of order the cutoff scale.
Right, but when you write a Landau-Ginzburg theory in the first slide, when you have a U1 symmetry which is unbroken and use a complex field phi, then it's valid only near the transition point. It's not valid deep in the unbroken phase. Whereas if you are in the broken phase, you use var phi, and then again you should just expand it. It seems like you're trying to get both.
Good, you're right. So indeed, the perspective is. The theory, indeed, the ordinary Landau-Ginzburg theory is useful, say, near the phase transition, if you wanted to really use it as a theory to describe the excitations. But I think maybe a useful perspective is that it nevertheless provides a representative of the phase, a representative state in the phase, which how to say, the universal properties should agree. You're right that deep in the phase, maybe there can be some other microscopic degrees of freedom that come down if you want some theory that's valid up to some large energy scale. I agree. But I think the analogy is precise. So whatever you can do with the zero form case, you can do with this one form case.
Okay, so Miguel, So time is quite running out, so please ask a short question.
Yeah, it's a very quick question. I just wanted to know if you thought about maybe generalizing this thing to, for instance, two-form symmetries in 5 dimensions or something like that, where you would have something like a membrane theory, which is more complicated.
Indeed, yeah, good. So it's really inevitable that you know, everything I said in this talk can be generalized to p-forms, except that, you know, instead of the action being a world line integral, the action becomes some integral over membranes, which is something that, yeah, I don't, maybe in the case of p equals 2, we can use string theory technology to control it a bit. But for the higher case, I'm a bit frightened, I have to say. One reason that this is particularly interesting is that the story I was trying to say about the Kosterlitz-Thouless-like transition in 4 dimensions, there's an analog of that in 6 dimensions for 2 forms. I think, yeah, a very precise analog, which I think is, yeah, very much worth exploring.
Okay. So Emil?
Yeah. Is the conventional string field theory that was reviewed by Sweetback last week fit into your framework or no?
I don't think so, no, because the string field that I'm talking about is gauge invariant. The ordinary string field theory has, you know, the string field is a highly redundant variable. So all of the difficulty, you know, a lot of the difficulties with like the A infinity algebras is to impose that gauge invariance, right, to get that gauge redundancy. And whereas here, my string field is really a physical degree of freedom, except to the extent that many of the excitations it creates are, you know, at the scale of the cutoff.
But so to the extent that I can ignore that, that critical string field theory has vertices that are not local in loop space, right? They have sort of, you know, the sort of theta diagram that you were drawing on an early slide. That has various things attached to it that propagate things, or I think what Barton called stubs. So it's not really local in loop space. And I was wondering why you were insisting on writing something down that's local in loop space.
No, I'm not. Indeed, just as you said, this term is not local in loop space. It involves an overlap of loops which are, you know, different points in loop space, macroscopically different. Yeah.
All right. Well, maybe I'll ask further questions in the Slack channel.
Thanks.
So yeah. So now it's time. It's just enough. So let us thank the John again for great talk.
Okay, very good. So let's move to the first discussion of week 2. And let me make a few remarks since I know that some people are joining for the first time for week 2. And so I want to remind a little bit how these discussions work. So these discussions are something new. We are trying, so we are tweaking as the days go, and we are hopefully improving a little bit. And so let me mention not only how it has been working so far, but a few things that we hope will improve by an epsilon more for this week 2. So the idea of these discussions is, first of all, to keep to try to generate a more informal feel for the meeting and for us to have fun chatting with each other and seeing each other. So please, if you are participating in the discussion and if you can keep your camera on, that helps give this informal feel to the meeting. Now, let me make 2 comments then. Let me describe the 2 parts of these discussions. The first part is where the chairman introduced the topic that is going to be discussed, where the leaders of this discussion remind us a little bit about what we are about to discuss, present some open problems, etc. So this period of 20 minutes, it's in this case totally up to Sergei and Igor to distribute and do absolutely as they please, eventually invite people to speak, whatever. It's 20 minutes totally up to them. Now, there's something that we realized, and by the way, this I should also thank the advisory committee for many useful feedback during this weekend, that one thing that could be very helpful, especially for non-experts, is to get the PDF beforehand, especially for this type of session where we are thinking about problems and thinking about questions to ask. So I urge everyone to please send me their PDFs of your discussion sessions ahead of time. And as you notice, this discussion session slides are already online on the next one, and we will soon post the next one. So that should hopefully help a little bit. The last 30 minutes are the period for the audience and for everyone to discuss, make comments, ask questions to the leaders, ask questions to each other. And for that period, please raise your hand, wave, and we will, in this second week, I will really try to give priority to people that did not speak yet. So please, I encourage you very strongly to try to participate if you did not in the first week. If you did not participate yet, and if you wave, then you get really ultra top priority. So please, please, I encourage you to participate. But if you are really, really shy and you really don't want to raise your hand, then you can use Slack. I encourage you in that case to use Slack and post your questions there beforehand, and I will transmit them to the discussion people. So don't forget that often the most basic questions and the most down-to-earth questions are the most relevant ones, and the very latest development on the latest supersymmetric generalization of this or that will probably fade away in a month or two, whereas some big questions about large N QCD will definitely survive for a few more years. So don't be shy and don't be afraid of asking what would be called normally basic questions. So I guess that's it. This was a slightly longer introduction. And the other thing I should say is that, as you notice, the discussions are right before the coffee breaks or at the very end of the day, because while I will try to be rigorous as much as possible with the first 20 minutes, I will not be very rigorous with the last 30. So the last 30, if they go a bit over time, that's fine. People can just leave and go for coffee. As soon as I see cameras on and people are having fun, I will keep the discussion going. So again, if you are participating and if you can, if your internet allows, please turn on your camera. And I pass the floor to Sergei and Igor, and I'll start counting the 20 minutes. Thank you.
Okay, thank you very much, Pedro. And I want to start by thanking all the organizers of this magnificent worldwide virtual event. So I've been entrusted with making a few remarks on color confinement. Just one second. Yeah, this picture is both to remind us that it is organized in Brazil and about the beautiful homepage of the conference, and also of the fact that most of the things I'll be saying will be a repeat of what you hear all the time. But hopefully there will be something new. And in particular, Ofer's great review talk this morning has a lot of overlap with what I have to say. But let me just start with why work on the confinement problem. It's a kind of classic problem that comes to us from the past. It's one of the problems that has cache values associated with it. It's one of the clay millennium problems. And you can see the formulation, brief formulation. You can also find a much more elaborate formulation online, and the status is unsolved. So there is still work to do. Then going back 21 years to an interesting event at another great string conference, Michigan 2000, Millennium Madness. There was a call to submit problems for the next millennium. And I and Oyvind Tafjord submitted this very basic question: can one quantitatively understand quark and gluon confinement in QCD? It came in dead last in these top 10. You can actually still find this online on John Preskill's Caltech homepage and see that basically none of the problems have been solved, at least completely. I mean, some may be addressed more than others, but this problem perhaps should increase a little bit in relevance in view of recent developments. In particular, there is a flourishing of experimental results on strong interactions and discovering of new states, tetraquarks and whatnot. So just a few words about the basic confinement problem, lattice SVN gauge theory. Probably all of you know this. There is the plaquette action, and the basic criterion is whether the Wilson loop has area law. If it does, e to the minus something times a, then the quark-antiquark potential is linear at long distances, and we have confinement. It's very easy to prove this in the strong coupling expansion, where you just tile the big loop with lots of small loops, and you immediately see the area law. But of course, it's harder than that because of asymptotic freedom. We really have to go from strong coupling to weak coupling at the lattice scale. And then things are much harder to see analytically what to do. In principle, confinement can disappear in this limit, but numerical simulations decisively tell us that this is not the case. And while maybe in the 70s you could criticize them because the lattices were small, now they've grown to 100 sites per dimension and perhaps can even go further. So the computers have not been standing still for sure, and we have constantly improving data. Okay, so now what we see, this is one of the commonly shown pictures from Lineweber's group from the lattice. You have probe quark and anti-quark, and we show action density between them. You see that it's collimated into a fabled flux tube or QCD string. It's not infinitely thin. It has thickness of order 1 Fermi. And while the potential between quark and anti-quark is approximately coulombic at scale below 1 Fermi, it kind of becomes linear at scales above 1 Fermi. So strings have definitely been observed in numerical simulations of Yang-Mills theory. They're a very real thing. And they're governed by non-Bugota area action, as you heard from Ofer's talk, and we'll soon hear from Sergei's remarks, with corrections. And it's more than the lattice. Even in nature, we have evidence for these flux tubes because high spin mesons are described by these spinning open strings. They have energy density, again, characteristic scale about 1 GeV per Fermi, which is a lot of energy. If we could harness it, would be great, but we can't because n is too small. What happens? So while we see the evidence that that the leading Regge trajectories are linear, the states become too broad to identify for spin around 6 or something like that and above. So this is a very basic Regge trajectory for rho, A2, and so on. So this is still one of the best empirical evidences for relevance of string theory to real world. Now, of course, large n helps. I always tell people if n were not 3 by 33, there would be no mistake that we're seeing these Regge trajectories would continue to much higher spin before strings can snap by QQ bar creation. As we heard many times in large n gauge theory, in the string dual to large n gauge theory, this coupling is 1 over n. And in particular, this is an example of a stable non-supersymmetric theory of closed strings, loopholes, and open strings, mesons. Of course, as we all know, adding maximal supersymmetry makes this theory conformal, and then we basically know the dual of the theory, type 2B string in ADS 5 crosses 5. In this case, of course, there is no color confinement, but the surprise of 1998 is that there are still strings. And furthermore, it is possible to find more general backgrounds that do describe confining theories. So let's just go back to the now classic ADS CFT result of how you compute the QQ bar potential. You connect it by a string, the fundamental string that goes into the 5th dimension. And because of the scaling symmetry of the whole story, you do see coulombic potential even at strong coupling, where this dual gravity is applicable. But then if you introduce phenomenologically some kind of infrared wall, then the string will go and lie down along this wall, and there it becomes really the confining string. So it happens generally in warped metrics, and there has been a lot of model building, a lot of these along these lines, right? The important thing is that the warp factor doesn't vanish at this infrared wall, and then you've got yourself a confining string. Now, just a few words about this warp throat example that has been mentioned at the conference, mainly in the setting of phenomenology and cosmology, but originally Stressler and I were really worried about it in the context of confinement and chiral symmetry breaking. It's a kind of toy top-down example where you have a rather very well-defined weakly curved solution, which is a work product of deformed conifold and R3, 1. And the warp factor exactly has the properties that were shown before. So one can actually use the technique to compute the string tension, and nicely it incorporates from the nearly Coulombic behavior at short distances to linear behavior at long distances, just like in QCD. This is, I'm showing the lattice data actually from long ago. So this example incorporates dimensional transmutation where the argument of the log becomes the QCD scale. With maybe bold interpretation, you could say that gauge gravity duality has provided us with a kind of physicist proof of confinement in some exotic gauge theories, perhaps even more exotic than the parrot on my first slide. But we don't really have the dual of QCD because of the asymptotic freedom. The asymptotic freedom makes the gravity dual description difficult at short distances. So if you want the full flow from UV to IR, we haven't come up with it in spite of efforts, mainly 20 years ago. So maybe it's time to come back. But one can also go even further back in time, and as a modest step, drop back to some 1+1 dimensional gauge theories, which can also provide some intuition. Of course, there is the famous Hooft model, which is exactly solvable in the large N limit, just 2-dimensional QCD with fundamental quarks at large N. But that doesn't have any adjoint degrees of freedom like gluons. So, so let me mention this adding adjoint matter. Then it becomes not exactly solvable, but can still be, it's a kind of useful toy model for practicing your light cone wave functions. And this was attempted going back to the early 90s. And in particular, the model with an adjoint Majorana fermion, which is a toy gluino, has been receiving some modest renewed attention. It is super normalizable, has non-trivial set of vacua, and actually a mass gap even at the limit of M going to 0. The mass is not renormalized. And interestingly, just to comment on something that's been said, it has both Fermi, so it has both bosonic and fermionic kind of blue ball type states. And asymptotically, they do exhibit degeneracy for a special value of mass, as pointed out by Kutasov. In 93, it exhibits actually exact Bose-Fermi degeneracy. So now the new result, there have been very interesting new results by Kamargotsky et al. And let me mention a paper that we wrote with Silvio Pufu, and who is at Princeton, and Ross Dempsey, a graduate student at Princeton, where we basically, in addition to the massless adjoint or light adjoint, we added NF fundamental Dirac fermions. So it's a kind of souped up version of the Hooft model with additional explicit adjoint quanta. Now there are much more complicated states where mesons have a Q bar and Q with a bunch of adjoints in between. And they can again be either bosonic or fermionic. You see multiple Regge trajectories. And the interesting thing here is that this theory actually, when this adjoint mass is 0, it's not confining, contrary to the sort of intuition you might have that all 1+1 dimensional gauge theories are confining because just perturbatively the potential is linear. Basically, what happens based on the results that we observe with Dempsey and Pufu is that the spectrum of mesons is continuous above a certain threshold, which means that the QQ bar potential is asymptotically flattens out. At short distances, it's linear, but it just flattens out. And this means that the massless adjoints renormalize string tension to 0. This was sort of conjectured long ago, and then using non-invertible topological lines was demonstrated in a different way by Kamargotsky and collaborators. For a very small mass, it becomes non-zero, giving a model of weak confinement, and one can study various string tensions in this model and so forth. So let me summarize and pass on to Sergei. One lesson is don't take confinement for granted, even in 1+1 dimensions where it just seems obvious. It can actually be kind of screened in a certain way. I think proof of color confinement in 2+1 and 3+1 dimensions would be very important. Not both as basically giving us confidence that we're doing the right thing, and also for practical reasons. What we would like to improve connections between QCD and fundamental strings, and hope to get new analytical insights and approximations to spectra of hadrons and K-string tensions, where K is the number of quarks on one end and quarks on the other end. And this should be guided by the improving numerical results on SEN gauge theories for a range of n. Recently, there was yet another big opus by Thanadara and Tapper, and there are other groups working on this. So I think a good road lies ahead, I think. And let me finish here and pass on to.
So while Sergei sets up his share screen, let's thank Igor. So you are at 14 minutes, more or less. Of course, I'll give you a little bit more. You might be muted if you are speaking. We can see your screen, but I cannot hear you. Can people hear? Okay. No. Maybe if you disconnect your headphones, it might work. Sometimes that's the issue. So just.
Is it better now?
It's working.
Yeah, I don't know what happened with my headphones somehow. Okay, so sorry for this confusion. So let me present my remarks, and I hope we'll have a fun discussion session afterwards. And my remarks will be roughly, well, they will be largely complementary to what Igor covered. So namely, I will assume confinement. And the main question I want to discuss is what is the result in string theory one gets there. And I think compared to some other sessions, one of the questions to discuss here is it feels that relatively few people are actually thinking about this problem. And it would be nice to discuss why is it so. And I think the related question is what are the right questions to ask in this field. As far as the first question is concerned, oops, sorry, it's not, yeah, okay. The answers I heard is that, well, gravity is cool, QCD is boring, there is no clear, sharply formulated problem here, the problem is too hard, the problem is morally solved by holography, and clearly there is some tension between these answers. And I will try to convince you in the few minutes which I have that actually all of these misconceptions. So first, let me start with a limited sharp version of the problem, which was already explained by Ofer very nicely in much detail. Namely, let's consider an infinitely long string in the string planar limit on the gauge theory. It defines a microscopic relativistic theory of fluctuating 2D geometry, which I'll naturally to call asymptotically flat 2D gravity. And in this setup, then the natural question to ask is what is the S matrix of this object? As reviewed by Ofer, the low energy asymptotics is largely fixed by symmetries. This is a system of Goldstone bosons plus maybe some additional massive modes. So I think as in many theories of gravity, the most interesting question to ask what happens at high energies here. And well, that one advantage of having sharp formulation of the problem is that at least it allows to see what are not good questions to ask. Namely, I guess in early days of like idea of 1/n expansion, the reasonable goal seemed that, well, 1/n expansion looks like a genus expansion. So the reasonable goal was to solve the free planar theory and then to develop string perturbation theory. And that works beautifully in unequal force Mills. And this picture tells us that will never work. It will never really work in pure glue. And the reason for that is that Worldsheet theory, which you obtain even in a strict planar limit, is still non-integrable. There are, as explained by Ofer, there is particle production on the Worldsheet. So we won't ever be able to really solve the planar limit of this theory. So the question, what can we do instead? Well, and there are several directions which I see. First, it would be interesting to find a confining theory with integrable dynamics on the Worldsheet. It looks very hard, and I will comment that maybe there is a reason why it's impossible at dimensions higher than 2, sorry. But I think the best place to look may be the family of two-dimensional adjoint QCD-like theories, where there is a chance for that. Then one can do bootstrap. And finally, one may try to develop high-energy perturbative expansion for the Worldsheet theory. So let me give some comments on this last point. Well, and it kind of addresses what Ofer was asking in his talk. So why would one expect that there is something like integrability at high energies on QCD string? And I think the cartoon which motivates that is presented here. This is a cartoon of scattering, of Worldsheet scattering at high energies in the asymptotically free theory. So degrees of freedom on asymptotically free theory at high energies, it should be partons, gluons, and pure Yang-Mills. Then scattering goes through hard collision described by perturbative QCD, but because theory asymptotically free, one doesn't expect particle production there. And then because string cannot break, will be this zigzag period, and then particles will bounce back. So first, this picture tells that the full S matrix will be factorized. There will be long energy, long distance contribution coming from zigzag and UV contribution coming from hard collision. And because zigzag produces non-trivial time delay, it tells that the theory cannot be free. The best it can do, it can be integrable. So that's a kind of motivation of thinking about high energy integrability. And clearly, well, it's interesting to study this zigzag. And it can be studied quantitatively, at least in 2D adjoint QCD, where actually it does lead to interesting n-body relativistic integrable model. And there are two consequences of the zigzag. One is that it leads to long time delays as a result of collision, reminiscent of TT bar deformation. But it's different for TT bar because if the two particles are different, two quarks are different, then actually this process here goes, it's total reflection rather than total transmission in TT bar. Still, it's kind of similar in spirit in many respects. And furthermore, if there are light degrees of freedom here, like in high dimensional Yang-Mills, then it's expected, because there is long period when particles move with acceleration, one expects that there should be copious soft particle production. And that's maybe kind of a sketch of the no-go for exact integrability in confining theories in high dimensions. But also it tells us that TT bar is described by some very simple model of quantum gravity. It's roughly speaking JT flat space, JT gravity. But it tells us that the 2D gravity describing actual confining strings is more interesting. It also has this property of soft particle production, which is we all like in conventional gravity. And also this picture suggests what the expected degrees of freedom. So basically one inserts bulk fields into Wilson lines, and in 4 dimensions, this way one gets Goldstone modes, but also one expects to get gluon paralyzed in transverse plane, which corresponds to kind of pseudoscalar excitation on the Worldsheet. And that's exactly what one finds on the lattice. And that's what we call axion. We should probably call it just gluon. And interestingly, as was mentioned by Ofer, so the coupling of this particle on the lattice takes an integrable value, supporting this picture, which was presented before, that maybe there is some approximate integrability in high energies. So let me come to bootstrap. So bootstrap, as we heard already in some talk, so it allows to restrict high energy, some Wilson coefficients in the low energy theory. And the interesting conclusion which one finds here, one finds that there is a boundary of allowed region, and there are 2 shores of this boundary, and one shore can be described by something like roughly conventional holographic Liouville shore, because what one finds there, one finds a sharp scalar resonance on the Worldsheet there. And another shore, which corresponds to more like actual QCD, there one finds sharp pseudoscalar resonance. And there is a piece of good news here that one really finds two shores rather than an island, meaning one can interpolate from one to another. So it looks like that these two regimes are not completely disconnected, but also it suggests that, well, actually, actual QCD string, it operates in different regime than conventional non-critical strings or holographic models. So finally, she already asked this question. So what is it? Can we say anything about short strings or glue balls? And at Strings of Jerusalem, I presented predictions, semi-classical predictions for glue balls, quantum numbers of glue balls in D equals 3 on Mills, well, which predicts the quantum numbers. And that was an experimental situation back then. It worked for first 3 levels, and there were some tensions at the 3rd level. And this is experimental situation now. It looks to work very nicely for first 4 levels, which means first lightest 39 states. So I think this picture really shows that glue balls, they do look like oscillating strings. And we structurally understand, I think we're close to claim that we structurally understand the whole spectrum of glue balls in D equals 3, which I think is very interesting. Of course, there are many details here about mass splittings, which needs to be calculated. So let me finish with a propaganda slide. So one can often hear, well, that string theory may be beautiful, but we may never know whether strings are realized in nature. Well, I think we see that's clearly wrong. QCD is a theory of strings, and string theory was born to describe strong interactions, but then was repurposed as a theory of gravity. But I think one of the lessons we learned in the last 20 years that gauge theories and gravitational theories, they're much more close to each other than one could have expected. And in some sense, confining strings, perhaps they provide the most basic example and reason for connection between gauge theories and fluctuating geometry. And they may be the closest we'll get ever to doing experimental quantum gravity. And I should say that, well, in particle physics, we may wait another 30 years for a new collider to come and provide new data for us. But I think we are very lucky. So we have a tractable and fundamental problem to solve while waiting. And I think participants of String 2051 will be happy and puzzled if we don't make an effort and solve this problem now and leave it to them. So thank you.
Thanks very much. Let's thank Sergei and Igor. And as I said, please, if you can turn on your cameras, raise your hand if you want to ask a question, wave if your question is related to what is being discussed at the moment. And maybe there is already a question in the chat that from Nikolai. Nikolai, maybe since you would be one that I don't think you unmuted yourself yet. So I'll put you on the spotlight if you are there.
Yes. Hi, everyone. Yeah, well, I asked my question and also I followed up, so I don't have much more to say. I was asking whether, well, n equals 1 star is an example that is a 4D gauge theory. Well, obviously a toy model with a certain amount of supersymmetry that has confining vacua, and so I was wondering whether it fits the bill as an asymptotically free theory or not, because of course the UV is n equals 4 Yang-Mills, which is, well, it's a bit weird. It's both asymptotically free and asymptotically safe. So I'm not sure if it's a useful toy model that we can learn stuff for real QCD, but anyway, so I was just asking for an opinion from Igor, basically.
I mean, I can elaborate on my comment a little bit. I mean, of course, embedding theories in n equal 4 super Yang-Mills is fine, and we can make some of the superfields massive, and then formally you get just pure supersymmetric law dynamics. That's great, but I think we want to be in the regime where first you decouple all the extra degrees of freedom of n equal 4, and then you follow the RG of the supersymmetric law dynamics starting from pretty weak coupling. So you start, that's what I feel. So you have to get an approximately asymptotically free regime, and then you have to see the dimensional transmutation in that theory to declare victory. And there is a related story. So generally, I think one thing that you said is very valuable, that maybe as a good goal, we should not be thinking about the just pure glue SUN, but supersymmetric SUN, n equal 1 supersymmetric, because that's a confining theory with lots of wonderful properties. Another approach is this deformed conifold that I mentioned. There again, formally, far in the infrared, you just have pure supersymmetric fluid dynamics. But the problem is you want to be in the regime where these cascade steps are very far apart. So you have to, again, exit the gravity regime, But I think there is some glimmer of hope here that maybe if you go to sort of start with this, as often in life, you're sort of on the other end of where you want to be, right? Like we saw that in strong coupling expansion, you're far from where you want to be. I think in gravity duals, you are also kind of far from where you want to be, but hopefully we can make this journey. Was that a reasonable answer?
Yeah, I was just wondering out loud. Yeah, certainly. But we know models of like pure n=1 Yang-Mills, like model Sena Nunez, but then the UV completion is
not
a bit
pure n=1 Yang-Mills. It has lots of other stuff.
Right. The
It's
KK scale is
scales.
not.
We want to decouple. We want to separate scales so that we can say for a very large range of RG flow.
Exactly.
We're in the n=1. I mean, as far as I can tell, all the models we know have this issue, and that's why I could not declare victory by gauge gravity duality.
And maybe a final comment, maybe this scale that we want to split is, again, related somehow to this issue of last week of ADS4 scale separation. I mean, it seems that we're unable to kind of find this hierarchy of scales in supergravity so that we keep control.
Right. I think it's inevitable we have to exit the supergravity limit. That seems clear, and that's why we need a whole new toolbox.
Jaume?
I mean, the comment is unrelated to ADS50, so maybe I don't know if people wanted to comment about that.
No, but people are not waving. No, this is a very clear rule. If you are waving, that's okay. Otherwise, it's new people that have priority.
I just want to make a comment about the presentation by Igor and Sergei, and it's just about what are the expectations about confinement versus deconfinement. And I think kind of recent work not in 2 dimensions, but in 3 dimensions actually kind of shows that actually 3-dimensional gauge theory, say with an adjoint quark, actually, contrary to naive expectations that it would be a confining theory, is actually deconfining. So I think we have to upgrade our expectations about what happens to confinement, even in 3 dimensions. And one important difference in 3 dimensions versus 2 dimensions is that in 2 dimensions, the confinement essentially disappears the minute you give a tiny mass to the quarks. Well, this is not what is expected in 3 dimensions. The confinement is expected to survive kind of a finite mass for the quarks. So that just was a comment.
Could I make a comment, just a very brief comment to respond to this? I think in 4 dimensions, it's also true. If you add enough, say, gluinos, adjoint fermions, you will just lose asymptotic freedom. You will go to the infrared free theory, right? So in any theory, if you add enough adjoint, in any dimension, if you add enough adjoints, you lose confinement, it appears.
No, but I was talking just like exactly the example you were discussing in 2 dimensions, just add one adjoint. As you went
right.
with
Yeah, where the boundary is in 3 dimensions with enough adjoints, you very clearly see that if you take the large NF, like many adjoints, you very clearly see it's a conformal theory. Then you start dropping an F, and the question is, where does this conformal window end? That is the hard part. And yeah, I should learn more about your work about 3D, but I would say it's definitely always true that with enough adjoints, you get deconfining behavior, and where the boundary is maybe somewhat dimension dependent.
I don't think it's about the number of adjoints. It's just one Majorana adjoint.
Yeah, no, I was just bringing in the case of many adjoints, right? Where you clearly see the CFT in 2+1 dimensions, right? So then in 3+1, you also see a free CFT in the infrared.
But it's not the same mechanism that Jaume spoke. When you add lots of adjoints, the phases that you observe of gauge theory are the same phases that you see semi-classically.
Okay.
In the example that Jaume brought up, the deconfined phase is not semi-classical, it's extremely strongly coupled.
Yeah, no, I agree. sorry if this comment was a little off mark, but I've been thinking a bit about related things.
Not at all. Let's maybe Rajesh also has not yet chimed in the discussion. So following the new rule, let's move to him.
Thanks, Pedro. So I just had a sort of a thought. I wanted the experts' opinion in trying to connect the top-down to these effective strings, whether, and this was something with Ofer, we were just chatting also, but whether this anomaly term could be something which is very robust and which is something you could hope to connect between from the bottom-up approach to the top-down approach, and the term that Ofer mentioned in his review, the one with 26 minus d as its coefficient, and in particular, that seems to be it seems to be a very universal term, and it's not unreasonable that you can sort of see something like that in a microscopic description. And in fact, in the ADS3 example, we see something very close to that sort of a term. So I was just wondering whether anyone had any thoughts on the possibility of connecting these two approaches through a term like that.
I may say that. Well, first of all, this term is really just as Ofer explained. This is really calculable one-loop effect in low-energy theory, and this is the same effect as familiar Virasoro anomaly. So in that sense, it's present everywhere. But I think, well, at least from my viewpoint, there is interest in numerology, which is somewhat related to what you are saying. There is interest in numerology related to this term. Namely, one thinks about four-dimensional gauge theory, that the coefficient which appears in this term, it's exactly the same coefficient as in one-loop beta function. It's like 26. It's 26 minus 4 is equal to 22.
22, yeah.
Which is, and one-loop beta function clearly very, very UV thing. And I think it's not a coincidence. For instance, one may add adjoint matter in gauge theory, add adjoint scalars and fermions, and one knows then how this thing is shifted in UV theory. And it's shifted in the IR theory in the same way. And that's kind of, I think that might be one reason why integrability, what I'm saying, that integrability is in conflict with confinement. So somehow to cancel this term, that means to restore integrability, in UV theory seems to correspond to getting conformal theory. But of course, it's a mystery how to relate it to, which might be related to what you're saying, because it requires really relating IR and UV to phenomena.
Yeah, in fact, that's interesting that you mentioned that, because the picture I was having from the examples I'm familiar with was that term is essentially coming from the radial mode, from the radial direction in a holographic picture. In some way, it probably could be thought of as the kinetic term of the Liouville mode, or the radial mode, and that would be natural that it should have the information about the beta function. So, yeah, okay, thanks.
So, as I see no new people, maybe let's go to Sandeep, and then unless a new people raises his hand.
I'll quickly ask and get off so others can participate more. But I wanted to respond to Sergei as to why more people are not working on the QCD string by just saying why I'm not, so you can respond to me. You know, I was always held back because the real world has light quarks and therefore strings will break. But I say this by adding all, so that, you know, when you go to, you know, talks on data and phenomenology, which I used to, at least till some time ago, it's a striking fact that the process of fragmentation, right, how quarks break up into hadrons is actually often modeled using a string model, like the Lund string model and so on. And so, you know, in the real world of phenomenology and using models, the string model is quite useful for that process, which involves strings breaking due to quarks. So am I being too conservative? Is there a way to put that on a better analytical footing and make it actually useful? This was my question. You can ignore it, all of you, if you like.
I think it's a very good point. But also, well, first, as you mentioned, like really in the real phenomenology, people use string model. But also we know that 101 expansion then for many purposes works quite well. So it seems reasonable. And one expansion, it leads in order, the string breaking effect is suppressed. So it seems reasonable, if one wants some project systematically, it seems reasonable to start at infinite end limit where string breaking doesn't happen and then include that perturbatively.
But just very quickly, I mean, would it be worth trying to actually model fragmentation in a systematic 1/n expansion and seeing? I don't know of any work which has happened in that direction, but you can correct me.
I think that's absolutely yes, right? But we just don't understand well enough this QCD strings to do that.
Thank you.
I think Pythia and such programs use basically Nambu string, I thought. So in that sense, it is phenomenologically relevant. But yeah, maybe, I don't know, maybe they tweak the string action too to some extent.
Well, to add to this, yeah, because we see, like in pure glue, we see this massive excitation on the string Worldsheet. And there are reasons to expect that it will survive also in actual QCD. And if so, it should translate into some features maybe of the PDFs, really of some nature of physical observables. So I think that's a very interesting question, but it's just that one, at least for me, it's too hard.
Thank you.
Yeah, so I have two questions related to what Sergei was talking about. So first is, so Sergei, you were suggesting this approximate integrability in the high energy limit on the confining string. I'm trying to understand how to formulate that kind of in the language of usually what like to think about RG flows. So does it mean that there's supposed to be a UV CFT and we can think of some deformation of that? Or I mean, what does that actually mean?
Well, no, I think we know that there is no UV CFT because of this TT bar like phase shift. So this is integrability. If it's there, it's really it's some TT bar asymptotics. So it's asymptotics which is incompatible with CFT. And I think in massive theory, like adjoint QCD in 2 dimensions, I think there is a real chance, as I was trying to say, that there is a hope that really there will be actual integrability because there are no soft particles. In actual QCD, because there are soft gluons, I think it's hopeless to have, well, but I will be happy to be wrong, but it's very hard to expect actual integrability. But I think there is a hope to get integrability for some properly defined exclusive observables, like some jet-like observables. So in this scattering I was talking about, yeah, one expects there is lots of soft particle production, but as one always does in QCD, one may try to define some jet-like observables, but suited for these 2-dimensional kinematics. And I think there is a chance that behavior of those described by integrability, by some integrable approximation.
The TT bar phase you're talking about, you know that's true in the high energy limit, or is it the low energy expansion? Because
well, that's the picture which I draw, right? So I think, well, if one, and in 2-dimensional adjoint QCD, one can really derive that. So because if you consider Worldsheet scattering of 2 partons on QCD string, yeah, they go through each other. That's asymptotic freedom, and they stretch the string. And there is a long period we describe really by semi-classics. And from that, you get time delay proportional to collision energy, and that's CT bar.
Okay, fine, but you might be able to remove that gravitational dressing by going to a different gauge, just like the usual going between static gauge and the conformal gauge, right? I mean, one could imagine maybe in another gauge you actually have a CFT in the UV.
Well, it's not a question of gauge because this is a physical effect, which is this is time delay. But one can do TT bar undressing, and that one will get kind of that. So I think the expectation for S matrix, indeed, there is a hard process. Then there is some factorized, like some dressing, TT bar like dressing, which describes this long time delay. And that's what we mean by integrability. By the way, these integrable theories, which Ofer was referring to, they're all just TT bar dressing of free theories. So by integrability, one really means here just this TT bar deformation.
I see.
But what I also was trying to emphasize in my talk, that in actual QCD, like in 3 and 4 dimensions, one expects that on top of these 2 things, on top of this long time delay and hard process, there is also copious soft particle production during when this zigzag forms. Just because there is like ends of zigzags, they move with acceleration, and one expects Unruh type radiation coming from there. So that I think is very.
Let me maybe ask something related to that. So when we scatter these two particles, these two goldstones in the flux tube, the absolute value of that S matrix that quantifies the amount of particle production at high energy, do you think, or do people think it goes to 1 and it's purely elastic, to 0 and it's dominated by inelastic, or something in the middle?
You mean 2 to 2 S matrix, right?
Yeah.
My expectation it will be exponentially small, just like 2 to 2 scattering in gravity. Well, because it is a theory of gravity. And the reason for that is because there is a semi-classical process, which one expects to be there in the presence of massless modes on a string. So the dominant process is really when you produce lots of stuff, plus maybe two hard jets. But a strictly 2 to 2 process, I expect that to be exponentially small.
Let me maybe pass to Zohar. Yeah.
It's about, I think one question that could be discussed is that this proposal of Sergei for the asymptotics of the scattering in terms of this TT bar deformation is also coincident with the classical analysis, classical answer for the time delay. And I think it's kind of interesting as a general physics fact, if it's correct, that the high energy limit is the same as the classical limit.
Well, but again, that's something familiar in gravitational theories, right? So that some like rough aspects of high energy scattering can be captured by semi-classics in gravitational theories. And I think that's one way to view it this, right?
Is there an expansion you can do to characterize the deformation away from this UV limit that's integrable?
Well, that's an excellent question. And well, I think the hope is that, well, it's some kind of high energy expansion, and the hope it may work exactly because that this violation of integrability is some long distance process. So kind of there is a hope to factorize it away. That's one strategy, and another. Well, again, of course, in a massive adjoint QCD in 2 dimensions, if the mass is heavy, then there is an expansion parameter. But also one may try to do something like D-26 expansions. That's related to comments which we had before. Of course, D-26 for D equals 4 sounds like a big parameter, but it is divided by something like 16 pi or something. So one may try to do maybe formal expansion in that parameter, which would be like expanding around a conformal field theory in the UV. But yeah, maybe there are other smarter suggestions, but that's one of the central.
Maybe let's go to Mukund.
Thanks. I was just going to, I had a question, but let me pick up on something that was just said. So when you say that the theory is like gravity, you really mean in the TT bar sense, that it's well,
the Worldsheet. Well, at the most basic level, I mean, this is a theory of fluctuating 2D geometry. And in TT bar case, we know exactly the corresponding gravitational theory, which is roughly speaking, flat space GT gravity, meaning that integral over flat matrix. And here I expect there should be some dilatonic gravity like that. So there is just some deformation of that. I expect there should be some 2D model of gravity, which is dual to Worldsheet, which describe Worldsheet dynamics.
Okay, let me go back to my technical question, which I sort of missed in some of the discussion. So this D-26 term, I understood from Ofer's talk to come from just imposing space-time Lorentz invariance. Now, what happens if your string is probing a cloud background where Lorentz invariance is broken in target? Is it still D-26 or is this term modified?
It's not a term in there. It's term in there. 1PI effective action. It's not a term in the kind of action term which defines the action which defines the theory. It is just calculable effect which is present there. It's one loop effect which is present there and which is related to particle production. And yeah, if you put it in, you put theory in a curved background. If it's non-dynamical background, you can definitely put gauge theory on that. One would still at this at least, well, it depends on the scales, but if background is curvature is long, then one expects, of course, there will be this term present. It's well, if there's a large curvature background, it's not clear well.
Okay. John?
I have a sort of naive question, which I guess is for Sergei. So in the literature on field theories on loop space by Migdal and Polyakov from the early 80s, an important role in their thinking was played by an analogy with chiral models in 2 dimensions. And in particular, the equation that they actually study is this loop equation, which they think of as like the analog of some integrability equation in the chiral sigma model. And that's, so you'll notice that didn't appear in my talk. We were studying some equations of motion instead. So my question is just whether this integrability that they were looking for, is it the same integrability that you see on the worldsheet?
Yeah, I don't know. Yeah, I should look in the literature.
Maybe I shouldn't put you on the spot. And does somebody else know anything about this?
Yeah, maybe I can comment then. So I think it's different. Yeah, because like the integrability Sergei is talking about is the worldsheet integrability, whereas like integrability they're talking about is like defined in a more like abstract space, which is more like a target space. Well, not really target space, but as far as, yeah, I also try to understand the relation, but I think it's different.
Thanks. By the way, let me advertise a beautiful talk that Shota gave at the London Integrability Journal Club, where he gave an introduction to that type of integrability of loop space and so on. So you can I really recommend it. I think we should test the screen share. So while we test the screen share, people are free to ask some more informal questions if she and Mukund still want to ask some more questions. Otherwise, let's thank Igor and Sergei for a nice discussion and reconvene at 40 past the hour.
So can I ask another question? So Sergei, so about this 3D integrable string, regardless of whether that's a theory of some 3D large gauge theory, I'm trying to understand what additional ingredients are needed to actually determine the short string spectrum, as well as even possibly formulate perturbative string scattering amplitude. Do you have some suggestions, like maybe some boundary condition on the floating point, something of that sort?
Well, my feeling, so this integrable series, this is really theory on infinitely long string. It's just a statement that like the TT bar dressing of a single Goldstone boson in three dimensions is compatible with Poincare symmetry. But my feeling, my expectation that actually it's not possible to define integrable theory of short strings. The way it happens is closely related to the fact that in light cone gauge in 3 dimensions, one doesn't see the anomaly. It's kinematical cancellation. And I think that long string sector is just not smart enough to see that there are some inconsistencies, which also in D equals 3 require theory truly to be non-integrable. Right.
But wait, there's some no-go argument. I mean, I'm not talking about necessarily of a given 3D gauge theory, but just construct some perturbative.
Well, for instance, if one, like there is a work of Townsend and Mizinchescu, well, as they pointed out, if one works do light cone quantization at D equals 3, when there is no local anomaly in Poincare algebra, because G plus I, like that commutator vanishes kinematically, but one necessarily gets anions in the spectrum. And that looks like anomaly to me, because one starts with a theory which is Poincare invariant, and the result of quantization, you get a spectrum which has anions. So you change the symmetry of your theory on the way.
But the logic of this is a bit confusing, because I would think that there should be some freedom. It's not like you already know exactly what theory is, right? I mean, there's some I would have thought that there's some freedom you can put in terms of choosing some boundary conditions and things like that.
No, they were doing just like quantization, and there's a freedom which they had there is this normal order and parameter A, which usually fixed by anomaly, by Virasoro anomaly, and there it's free. And they would show that at any value of this parameter A, there are irrational anyons in the spectrum. And instead, when we talk about spectrum of short strings, we do something very different. We kind of quantize around rotating background. In that way of treating theory, one automatically gets correct spin quantization. But yeah, so my expectation is that there is no really microscopic three-dimensional like theory, integrable theory of short strings. But it would be very interesting if I'm wrong. But
I think short strings, one can hunt for integrability just looking at, say, pure glue spectrum in 3 dimensions and continue to large N. And the integrability would be manifested by some accidental degeneracies between different, say, charge conjugation glue balls, and I don't think we see it.
No, they were clearly.
My question was specifically not necessarily making reference to the large gauge theory.
But you want some large N gauge theory that would be described.
No, not. I want to construct the perturbative string theory, like how we construct critical string theory, right? I mean, I'm just trying to understand whether it's possible to construct a weakly interacting or perturbative, perturbative critical-like string theory in 3D, since there's a consistent theory from a long string. What more can we, or can we one rule out, or what more ingredients can one add to complete into a perturbative string theory? I mean, it doesn't seem obviously impossible.
I think it's not obviously impossible. It would be very interesting. But
I have a selfish question since we are in this very informal period. So with the bootstrap, we have this big region of allowed parameters of the S matrix, right? And one short seems to be relatively close to what we measure, the other not so much. What other things could we impose to shrink these regions? Any suggestions of what else could we impose? We imposed the right soft behavior. We imposed what we knew from effective field theory that Ofer told us. What else could we try to impose and shrink this region and make some sharper predictions? Do people have suggestions?
Can you try to impose because you have in your bootstrap, you have some additional very broad and very heavy zeros, very broad and very heavy resonances. Can you somehow impose the condition that you will try to remove that, kind of to minimize the number of zeros of S matrix in the physical sheet? So can you impose that?
Yeah, we have some discussion in our version 2 of our flux tube paper. I think the short answer is no. It's hard to push zeros away of analytic functions, right? If you have some general functions, if zeros want to come in, they come in. It's very hard to keep them away. Poles is easier, right? So, but zeros, they want to be there, they will be there. So no.
Is there any update on 2 to 4 processes? Because that's a thing that would obviously help.
Yeah, that we put on hold. I think Andrea's new technology could be very powerful for that. He has this dual technology. I don't know if he's here, but I think according to him, that is, we started, and then it was too hard, so we moved to 10D supergravity, which compared to that was easy. But now I think with his technology, I think maybe 2 to 3 and 2 to 4 is.
Yeah, because it's multi-particle processes which really tell you that you're dealing with Goldstone bosons. So I think it would be very good if you could include those. Right.
What about just estimating some soft radiation and use that to bound the total?
Yeah, that would be great. If we had an estimate of how inelastic the S matrix is, that's why I was asking Sergei, do we know anything about the absolute value of S, the fall off, right? So if you could tell us that the absolute value of the S matrix at this much L string is 0.7, that would be great. Then it would be straightforward to input that in the S matrix. That would be the easiest thing to input. You just change a 1 to 0.7 and you click Shift Enter.
I think there was a paper just a few weeks ago where this soft radiation was modeled using the Unruh effect.
Ah. Wow, I missed it. Oh, very interesting.
By Aminov.
The authors, do you remember any of the authors?
Yes, I'll write in the chat. He just, I mean, the idea was that because these particles on the zigzag, they undergo constant acceleration or deceleration. You can model the soft remission with the Unruh effect.
But that was in the DS3, right? That wasn't in the for flat space string.
Right. It was there was some octap version, but maybe the idea is correct that because these particles are undergoing constant deceleration, you can use the Unruh effect.
Yeah, no, that's exactly what I was. Yeah, so that sounds like the right thing to do, right?
I'll write the name of the author in the chat.
No, that would be awesome.
Well, also what Sergei mentioned a bit, alternatively, one could try to understand connection with perturbative high energy QCD and estimate this particle production from there in some way. But
oh, of course, also, as you know very well, Pedro, at low energies, there is at least universal contribution to particle production. Well, at least, well, not universal, but in 3D, there is no universal part. But from lattice, we determined the coefficient of R² operator. And that R² operator also implies 2 to 4 processes. So we have some input from lattice about how much particle production one expects, at least at low energies. So if you can at least use that as an input, that would already be.
Yeah, but okay. My feeling is that at low energy, it will not change anything, but I think we can discuss later. The point is that if you just say something about the derivative of how it starts going down, what the S matrix will do is it will start go down and then immediately go up again, and it will do nothing. You need something more integrated. You need to say, starting at this energy onwards, I have this effect that is big. If it's something just about some derivative being negative, it will be very hard to make use of that. I had to leave. I had to leave for a few minutes, so I did not see if everyone tested the share screen already. So and
just waiting for Michael. Hi, Michael. Want to try to share screen, Michael?
Sure. Is it there?
Not yet. I don't see. Do other people see?
No. I also do not see.
So it just looks dark. It doesn't look like there's anything. Now I see it.
And now it's good.
Oops. I'm not sure I can advance properly. How about now?
Looks good. You want to just make sure you can, yeah. Looks
good.
Good.
Looks like I got it.
Okay, thanks, Mike.
By the way, Dimitris, if you want to ask something, now we are in this super informal period.
Hi.
Not
yes.
just a minute.
Okay, so I have a really sort of basic question. I guess I wanted to understand to what extent the general structure of effective string theory has the structure of a nonlinear sigma model, perhaps supplemented with curvature terms, or whether one needs to, at higher orders, whether one can get away without ghosts, or whether one needs to include ghosts like in fundamental strings. For example, and yeah, and a related question is whether the orthogonal gauge that Ofer was referring to leads to non-local effective action, whether it's a differential gauge or algebraic gauge, whether the corresponding effective action in general is non-local or local. There's a few questions. I don't know if anyone wants to just to take a stab at it.
Well, these are good questions. I mean, in the orthogonal gauge, I mean, well, the effective action that I wrote down was local, but it had these negative powers of fields. I mean, so obviously we don't expect that to be there in the fundamental level, but you can add a few more fields on the worldsheet that are massive, and then integrating out would give these terms. So I think the expectation would be that even in the orthogonal gauge, I think the expectation is that the theory should be a local theory. But it
so
should have
is it actually
some extra modes beyond the nebuloso bosons.
Just to clarify, is it a differential gauge or isn't it algebraic gauge? Because I mean, conformal gauge in fundamental string theory, or whether you need whether the gauge is set by differential equation or by an algebraic equation.
Oh, no.
For example, conformal gauge.
Yeah, no, you need a differential equation. I mean, you're solving
because
for the induced metric, so yes, it's differential.
Okay, but then isn't there a general argument by Polchinski that the corresponding effective action will necessarily be non-local, at least at some order it will appear in general? There's this argument by Polchinski in his vertex operator paper 1987, I guess, where he discusses this.
Well, Dimitri, I don't think we're going to have time to answer your question here. Maybe we can continue it on Slack because we're going to start in 1 minute. So.
Okay. Yes. I unmuted late. Okay. Thanks. Anyway.
Sure.
Yeah. Very good. Well, maybe we can thank everybody for that was a very interesting discussion. And Lara, do you want to share your screen? Just get things set up while that wraps up. Great. So thanks everybody for being here. I guess I'm moderating this next session, and Lara Anderson is the next speaker. She'll tell us about progress in string compactification. So Lara, I'll give you a heads up 5 minutes before your 25 minutes is up. So please take it away.
Thank you very much. Thanks also to the organizers for putting together a really interesting roster of talks, both last week and this week. And thanks to everybody for hanging in there late in the afternoon. I know this is a lot of things to listen to in one day. So I'm going to be talking about the subject of string compactification. And in particular, I'm going to talk about two papers that were completed recently in collaboration with James Gray at Virginia Tech. The first one with Magdalena Lefors, Matt McGill, and Robin Schneider, all at Uppsala. This was a project that was done while Matt and Robin were visiting students at Virginia Tech and proved to be a fruitful visit. And then I'll also be talking about work done with James, Mattis Gertis, Sven Krippendorf at LMU, Nikhil Raghuram, who's our postdoc at VT, and Fabian Ruehle at CERN. So to begin, I'd like to start with a little bit of quite general motivation, which is we've heard about lots of different limits of string theory, lots of different effective theories that are obtainable from string theory through different approximations in different dimensions. The process of beginning with 10D string theories and trying to get down to particular, for example, 4-dimensional effective theories is one with a history dating back to the start of string theory, and it is continued over the last 30 years to be a challenging one. So in general, if we begin with some higher dimensional string theory, we need to reduce on compact geometry to obtain 4D physics. And the question is, how does one actually practically do that? So you need a tremendous amount of technology to actually push the effective field theory down to the level of detail that you'd really like to be able to decide, is this useful, for example, for the 4D universe that we seem to live in? So here I put on my slides, for example, can you calculate the mass of the electron in a string vacuum? That's already come up in this conference as perhaps an overambitious hope in the early days of string theory. So the goal of my talk today is not to say that we can calculate the mass of the electron in some fully stable ideal string vacuum, but rather in any string compactification, how do you actually get out a number even if it's wrong? What are the rules that one would want to impose on the geometries that you want to study, rules for top-down model building, patterns, constraints, and predictions? So in general, as we know, there's truly a vast number of different compactification geometries that might be considered, but the question of which ones you care about is an extremely difficult one. Whether there is 10 to the 500 or perhaps an infinite number of string vacua in some corner where none of those theories have an electron, maybe that's a different question or a question that you aren't so interested in answering. What you want to understand is something in this Venn diagram. If you have some field theories of interest, here I highlighted string Vino, but this could be any theories, gravitational or gauge, with properties you're interested in. The question is, how do you understand what subset of string dimensional reductions can actually lead to the physics you're interested in? And of course, that's an incredibly complex question where we replaced which of possible effective field theories with which geometries in general. So this is a broad set of problems and aims to be solved, but I want to highlight a few of these effects today in the context of n=1 4-dimensional compactifications of the E8 cross E8 10D heterotic string, just to illustrate how one might try and gain some traction both on these large-scale questions about general constraints and patterns, as well as how do you push the theory as far as possible. So to begin, I'm going to talk about one particular feature of a 4-dimensional heterotic compactification, which is the trilinear Yukawa couplings that arise in the superpotential. So as a very broad strokes, in the background of a heterotic theory, we have some compactification manifold, say 6-dimensional, and a holomorphic vector bundle over it. And in terms of that background data for the theory, we can perturbatively define the 4-dimensional theory and fluctuations around that background. Here I've defined a gauge field in the compact extra directions, i.e. x, and fluctuating around some initial value of that connection, you have what are going to now be 4D matter fields phi that are expanded in a basis of harmonic 1 forms over the compactification manifold. It's well established then that if you ask how do those fields couple to one another via the superpotential, then the trilinear couplings have a simple form in terms of integrals of these harmonic forms over the background manifold. I'm going to start saying Calabi-Yau here is the simplest class of geometries, but we'll broaden that out later in the talk. So for example, a Calabi-Yau background, we have an integral of 3 harmonic forms wedged together with a holomorphic 3-knot form. And in principle, this gives you the coefficients of the trilinear couplings. Now, in any given theory, as I said, we're interested in particular structure. So as examples, in the standard model, for example, we know there's a heavy top quark. So you ask, can I have hierarchies of masses? In supersymmetric theories, famous problems like the mu problem, how do you forbid stuff that's allowed by gauge invariance, forbidding rapid proton decay operators? There's a lot of structure for these couplings that one wants to consider. Of course, this is just the superpotential in the supersymmetric theory. If we were actually doing a realistic vacuum, we've got to run this down to lower energies, break supersymmetry, a bunch of other things will happen. But if you can't control this supersymmetric data, then you don't have much hope of controlling anything else. So here's the topic that I want to explore today. In general, if you take a heterotic theory out of a hat, what you find is that you need to be able to compute these couplings effectively, and you want to say something about general structure of all possible heterotic compactifications. And one observation that you can make quite rapidly in particular examples is that heterotic theories tend to exhibit so-called topological vanishings. That is, if you actually calculate these numbers in a given background, what you find is that there are many more couplings that are forced to be 0 by the choice of compactification geometry than you would expect due to gauge invariance of the theory. So the question that my collaborators from Uppsala and at Virginia Tech and I set out to understand is what geometric effects in the background can lead to these topological vanishings? How do these effects differ? Can they be related? How generic are they? And can these be explained by some sort of hidden symmetry of the theory? So first, I have to tell you a little bit more about these numbers, actually computing superpotential couplings and what goes into that. So how do you actually compute the numbers? Well, the earliest examples that were explored in the literature were Yukawa couplings for so-called standard embeddings of heterotic string theory, in which the gauge bundle and the tangent bundle were chosen to be the same. In these, you have a lot of the power of 2-2 theories instead of 0-2 theories, and you can use mirror symmetry to interpret these numbers as some statement in the dual geometry or mirror geometry, particularly triple intersection numbers in the mirror. However, in general, you have no such in for these numbers. And very early on in the late 80s, early 90s, it was discovered that you could reformulate this question as one essentially of polynomial multiplication. So the integral formulation of these harmonic forms that I mentioned previously can be rephrased as a cup/Uneta product in cohomology, in which you're mapping bundle valued 1 forms of the following type. Now, I've written an expression in terms of harmonic forms. I've now generalized this to a general closed form, but these numbers will differ by a closed piece and can drop out of the integral. So up to overall normalization, which is important and we'll return to, we can say something about the structure of these numbers based on such trilinear products. And basically, there's a lot of cool tools for taking a bundle-valued cohomology group and transforming it into a problem in polynomial multiplication, i.e. Grosvenor basis calculations. So this is intensive, but possible, and you can tackle various problems computationally, and people over the last 15 years have done so, including myself in various contexts. More recently, also different groups were interested in returning to the sort of differential geometry origin of this problem. And in particular, they were interested in looking at simple manifolds defined, Blesniak and collaborators, this was Blesniak, Bookbinder, Candelas, and Lucas, were interested in computing these couplings in heterotic backgrounds defined as complete intersections in products of projective spaces. This could be generalized readily to toric varieties, but this was the simple initial class that they were considering. And what they found is that if you have a simple description of your compactification manifold in terms of some ambient space, then you can effectively, in simple cases, pull back this integral problem to one that is simply defined over that ambient space. Now, the point of this is that you can take forms that are closed on the Calabi-Yau and pull them back to not necessarily closed forms over the ambient space. And here the holomorphic 3 form has a very simple relationship to a delta function current that allows you to actually transform this integral into one that is quite tractable in structure. And the interesting thing is, for simple ambient spaces, you can see structurally that many couplings have to be 0 simply by the form of the ambient space. So as a simple sort of toy bit of intuition, if you have an ambient space that has small dimensional factors in the product, later we'll talk about this in the context of blowups or other things. For example, if you had a P1 factor, you can see that you can only stick sort of so many legs of a differential form into that direction before this must be forced to be 0. So a simple form for the ambient space can affect the form of these trilinear couplings. In this formalism, it's easy to see that some things must be 0, and this is using an ambient space to obtain information of that type. So what my collaborators and I set out to do was to try and understand, can we phrase that in a bit more generality, the types of observations that was just made using differential geometry. And we proved a number of theorems in a recent paper. I'm just going to give one as a rough bit of a flavor for the idea here. We found that the tools of homological algebra, which in general, one should not show one's algebra in talks, including homological algebra, but I will say briefly, the tools of homological algebra allow you to get nice information about the structure of these Uneta products or trilinear products in cohomology very readily from specific descriptions of the bundle in which your forms are valued. That description can involve an ambient space, like the differential geometry approach I just mentioned, or it can be much more general. So in general, what we said is, given any resolution of a bundle, this is a description of your simple bundle over the Calabi-Yau in terms of some data, possibly bundles on an ambient space, possible simpler sheaves, line bundles, abelian gauge fields, anything that's giving you easy information about this. If you can package your bundle in terms of a resolution, then we can filter the bundle valued 1 forms according to the data of that resolution. And specifically, we can come up with vanishing criteria based on the dimensions of cohomology of objects in the resolution, which will tell you which couplings, i.e. which forms living in the bundle valued cohomology can consistently couple to one another. So this is a notion of type, which was generalizing the work of Buchbinder, Candelas, and Lucas, and we come up with some vanishing criteria. In this framework, you can easily see that the differential approach that was obtained previously can be described in terms of a causal resolution of the bundle. So this is describing a vector bundle in terms of a resolution where the curly data here is defined over some ambient space and then is restricted to a Calabi-Yau. My goal today is not to get into the details of this theorem or how we proved it, but rather to point out that there's interesting structure that can be described quite generally about heterotic theories in this context. So in general, this is one example. I gave you a description in terms of an ambient space where you can say something about whether the trilinear couplings must be 0 or not. There are several other effects known. This is not necessarily exhaustive, but several other geometric effects that can force topological vanishing, couplings to be 0 that you didn't necessarily know were going to be. Broadly, these can arise either from the manifold. So I gave you the example of a simple ambient space as one. 2 other effects involve another description of the Calabi-Yau manifold as, for example, as a fibration. And this has dated again for the last 15 years. For manifolds that emit fibration structures, it was well understood that this imposes strong constraints on bundle-valued cohomology and their possible couplings. And we also have data involving the so-called Mumford slope stability of the bundle and Kähler-Kohn substructure. I won't get into the details of this, but simply to say that the vector bundles have to satisfy non-trivial equations of motion, just like the Ricci flatness of Calabi-Yau manifolds. And their ability to satisfy that can lead to massive symmetries that can have an effect in terms of constraining the possible couplings in the theory. What we showed in our paper is that homological algebra tools can also be used to describe these other effects as well. So you have an in for calculating broad classes of topological vanishings. Now, the next question you ask is, who cares, right? Can you actually see some structure? Does this tell you anything about what classes of theories you might want to write down or what types of geometries might be of interest to you? So the first question you can ask is, given diverse geometric origins for topological vanishings, if I have, say, constraints on the couplings due to the description of the manifold in some ambient space or to its description as a fibration, will I get the same data from different geometric origins, the same topological vanishings from different descriptions? And the answer, we explored this in various contexts, is a definitive no. So in general, each distinct description of a geometry can impose different couplings to vanish. And of course, if any one description tells you it's zero, since it's the same theory in different descriptions, that's telling you that many more couplings are zero. So let me give a flavor of just one of those. I mentioned that the elliptic fibration structure or K3 fibration structure of the manifold will impose conditions on the couplings. It has recently been studied by many groups, including myself, James Gray, and our postdocs, Zhengao and Sung-Ju, as well as Body Taylor and his student Huang, that Calabi-Yau threefolds are quite commonly fibered. So how commonly? One has to ask in different contexts, depending on the construction of Calabi-Yaus. But essentially, it is a true statement that almost all known or constructed Calabi-Yau threefolds admit fibration structures. So here is the famous Hodge number plot of Calabi-Yau threefolds and a figure I stole from Waddy's paper, which was from some time ago. This has to be, it can be updated in much more detail now, of the number of Hodge numbers that correspond to fibered manifolds placed over the top. So observation, if you pick a Calabi-Yau manifold from the hat, odds are it's going to be fibered. Observation number two is that if you pick such a generic manifold, in general, we have found from many data sets, they do not admit just one elliptic fibration, they can admit many, order tens, hundreds, thousands, or in one case, actually an infinite number of distinct fibrations. Each of these distinct fibrations can induce topological vanishings of the type I'm mentioning, and the overall conclusion is that in any given description, you are going to have many, many constraints on the couplings. This is going to be extremely restrictive in general, probably too restrictive. So the sort of generic situation is that you will force nearly all of your couplings to be zero. Okay, so now let me change track for a minute and say, with that information in hand, what does then want to do? When you want to perhaps ask, can I use this general topological vanishing to eliminate large classes of theories that I might be interested in, or can I tune towards ones that might have coupling structure that could be relevant? For example, standard model type vacua with a heavy top quark. In that context, then, we need to be able to push the theory further. And with that, I want to turn to the second paper that I mentioned today, which is trying to determine the structure of the low energy potential in as much detail as possible. So I have glossed over in talking about superpotential couplings, I glossed over the fact that the technology as I described it to date could only talk about the couplings up to overall normalization. That is, the matter field Kähler potential for matter fields in heterotic theories is unknown except for very special cases. So structurally, the Yukawa couplings that I mentioned before, these will be derived from 10D terms in the 10D Lagrangian of this type. And crucially, the normalization and coefficients of these terms will depend on the metric over the compact directions, i.e. the Calabi-Yau background, and the choice of gauge connection over the Calabi-Yau. Also, I glossed over using harmonic forms versus general closed forms. Of course, the exact harmonic representatives are also metric dependent. The problem as well of pushing the theory to its limit, one of moduli stabilization, which we've heard lots about in various contexts in this conference already. Again, you may, in order to even find a stable vacuum, also need to know something about the structure of the geometry beyond just its topology. And that leads us to the question, how to determine the metric and connection. So in general, the only current totally general approach, especially for Calabi-Yau threefolds to this problem, is via numeric approximation. Now we're going to hear more about this in the next discussion session, but let me try and set the stage for that briefly. So the state of the art up until very recently is the so-called Donaldson algorithm to try and approximate a Calabi-Yau metric, a Ricci flat metric over a Calabi-Yau threefold. The idea is to use projective embeddings to try and generate simple metrics that can be parametrically tuned to a Ricci flat solution. So simple idea, given any projective manifold, i.e. a Calabi-Yau, we can use global sections of ample line bundles over that manifold to define the Kodaira embedding into some large projective space. The reason that this is an attractive thing to do is that projective spaces have very simple metrics, lots of isometries. The so-called Fubini-Studi metric is well understood as a Kähler metric on a projective space. And once you have a description of your manifold embedded into this simple ambient space, you can then try and restrict this metric down to your Calabi-Yau. Now, what you'll get will, of course, not be Ricci flat, but it is controllable. So in general, if we have a generalized Fubini-Studi metric generated by a choice of some ample line bundle in its global sections, we induce a Hermitian fiber metric on that line bundle over the Calabi-Yau. And it can be shown that the Kähler potentials that you would write down over the Calabi-Yau are in fact dense in the moduli space. And a theorem due to Donaldson, including his definition of a so-called balanced metric, provides a path in moduli space that can lead you to Ricci flatness. Specifically, he showed for each k greater than 1, where this is the twist of the line bundle, a balanced metric, which is not going to define here, but is defined as a fixed point of a T operator, which is iterating this fiber metric on the line bundle. This exists and is unique. As k goes to infinity, this sequence of metric actually converges to the unique Ricci flat metric for the given Kähler class and complex structure. Cool. So 15 odd years ago, various groups, including Mike, who will be leading the discussion session after this, actually worked on implementing this numerically and computing Ricci flat metrics numerically on Calabi-Yau manifolds. This is a computationally intensive task, as I learned when I worked on this some time ago as well. And the question you have to ask is, having generated a big numeric approximation to a Calabi-Yau metric in some particular case, is this accurate enough? The short answer is we don't know, because actually pushing this forward in terms of computing the metric, computing a connection, computing harmonic forms, and actually working out the terms in the 4D theory, for example, in heterotic that I mentioned, has not been run all the way to completion. In addition, moduli dependence of that metric is very difficult to obtain via the Donaldson algorithm. And this, although important in principle, in practice has not led to major new studies of field theories or vacua, simply because of the computational difficulty. So
about 5 more minutes.
Thank you very much. So I'd like to use my last 5 minutes to highlight a different approach to this using machine learning, which was done in collaboration with the people I mentioned earlier. And I'd especially like to flag the work of Fabian and Sven, who both have long programs on machine learning and are the real experts on the art of getting neural networks to do what you want. So we devised a series of goals. We wanted to study supervised learning of moduli dependence of Calabi-Yau metrics using the Donaldson algorithm to generate training data. We used direct learning of moduli dependent Calabi-Yau metrics, both using a metric ansatz such as the Donaldson algorithm and without it. And then perhaps the most significant, we studied the direct learning of metrics associated to SU3 structures with torsion. This is moving beyond the Calabi-Yau case and is the first time numerics of this type has been used in this context. And I'm going to give a brief flavor of these results. I should also mention that there were 2 papers that appeared in very close succession to ours, Douglas, with whom we coordinated, and Jajala shortly afterwards, who did similar things. So briefly, a definition of a Calabi-Yau threefold is as a complex threefold admitting a nowhere vanishing real 2 form and a complex 3 form that satisfy these identities on the top form and are both closed. The metric is related to the 2 form in the obvious way. And for the purposes of this talk, I'm going to be defining everything on the quintic hypersurface with a single complex structure parameter because it's easy to illustrate. So the first I'm going to discuss is direct learning of the Kähler potential. So the balanced metric output by Donaldson's algorithm at a fixed k is not necessarily the most accurate approximation to the Ricci flat metric. The first question, which is one of computational efficiency, is can a neural network do better? So in particular, we're going to use a basic feed-forward neural network, direct learning, to try and minimize a loss function, here designated as a loss sub MA, mange impair, which we are going to try and force the numeric solution towards the Ricci flat one. This is very similar in spirit to work done by Hedrick and Nassar, although we're obtaining moduli-dependent results and using machine learning rather than minimization functions in Mathematica. And what we find is that this actually works surprisingly well, or at least surprising to me. So here I'm showing 2 different results run over different ranges of the complex structure. The basic punchline is that what we find is that the neural network can produce results that are very comparable to Donaldson much, much quicker. So here, for example, this line is the Donaldson algorithm run at an accuracy of k equals 6. And the Donaldson algorithm, I should say, at k equals 12 takes order days or weeks to run, even for the single case of psi equals 0. This network at k equals 6 can take minutes and gives comparable accuracy for a whole range of psi. And we can do better than the Donaldson algorithm at k equals 6. This can be extrapolated. I should say here the shaded ranges are extrapolation in complex structure using these networks. Since I'm almost out of time, let me jump slightly ahead, which is to say that we attempted to direct learn the metric as well. So not using the Donaldson ansatz for the Kähler potential, but just directly learning the metric. The reason that this was useful is that it can be immediately generalized to non-Calabi-Yau cases. And again, this is the first time in the literature that we've been able to sort of distance ourselves numerically from the Kähler framework. The disadvantage of this is that you have to put in by hand, if you're learning the Calabi-Yau metric, that the thing is Kähler and that it's globally consistent. So we do this through the generation of loss functions of this type, where we have to impose the fact that the Kähler form is closed and overlap conditions to guarantee that this globally patches together correctly. What we find is that, again, this works reasonably well. So here we have the overall loss, which is trending downward for a direct learning of the Calabi-Yau metric. And we can play games with what happens if you turn off the Kähler condition or if you turn off the condition for global overlaps. And we find that if you turn off the Kähler condition, the overall error is bad, this doesn't work. But the solution is still trending downward towards something. So the question is, what is it converging towards? And with my last 1 minute, let me just say that the final experiment that we did was to try and learn SU3 structures. So we want to now move beyond the Calabi-Yau geometry. We want to consider situations where we again have a 2 form and a 3 form, but this time with different differential properties. So an SU3 structure can be classified by its torsion classes in this way. And these torsion classes parameterize how far off of closed forms you're running in this case. Specifically, we again were interested in the context of the heterotic string theory, so we're looking for solutions to the Hall-Strominger system. Now, I'm out of time, so rather than going too far over, let me just say, instead of trying to generally solve for some mystery SU3 structure, we don't have existence theorems in this context, and we don't know about the global minima of the functions that we're attempting to optimize. So in this context, we decided to move towards a known analytic solution that was found by Larfors, Lucas, and Ruehle as an SU3 structure solution actually on a topological Calabi-Yau manifold. So although a Calabi-Yau can admit a Ricci flat metric, it can admit other non-Ricci flat solutions. And we used one of these to try and test the neural networks and see if it worked. So this is particularly important because such metrics have no analog of Yau's theorem. Again, we need to know that we're actually seeing something that isn't a numeric artifact. So let me just go straight to the result. We find, again, that this proves to be quite successful. Exactly how successful we can talk about in the context of the discussion session immediately after this. But what we find is that running this over the topological quintic, we can find that we converge to the known solution to high accuracy. We can actually test this against the known solution point by point over the manifold and find a strong correspondence. So this, as from the point of view of the neural network, there is nothing special about the Kähler geometry that we're tied to initially in the Calabi-Yau case. We can generalize to non-Kähler very readily. The catch in this context, we considered the Strominger system because we are still using a lot of tools from complex geometry. And of course, it would be interesting to drop those as well. So since I'm out of time, let me try and summarize what this was a very brief tour of, hopefully. The point I wanted to try and convey in this talk is that progress is being made in several aspects in terms of broad-scale characterization of generic features of vacua. There are many other questions like the topological vanishings and couplings that are being actively studied that I didn't have time to talk about today. But the general broad brushstrokes that I hope to convey are that there are properties of this theory that you can state at a very rough scale that can help you filter through large numbers of possible geometries. And we have come up with consistent frameworks that very readily allow you to access that information. In the case of these topological vanishings that I mentioned, these constraints are ubiquitous. There are, of course, lots of open questions. Can you apply these same techniques to higher order, to non-perturbative contributions to superpotential? The answer is we think so in various contexts. That's for the future. You can ask what happens for dual theories, for example, F theory. Can this be described as a hidden symmetry? These vanishings are very similar in spirit, though not in letter, to certain recent swampland conjectures. And more broadly, when you want to actually push the theory through to a detailed understanding of the couplings, control of the metric is necessary to specify the 4D theory in enough detail. And what we are experimenting with, and we'll have a chance to talk about in the next discussion session in more detail, is that machine learning techniques can provide a powerful new tool in terms of addressing some of these questions that have been serious obstacles over the last 15 years. In particular, we provided the first numeric approximations to SU3 structure metrics, and there are a variety of open questions. For example, what other aspects of the 4D theory that are metric dependent do we want to try and calculate, moduli stabilization, and hopefully we can turn to many of these in the next session. So I apologize for going a minute or two over, and thank you very much for your attention.
Great, thanks very much, Lara. So if you have questions, please raise your hand. There is a question from Chris Krylova in the chat, which was actually about 3 or 4 slides ago, Lara, I think when you first had a graph of the machine learning. Chris asked, what is the efficiency of your loss function, i.e. the percentage of certainty that your result is correct? So it's probably back about 4 slides.
So yeah, to answer that, so the loss here, we're starting out. So there's a variety of different loss functions that we're optimizing. Actually, let me go back one more here. So this loss function, this is for the Calabi-Yau case. So this, in the case of the Calabi-Yau metric heading towards Ricci flat, the axes here, this is about 10 to the minus 1. This is getting very good at low complex structure, and of course, in extrapolation, worse at high complex structure. Various games can be played with this. These numeric approximations, all of them are worse at higher complex structure. But yeah, this is the basic structure. The width of these plots here is the range over the complex component of the complex structure that we're running over. I don't know if that answers your question.
Thanks, Laura.
Yes,
So we have a few questions, hands raised. Can we go to the node from the IAS?
Sure.
In the real world, we'd sometimes like to have very small but not zero Yukawa couplings. For example, to get the electron and light quark masses. So with that in mind, I wonder whether you've tried to figure out if worldsheet instanton corrections turn your vanishing heterotic string couplings into small ones.
That is exactly the hope, right? So just as you said, I mean, and this has been a hope, I should say, I'm sure you know, for quite a while, is that you can kill off perturbative couplings and then attempt to regrow them non-perturbatively at an appropriate scale. So I think we have thought about that indeed, and in various contexts, people have tried to push this quite far. I should say that a lot of progress has been made in calculating those non-perturbative corrections recently to greater accuracy. So indeed, in a given situation, that would be a promising avenue and an explanation for small numbers. In practice, though, of course, we have to have a fully stable vacuum with the right massless spectrum, and we don't have that yet. So structurally, the short answer is I'm definitely thinking about non-perturbative corrections, and then what types of constraints you can say even at a broad geometric level for those as well. But
thanks.
Great. So we're short on time, but we have time for maybe 1 or 2 more questions. So Miriam has a question.
Yes, actually, it's I have more of a comment, and one is related to the one that Ed mentioned. I do want to mention that, sort of interestingly enough, in the globally consistent model that has MSSM spectrum of Bouchard and Donaghy, surprisingly enough, in our work, the R parity violating couplings were indeed 0, but also the lepton couplings were 0. So that's exactly what quantum cohomology should start playing a role in modifying these classical values. And there is actually concrete work more on a toy models done by Katz and Donaghy and company.
I completely agree. Very, very interesting structure, and exactly of the spirit of the previous question that you guys found. I'll add there are many now many other vacua, heterotic vacua with sort of on the similar standing of control of couplings and properties of the type you mentioned. The question then is, if you need further detail, yeah, how do you filter that efficiently and so on? So, but excellent point.
Thank you.
Great. Okay, so we're just about out of time, maybe 30 seconds for Ivano Basile.
Okay, thank you. I'll be very brief. So I was wondering, regarding extending your methods to more general geometries, right? Wouldn't there be, in general, also the constraint that the metric solve the background field equations, at least to leading order?
Sorry, so you mean beyond the Ricci flatness condition, or you mean the,
exactly.
the equation? Absolutely.
Well, even the, okay, yeah. Say beyond the Ricci flatness, yeah.
Yes, indeed. So, I mean, one could ask about high order structure. I mean, certainly in the case that I was referring to, the SU3 structure, the point is that that is solving the equations of motion for the heterotic string. So the Hull-Strominger solution, to leading order in the theory is the full solution to the equations of motion and specifying constraints on torsion classes. So the examples that we're looking at were of that type, and those are consistent. Yeah, one could ask for different setups in different, compactifications of other string theories or M theory. And from the machine learning point of view, of course, this is all totally generalizable. So doing this for G2, for M theory, as long as you have conditions on the torsion classes, you can do many different types of G structures.
Right. Thank you.
Okay, great. Thanks very much. So let's thank Lara again. Lara, if you could stop sharing your screen so we can switch speakers. I had a couple of questions, but I'll take those offline. So thanks again. And moving on to Mike and Fabian, who will run the next session. So Mike or Fabian, do you want to share your screen?
I have to have it enabled. I switched computers. So I'm not sure.
I have the capacity to do that.
Nathan, Nathan,
you want as a co-host?
Michael co-host. I think I cannot. Only Nathan can. Yeah.
Okay, I should be able to now.
Okay, great. And Mike and Fabian, I think you guys are moderating your own thing, so I'll just let you take control of everything. And note that you're starting about 5 minutes late, so feel free to run 5 minutes plus over.
Right, thanks.
Yeah, so let me just remind people. So you have 20 minutes. And for those that were not here in the previous session, let me remind that we are encouraging new people that have not spoken yet to not be shy and ask questions and participate so that we can all see each other. So yeah, I'll pass it over to the 20 minutes of introduction by Mike and Fabian.
Thanks. So I'll give some background and talk about problems from machine learning that physicists have contributed to. And Fabian will continue focusing on how machine learning can help physics. So the field has really changed a lot, just as every active field of science, string theory. And just to illustrate that, I'll talk a bit about my introduction to this. So I went to Caltech, in fact, not to study string theory because this was 1983, but to work with John Hopfield, who, as some of you will know, proposed one of the early neural network models, which is still used in machine learning. And so I've followed the field and seen many of these changes over the years. So let me start, because again, it's more physicsy than many of the other things in machine learning, with this Hopfield model. And you can see a Hamiltonian energy, and basically it's a spin glass. So the S's are two valued spins here. Jij is a set of independently adjustable couplings. So there's no symmetry, it's a disordered system. And Hopfield's idea was to use this as a model of memory, to postulate a dynamics rather than a statistical interpretation, where if you start with a given configuration of spins, the system would be attracted to one of a few memories, special configurations. And so it's sort of associative memory. And it's easy to see that if you take a sum of terms, memory, tensor product memory, the second line here, then the configuration that is close to one of the given memories, the term that has the largest dot product with that memory will dominate and attract it to that. And then a good deal of work at the time showed that this is fairly general, but there's a limit on the number of memories, in fact, linear in the number of spins. So there were many directions in which physicists and other scientists got into these problems. It was back then the field called natural computing, this whole topic of computational schemes inspired by one or another natural system. And perhaps the most famous and probably the most important of these early developments was what's called the perceptron originally, and now is, of course, the feed-forward network. And let me, again, this is not any kind of history. This is more from my own point of view, but just to give a sense. So this early period, people, physicists were some of the significant contributions to neural networks. And there were important empirical work, such as the first successes with convolutional neural networks date back to the late 80s, Jan LeCun's net for digit recognition. But this was still the period when symbolic AI and expert systems was the dominant mode of thought. But that would change in what people in that field often refer to as the AI winter of 1990s. And there was not much sense of what would work, but what was gradually realized over the 90s, I think, is that machine learning, although you can draw on physics and many other sciences, is most naturally a subfield of statistics. And that, again, that's kind of taken for granted now, but that was a recognition that various people had to make. And in our field, one of the very early people to get into this and write such papers was Vijay Balasubramanian. So you can look at
that example as a how those sorts of connections were made. I'll come back to this topic of phase transitions and combinatorial optimization, which was a very direct influence of physics. And having this type of foundation on statistics, one could then be systematic and decide, how did machine learning, what were problems it was adapted to, and were very simple models at first. And really, it was the 2010s, of course, the famous AlexNet solving the ImageNet problem in 2012, and most famously of all, AlphaGo, GPT-2, to the point where it's clear great breakthroughs have been made, and they clearly have more scope that leading to this great excitement. But again, as in many fields of science, there's this almost universal phenomenon that after the initial ideas are formulated, they tend to go through this significant period of being unfashionable because it's just very hard for a variety of reasons to realize the potential. And in the case of machine learning, it was as much the need for much more powerful hardware than as anything else. Okay, so now let me, for the benefit of people that haven't seen this or just to set terms, here's a few of the standard machine learning tasks. So supervised learning is this, the basic example might be classify images into, label them as, this is a cat, this is a dog, and so forth. And then the computational and mathematical version of that is that what you're basically doing is fitting a function. The image is encoded in pixels. There's a big vector of intensities. And now you have a function which tells you, either what class or more commonly, what is the probability the image is in a certain class. And you need to fit this function given a set of examples and hope that it generalizes. But again, any problem involving function fitting, this technology can do something for you. And of course, a great number of problems can be phrased in that way. There's probabilistic modeling, which in the machine learning literature tends to be called unsupervised or self-supervised learning, where there's only X's, there's no Y's, there's some sort of input distribution, and you're just trying to learn the distribution. And this obviously has many, in fact, very clear scientific applications. One that a number of people have developed is to just say, well, what's the most straightforward and general analysis of collider data? Well, we have an event that distributes energy in various tracks and the like, and there's a probability distribution that in principle we can compute given the standard model of the detector simulator, and then we can compare that with the observed probability distribution. And of course, these are incredibly complicated distributions, so just modeling it is a almost necessary ingredient of making that comparison. Reinforcement learning. Fabian will get more into this. This uses these other things and is distinguished by the fact that you don't get immediate reward, but you get some reward. So when you play a game, you find out at the end of the game, did you win or lose? And then here I've reviewed the feed-forward network in a formal language. And maybe the point here is that it is a very natural structure that the original engineering definitions might or might not make clear. You have a sequence of alternating linear maps, act by a matrix on a vector, which I labeled W, and then a sequence of nonlinear maps, which I've labeled theta, acting on each component of the vector. And this ReLU function is almost the simplest thing you could imagine. And it works just, in fact, in some ways better than more complicated functions like tanh. And then even two layers of this, W, theta, W, if you have a high enough dimension intermediate space, this is a universal function approximator, but it's advantageous to allow more layers and get simpler descriptions of the functions it's trying to learn. So the idea is that just adjusting the coefficients of these matrices W gives us this huge class of functions. And at this point, there's again, vast amount of hardware, software for doing that type of function fitting. And then just to complete the story, for supervised learning, we would define some loss function that tells us how close or what's the error compared to the how good the function is for our purpose. So it might be classification, and we would talk about how well the function models the correct classification that we're given. And then we just do gradient descent, say some numerical optimization within that class of functions of this loss function. And then of course, that's, again, it has this nice, simple conceptual starting point, and then one could easily give a course or 2 courses on this. And the physicists are already contributing quite a bit at this level. So just as an example, work of Miranda Chang and collaborators recently, the convolutional net is good for translationally invariant input distributions. But of course, you could have many other group operations and try to define distributions and networks adapted to those. Okay, so what does this have to do with physics? Okay, well, I'm going to go in both directions and tell you first, well, what are some of the questions that people do machine learning think are the essential questions? And so the most important that everybody would agree is, how do these models generalize? So if we have a function that tells us for an image what class is it, we've only given this negligible subset of the possible images. And the whole point is that it can classify images that it hasn't seen before. And in the statistics, there was this kind of paradigm for answering this, which I'll say a bit more about, that you have a model that encodes prior information, say, about the spaces of images. But one of the great lessons of these recent successes is that you do better often by not putting in all these priors and using these very general models, such as the feed-forward network, which knows nothing, or the convolutional net, which only knows translational invariance. And then that is, in general, often more powerful than these models that know something. And so there clearly is some sort of more general mechanisms that are really not well understood. Now, there's a more specific paradox if you want something, a little better defined. The successful models have very large numbers of weights, these matrix elements, W, and often so many that you can completely fit the training set. Now, if you've taken any course in statistics, you know that that's a bad thing to do, that if you can fit all your data, then you're overfitting, you're fitting all the noise, and you're not going to generalize. But that's not what happens here. And this has been sharpened, this paradox, to what in recent literature is called the double descent curve. So this is considered to be a central thing to explain. So if from your statistics class, you might recognize the left-hand graph here, which is the number of parameters basically on the x-axis and the error of the system on the y-axis. But the modern picture that comes out of machine learning is on the right-hand side, where there's a point exactly where you get enough parameters to fit all the data. And then as you add more and more parameters, you do even better. So this interpolation threshold. So the curve goes down twice. And you often work in the second branch where it's going down the second time. And so how does that happen? So that's a much more crisp theoretical problem. So so I'll give 2 or 3 more, and then I'll give it to Fabian. So how do you do data, theory in a data-driven field? Well, you tend to have to make a synthetic data. And one way of doing that is to use an analogy to a disordered systems. And that leads fairly directly to the idea of phase transitions in these theories. And the original hot field model had a phase transition where you put in enough memories. And then this is something you can study using the replica method and other physics methods. So this has been a point where physicists really contributed even the conceptual framework for understanding phase transitions. There's a natural method from a theoretical point of view called teacher-student, where you have one model that produces the data. Say you give it some X and it puts out the Y, and then you study the problem of how does the second model learn to fit the thing produced by the first method. And again, there's a lot of statistical physics which is directly applicable. Random matrix theory is one of our go-to tools, which has been much used here. And in fact, I'll recommend a work that derives the double descent curve in an interesting class of models using free probability of Adlewing and Pennington. Okay, so let me say a little bit about what machine learning will do for physics, and Fabian will say much more. So, again, on the 30, 40-year time scale, all bets are off. Life may be revolutionized, but on the decade scale, it's clear that machine learning for science will do a lot of useful things. But what about conceptual influences? Okay, my own following this field over my career had many influences on me, and one was this interest in statistics of vacuum. It came out of, in part, studying statistics for machine learning. There's statistical concepts that you can use to study physical models, and especially spaces of quantum field theories. Again, Vijay Balasubramanian has written many works in that direction. You could try to make direct physical interpretations of architectures. There's an interesting paper of Akutagawa et al. That relates the feed-forward network to renormalization group in the ADS and gets an interesting model of hadronic structure. I've been looking at another application, which is a very machine learning thing. I'll leave this slide for your later reference, but there's, I think, a lot of reasons to think that mathematical research will be far easier to perform within a decade. The technologies that, just as we use symbolic math quite often now, we'll be able to do many more things in terms of verifying and proving theorems. And finally, fundamental roles of physics in computation. And again, my interest in this was rekindled by Scott Aronson's 2005 thesis, basically about sharpening the point that physical systems can't do NP-hard computations efficiently. And of course, complexity theory in physics has become much more popular in recent years. And I think this field of applying it to get new insights into cosmology is a very interesting start that I've made in related papers of Curry, Alexander et al. Recently, that if you try to think of the vacuum selection not as say eternal inflation, but as non-equilibrium process and perhaps a computational process, you get many, many different insights that I think will be important. So with that, I'll let you go, Fabian. Let me, there.
Let's thank Michael while Fabian sets up the share screen. Yeah,
okay. I hope you can hear me and you can see my slides.
Yes, we can.
Okay, good. So let me go ahead with the second part. So the question I want to ask here is, are AI techniques, or I will focus on neural networks, are they appropriate tools for string theory? After all, as Mike just discussed, neural networks are just sort of a combination of affine transformation and nonlinear functions. They are universal approximators, so they can, in theory, learn any function, which can be a bad thing. I mean, you're sure they can learn the function you're interested in, but they can learn arbitrarily many other functions you're not interested in. So it's a question of what do they learn in practice, and then what tasks are they good at? One thing that time and again they have proven to be good at, and it's not really understood why, is they're very good in pattern recognition. So they're used in self-driving cars, for example, or they're used to play Go and chess, which probably also requires some sort of pattern recognition under the hood. So in string theory, there are also patterns in the solutions. For example, here, these are the solutions in the of some flux vector. And you might hope that it can pick up some of these patterns and help us find solutions. The second thing that they are very good at is natural language processing. And again, in physics or in string theory, these appear as discrete non-abelian groups where you have word problems that you're trying to solve, shortest word problems, for example. And they show up in, for example, grades when you study knot theory. And thirdly, there is this thing that Mike talked about, the double descent. So it devises common Lorentz statistics that they generalize well, and they do not overfit, even though you have included many, many parameters. So you can just vastly overparameterize the system and you get a very good result. And there are many ways of applying sort of these three properties. I will be only talking about two because I don't have so much time. So one is to use it for conjecture generation. So using the fact that it generalizes very well, and to try to learn a map between quantities which are not known to have any relation. If the neural network performs very well, so that it finds a map that maps these far above the expectation, if it was doing something randomly, you might conjecture that these things are linked, and then you could hope to go and improve it. And this has been done in, for example, applications to knot theory, toric geometry, line bundle cohomology, and Bruno theory, as Miriam briefly mentioned, and many more aspects of mathematics, especially by Yang Ruehle. And a second, maybe more classical approach or application is optimization and regression. So you're just trying to use this to find solutions for system of equations. And has been used for searches in string vector. And we had a talk by Mariana, which didn't use a neural network or an AI, but a genetic algorithm in order to find solutions. And then, as Lara mentioned, it has been used in solving partial differential equations for Calabi-Yau and SO3 structure metrics. So let me just briefly give you 3 examples for what I just said. The first one is pattern recognition Diophantine equations. So Diophantine equations appear ubiquitously in string theory because you have topological data and flux quantization and so on. However, asking whether an arbitrarily given Diophantine equation has a solution, let alone finding one, is actually an undecidable problem. So this is in some sense from computational complexity point of view as hard a problem as it gets. However, you might think that the Diophantine equations come out of string theory are not an arbitrary Diophantine equation, but they have some structure which are inherited from the stringent mathematical consistency conditions. So what was done in the study is there was a set up a game in reinforcement learning, which had targeted solving a particular set of coupled Diophantine equations, which were related to flux vector of type 2 orientifolds, and sort of hoping that the neural network can find some pattern because it's good at pattern recognition. And what was found there is that indeed it can rediscover a human-derived solution strategy for this coupled Diophantine system. But if you let it do whatever it wants, it also came up with new, more efficient strategies of solving the system. And as a second example for conjecture generation and natural language processing, I want to mention knot theory. So for conjecture generation, so what Hughes did is he used basic knot invariants and then tried to see whether you can predict quasi-positivity, slice genus, or the Osotsavo tau invariants using these. And what Vishnu Jejala and collaborators did was they fed the Jones polynomial and we're trying to see whether you can map onto the hyperbolic knot volume. And this actually performed pretty well. In the second part, what we did is we used reinforcement learning in order to get a provably correct result from machine learning. So we set up again a game, which was to find the unknot. You give a braid that represents a knot, and you're asking, can you reduce the number of crossings to 0 in this braid, essentially? And the neural network will then give you a sequence of randomized moves so that if you had the string physically in front of you, you could do these types of moves and you could physically unknot the string. So you can prove that a given knot is the unknot. And we found that it performed very well up to 100 crossings. As a third example, I want to talk about interpolation and Calabi-Yau metrics. So for the purpose here, we just think of the Calabi-Yau metric as a map from K-logs and complex structure moduli space and a point on the Calabi-Yau into a permission D by D matrix. And so we parameterize this map as a neural network and subject it to the condition that it's complex scalar and Ricci flat, which means it solves a Morse-Ampere type differential equation. And we have seen the talk by Gonzalo where they also use it for, they also propose to use a neural network to study some other sort of geometric background. Then you can use these expressions for the moduli dependent metric, as Lara explained, for Yukawa couplings to compute a massive string excitation, check Swampland conjecture for the SYZ conjecture, and so on. So Irene in her talk really fully summarized Swampland conjectures, and one of the conjectures was that the mass goes exponentially with geodesic distance. So what we did is we used this neural network, computed the massive string spectrum as a function of the geodesic distance. So we computed periods, computed the geodesics in complex structure moduli space, and we found that the value with which the tau becomes exponentially light is indeed given by this 1 over square root 6, or it's very close to this 1 over square root 6 bound while satisfying it. And we also made this interesting observation that if you look at these different masses as a function of the complex structure, we found that there's a degeneracy in the system, which has to do with a symmetry that's there. And we found that irreducible representations under the symmetry group, if they're in small irreducible representations, they become lighter as you make the complex structure larger, as you move in complex structure space, and others become more heavy. And the ones that become more heavy are the ones that have a higher irrep, that transform in a higher irrep of the symmetry group, which is very interesting, and I would like to understand why that is. So let me summarize and outline future directions, also to form a basis for the discussion. So one big area of application is to search for string solutions or to use adversarial training in order to delineate the swampland landscape boundary, which is what Mariana and her group did. They sort of tried to incentivize their algorithm to go as closely to the tadpole as possible. So you could imagine finding, if they had found a counterexample, this would have sort of moved the boundary of the swarm length further away, or would have expanded the landscape boundary. You can hope to get insights from machine learning where symbolic methods fail or just are not available, such as solving PDEs or equations of motions. For any background, as Lara said, you can do this for reduced holonomy or for special structure manifolds. I briefly talked about computing massive strings spectrum, and it also has applications in knot theory. And then there are, of course, many other applications which I didn't even have time to cover. Random matrix theory, SYK, or JT gravity. We had this nice talk by Jeff, where he had these graphs showing up in his SYK batteries. And one might wonder whether graph neural networks can help study this. Then there's mirror and tensor networks, quantum information, numerical bootstrap, and integrability. So these are things that are, to the best of my knowledge, already being pursued. So to go into this discussion, let me end with open questions and speculations. So one question we can ask is, from a particular method you're applying, if it works or if it fails, can you infer something about the pattern that underlies the problem? So if they're good at pattern recognition, for example, and it fails, maybe this means there is no pattern to the solution, to underlying this the problem at hand. Then there are questions that have to do with computational complexity, asking whether approximate but fast results are acceptable. And this maybe hinges at the fact of whether or not, if the neural network gives you an answer, can you actually check that the answer is correct? And this has to do with which complexity class the problem is in. Or you might ask, can I even approximate the problem fast? If you cannot even approximate it fast, then there's no hope that neural networks can do it, because they're just bound by computational complexity as any other thing. And lastly, if you find an approximate solution, what do you require in order to believe that it is a solution? If you're doing this, for example, for cases where you don't have existence proofs. And then the last ones are maybe more vague or philosophical. So if consistent string theories are governed by Diophantine equations, which are undecidable, or any other problems which are highly complex in the computational sense, how did the universe actually manage to solve them? And asking this question, does it teach us anything about vacuum selection in string theory? And coming back to theorem proving that Mike very briefly mentioned, so let's assume that in the very distant future, an advanced AI was able to prove a theorem such that no human can go through or even understand the proof. Would we accept it, or would we even consider it a proof? That's all I wanted to say, and now I would like to open up for the discussion.
Thank you very much. Let's all
leave the slide. How much should I stop sharing?
You can. I suggest something. Please don't stop sharing yet. Okay, don't stop sharing. So let's thank Fabian and Mike for a very nice introduction. So now let me suggest, while we start the discussion, that people look at the questions and memorize them, but then we will stop sharing. I think it is helpful for a few seconds, but not for long. So please have a look and do raise your hand. And I would suggest maybe Jeff could say some words if he's around. He was not yet put on the spotlight in these discussions. Or I also see a contribution in the chat from Sergei Gukov. Okay, maybe they are not here.
Well, I'm here, but I don't have much to add. And yeah, thank you, Michael. Thank you, Fabian, for a very nice summary.
Okay, I encourage people to not to be shy. No one is going to blame you for not being an expert in machine learning.
So. Eva has her hand up.
Ah, yes, very good. Yeah.
All right, thanks, Mike. The problem is I spoke a lot last week, so they're trying to let new people contribute. Thanks a lot for the really interesting introductions and questions. I guess very quickly on this question of what do you do with an approximate solution, one thing that we played with recently is when it comes to these problems of the landscape and trying to solve the related PDEs, another thing that you can do is define a functional version of the slow roll parameters and treat that as your loss function. And then as you descend the loss function, you're actually happy getting, epsilon and eta, the slow roll parameters to be small, but not literally zero. It's of physical interest. So treating that as your objective function is already interesting. The other thing I wanted to say quickly is, and Mike knows this, but not probably most people, one way that we can use physics to approach AI is, or to try and help with it, is in the optimization process. So stochastic gradient descent is like friction dominated motion. There are generalizations of that involve momentum. But in the world of descending cosmological landscapes, we have found other kinds of dynamics that are really qualitatively and quantitatively different. In that subject, they're called P of X models. An example is dBi inflation. And so the slogan here is BI for AI, where what you do is you take the square root BI Born-Infeld action, and you make the speed limit such that it causes the motion in the spate of weights and biases to go to zero velocity when the speed limit is the loss function itself. So that is, it flies around according to the standard relativistic dynamics, but only stops when it should, as you reach the minimum of the loss function. And we are finding that works better in some well-definable circumstances, but we're trying to understand what people practically want from their optimizers, like what the specifications are that we should focus on. Is it minimizing the time spent optimizing the hyperparameters? Is it just solving some problem that no other can solve? And we found some examples like that. What should we, if one is trying to use physics to design the optimization procedure and improve it, what are people looking for? What are the criteria to aim for, aside from just going faster or solving some problem that the others like Adam don't?
Well, the deepest thing people are looking for is the quality of whether a model generalizes. Depends on there's like a lot of it's a very the loss function is non-convex. There are lots of minima. Some generalize better than others. People don't understand that very deeply. So any kind of evidence, data insight is useful. But I mean, one fairly well commonly held idea is that if shallow or broader minima, so if low masses in physics language, a broader minimum will generalize better, and that actually just comes out of Bayesian statistics, and so that's a thing you can look for. And then people of machine learning have algorithms that try to do that, and they're not that efficient. So maybe there's physics-inspired way of finding a broad minimum.
That's great, thanks. I mean, what I was referring to was indeed very non-convex functions. So this approach flies over the barriers for sort of obvious intuitive physical reasons. Thanks a lot.
Maybe Sven, let me remind people, if you are participating, turning your camera on makes it for a nicer gallery view. So Sven, please.
Yeah, thanks. Thanks a lot for the talks. Also in spirit of what Igor was saying. So one comment to add, I think, to this discussion is that there's a whole subfield of deep learning, which is geometric deep learning, which kind of unifies and gives an understanding of why certain architectures are working. And this, I think, beautifully plays into the role of how, which symmetries we are using. And so that's, a lot of, interplay in terms of like building networks which obey these symmetries. And then there's a subsequent question, which also then comes into the play, is to actually find the underlying symmetries, because finding them for machine learning is very useful, because obviously if one knows about symmetries in the problem, one can then design architectures in the right way and get more efficient results for all sorts of problems. And that's very deep at the heart of what we also do in string theory a lot of the time, finding the underlying symmetries. And so that's another direction we are exploring in some sense with various works.
Maybe let me pass to Jeff and then Nathan, and then I will try to put some people on the spotlight from the chat again, so you are warned. Jeff.
Thanks, Pedro. Just to expand on the point that I was making in the
chat, it was not so much that, so I don't really have any insight into applications to GR, but we're together with a student of mine and Daria Rosa, who's my collaborator on that quantum batteries, quantum many-body problem program. So we were trying to understand the ergodic MBL transition in these quantum many-body problems put on graphs, and as Fabian pointed out, graph neural networks are a great way to explore this space. And one of the things that we've been trying to do is, I guess what Mike was talking about with this student-teacher system, where you can have cross-learning, where you can train a network on a particular problem, like if you've got a kid trying to learn to walk and then you learn to run, those are two different sets of things, but learning to do the one gives you information and insight into how to do the other thing. So we're trying to use a neural network trained on a really simple, let's say, Heisenberg's spin chain with nearest neighbor interactions, and then tweak the Hamiltonian so you can have next to nearest neighbor interactions, or even go to higher order interactions, and see if the same network trained on the simple system can learn the many-body localization transition, the mobility edge, without retraining the network. So that's some of the things that we're thinking about in that context.
Nathan?
So I want to ask maybe Michael and Fabian to try to extrapolate. So Michael started already, but suppose in 5-10 years, I assume some areas of study are going to be wiped out by machine learning. Like we have a translator who I think will not have a job in 5 or 10 years. What areas of physics do you think will be most affected by this? And should students learn this and when they take physics classes? And
yeah, I mean, I think physics deployment is pretty safe, for the next 10 years. I think the obvious answer is data analysis. There are all these kind of special purpose things that physicists and scientists developed over the years. And then in some cases, there are special cases of much more general techniques, or there's a general implementation that can do this much better. I mean, there are many examples in our field, or at least in particle physics. Work of Jesse Taylor is a good example, where a lot of the custom statistics for describing jets and collider events are actually special cases of things that if you talk about just statistics of energy distributions, the computer can learn itself. So data analysis. And then in other fields, and I would like to see more of it here, of course, there's this, huge excitement. And I mean, again, if you ask a machine learning specialist, our problems are very fringe, and what they want to do is help people discover drugs. They want to take these huge databases of drug activity or protein folding or this or that and discover new drugs. And, again, that clearly will revolutionize many areas of science, and to the extent that we can make our problems as well defined as the problems in quantum chemistry, say, we will share in that. I mean, that myself is how I like to see string phenomenology proceeding. We may or may not be able to compare with real world data, but we can certainly ask sharp questions that machine learning will help us answer in great generality.
Yeah, I agree with Mike here. So us as string theorists, we are probably safe, but I would still say that it doesn't hurt learning this. So there are techniques that are, there are questions, for example, the massive string spectrum, where I don't see any way of answering this in the near future. We need a Calabi-Yau metric, and there has been great progress in Calabi-Yau two-folds, for example. So we have an analytic solution for this, but this sort of relies on hyperkähler structure that you have on K3 manifolds, and so they don't generalize to Calabi-Yau 3 manifolds, or even if you're interested in just this much more broader class of compactification geometries where you don't have anything like the Calabi-Yau theorem. I think these are really places where you can sort of get inspired by applying machine learning tools, or any tools that help you go beyond beyond the case where you have an analytic situation and you can come up with conjectures, or you can just see what's happening, like, for example, reproducing this 1 over square root 6 bound that Igor was introducing, or then observing this interesting, and to my, at least for me, surprising correlation between the degeneracy of a symmetry of the Calabi-Yau space and the spectrum, because one can be computed very, very easily, and one is inaccessible without neural networks. So I think it would be interesting to understand things like this better, so it can serve as input of things you want to then study theoretically better.
Thanks.
So I would suggest maybe again randomly from the chat, maybe Ning Bao and then Lottie Taylor after. Again, I want to try to encourage new people to enter the discussion, but I don't know if Ning Bao is interested. So 1 second. Let's move to Lottie first, and
Sure.
okay.
So yeah,
Lottie and then
I just
Jeff
wanted to
will
poke for a second at one. Sorry, should I go ahead, Pedro?
Yeah, please go. Please
Okay.
go.
I just wanted to poke for a second at one of the questions that Fabian put up on his last slide, and maybe see what Mike and Fabian and others have to say about that. So one of the questions, if I remember correctly, Fabian, was, so in many cases, solutions of string theory are described by systems of Diophantine equations. And you said, okay, if that's true, how does string theory solve those? And I'm not sure I feel like that's the right way to think about it. If it was a dynamical equation, right? If we were talking about a differential time development equation and we were asking, how does string theory manage to solve, or how does physics manage to, how do fluids solve the Navier-Stokes equation? Then there's a real physics question there, because you have to figure out how the dynamics occurs in the way that accords with that. But I think of these Diophantine equations as simply discrete equations that must be satisfied by the proper solutions, but not something that the physics in some sense has to learn how to satisfy. It just is a characterization of the solutions rather than something that some dynamical mechanism has to solve. So I don't know if either of you have any comment on that. Maybe this dates back, Mike, to some of your work of a number of years back on back.
No, I do. I'll let Fabian speak first if he wants to reply, and then I do have.
Yeah, I can maybe just elaborate what I meant by it. So in principle, I agree with what you said. If it's a question of complexity, so if you might just ask, so how do you, if a problem is very complex, how do I find, how do I solve it? In the case of Diophantine equations is a bit different in my regard, because it's not the, I mean, it's really undecidable. So, provocatively, you might say if the system at hand was undecidable, also the universe couldn't have solved it. So the question would then be: are all equations that we get from string theory actually decidable Diophantine equations? And then sort of having the different solutions then is a question of sort of dynamically finding or hopping between the different configurations, different fluxes, and so on. But there's this fundamental difference between questions that are just hard to solve or questions that cannot be solved at all.
But just to follow through for 1 second before Mike speaks. So even if the equations are impossible to solve in principle for some general class, the fact that they're characterizations of the string theory that, or whatever world we live in, or of solutions to string theory, means that they're features of solutions rather than that the solutions in some sense need to solve the equations. That to me doesn't seem very different, but maybe Mike, you have something.
So you would say that anthropically, or for whatever reason, string theory is bound to give you Diophantine equations that have that are decidable.
I'll continue and say that I certainly agree. I think it's really the physical dynamics in the context where whatever dynamics is generating solutions is relevant is a non-equilibrium, and that's the case where you really care what the dynamics is. And the type of Diophantine equations we're talking about are, I agree, they're generally not dynamical. And there's a lot you can say about again, much more well-known established physics problems about if you look at the dynamics, you find that the physics can't solve a NPR problem, and there's a lot of Scott Aronson wrote a very good paper about that, which I recommend to people back from 2005, and so I do think that I mean any kind of string cosmology is very exploratory at this point, given what we know about the solutions, the landscape, the dynamics. I mean, it's still can be inspiring and help suggest more interesting questions. And I think again, I would recommend the second paper that I wrote with Denaf, Green, Zukowski, as my thoughts about this, that there really are pretty good reasons to think, from at least the picture we have of string cosmology and eternal inflation that we have now is valid, that that's really not what describes the actual quantum cosmology, and that there is something non-equilibrium about the real quantum cosmology. And the basic argument is just that the eternal inflation is so inefficient and seems to be dominated by configurations that are just so different than anything that we need to describe our universe. And again, I refer you to the paper for more well-defined, well-put versions of that argument. But I think this question of what are idealized but at least well-motivated non-equilibrium pictures of cosmology that we could build on is a very good one. And again, our paper, Curry, Alexander, et al., I think this is an area I would suggest people look at.
Let me see if someone is waving to discuss this type of topic. Okay, Jeff.
So just very quickly, there's kind of two sides to this story, right? There's the one side which is applying machine learning algorithms to physics problems, and then there's the other side, which is asking the question, why do these machine learning algorithms and statistical learning in general, deep learning, work so well? And it seems like, if we're asking about physicists having jobs after 10 years, if machines are doing everything, one of the things that it looks like there's a lot of development happening right now, which is trying to understand why these deep learning algorithms work, using, for example, renormalization groups, and something I pointed out in the chat that Eva raised actually is that Dan Roberts has a forthcoming book on deep learning that's very accessible to physicists. I think it's written in a language that we're all familiar with. It starts off with Gaussian integral and goes on from there. And there, the aim is really to try and understand why these algorithms work in a far deeper way than just, well, it's a computer science algorithm.
Maybe before turning back to Mike and Fabian, maybe we could go to the IAS node and then to Thorsten.
Yeah, so the way that the neural networks work and analyze images, for example, looks very reminiscent to the structure of tensor networks that we use in holography. And so one would wonder whether what's the relation and whether we can learn anything about one or the other subject by thinking about the similarities between these two things. I don't have anything concrete to say, but maybe someone has an idea.
Sven is waving, so I think he might have a comment related to this point.
Yeah, just as a comment. So there are studies actually trying to relate tensor networks and normal neural networks. So for instance, you could try to use tensor networks to do also like handwritten digit recognition. And so in that way, one can analyze the parallels. Yeah, that's just as a short comment on this. But in general, it seems to be the impression that neural networks have more functional capability than tensor networks.
Well, the biggest, there are many differences you could look at. But tensor networks are definitely a known thing in machine learning. And one of the biggest differences is that whether the calculations that you're doing have cycles or not, So feed-forward network, there's no cycle. You put in the input, there's a very clear rule for getting the output, and you don't need to solve, implicit equations, which you often do in other schemes, including most tensor networks. So that's why the feed-forward networks are so much preferred in practice. But definitely there are problems where tensor networks seem to do better. And I think there is a lot to be learned and to make contact with physics ideas about them, yes.
Maybe Sven, if you have the reference, maybe if you could put it in the chat, maybe it could be nice for people. Thorsten?
Yes, thank you for the nice talk. So I wanted to come back to a point that Michael made earlier, namely that the applications of machine learning that are pursued in string theory are a bit on the fringe in the machine learning community, and that the areas where the major breakthroughs are happening in types of models and types of applications are not really a perfect fit for the problems that we would like to solve. And one of the areas that has seen major breakthroughs in these years is of course language processing, with the advent of attention-based models based on the transformer architecture, these GPT models, which have been trained on humongous amounts of internet data. And to me, it seems that maybe the biggest application to physics, and that could perhaps lead to the most progress, would perhaps be to use language models to leverage the information that we have accumulated in these thousands and thousands of archive papers over the year. So in some sense, like a search engine on steroids that could help you to more quickly figure out the papers, the information that is relevant to the questions that you consider. I wanted to ask what your take on that and propose that as another area that is worth exploring.
Yeah, I definitely think that will make a lot of progress, and that will be a very, very valuable tool 10 years from now. I will put up a link about a talk I have given, which spends a good deal of time on that type of question.
Sorry, Amir. Let's move to, Ben. Let's move to Benjamin, actually, and then to Ben.
Thanks, Fabian, for the talk. I was just bringing attention to a slightly different tool, maybe related to some of the problems people have been talking about, where from geometric data or worldsheet constructions, you might have, for example, sets of constraints where you just don't know whether the equations may be unsatisfiable. So in computer science, there's these SAT solvers and SMT solvers, like satisfiability provers. And if you can get those constraints into a form that those solvers can understand, then they can be very fast at telling you if there is a solution, or whether you've got a sort of theorem like a no-go theorem in their absence. So yeah, I just wanted to mention that if it's interesting.
Yeah, this comes back to the computational complexity problem. So if you have an idea of the computational complexity class your problem is in, for example, if it is in NP, you know that it can be mapped by definition onto a satisfiability problem, and then you can work out this map and use these SAT solvers to solve it, and hopefully quickly. That's one approach you can take. But of course, if your problem is harder than that, SAT solvers won't help.
Ben?
Yeah, it's related to what people were saying, but it's exciting to get AI to help us solve problems. But I mean, the task of just learning how to write an archive paper that string theorists will cite, it seems like there's plenty of data available for that problem. And I mean, I'm not at all an expert on this area, but I would think that in a decade you could devise a system that would succeed at that task better than we do. Is that off base?
Well, there are a few people out there, like Christian Szegedy is a researcher at Google, quite famous in machine learning, and he actually does believe something like that. I can put up a link, but most people do not. Most people, I mean, again, where are we at now? You can ask basic questions that involve kind of doing simple logic, word problems and things. And basically, computers cannot reliably answer those. It's just, despite the language models don't have the ability to understand and do elementary logic in a reliable way. So it seems extremely optimistic to think that in 10 years. I mean, I actually in the end of the talk that I just put up a link to, and my talk has links to Christian and other people's works. I'd make a conjecture which, or at least I throw out an idea which kind of combines these things, which is to say that once the computers can pass that test, that they can kind of do elementary logical reasoning in a pretty reliable way, 10 years from then is when you might start to think they could start to perform human level mathematics. But yeah, I mean, I think by far the consensus is that we are at least 2 or 3 breakthroughs away from that kind of intelligence. And if people are forced to throw out time scales, it is this 30 to 40 time scale. And the more expert the person is in AI, the longer a time they tend to say.
I see. So you somehow can't just take the data from papers on the archive and
well, maybe you can, but there's some essential things the computers are not able to learn yet. So it shows up in this inability to really do basic logic on natural language. Obviously, if you formulate the problem as a logical problem in a program, it does it perfectly and very quickly. But melding those things together doesn't quite work yet.
Ning Bao is back, and I think it was very nice to hear his comments about complexity.
Yeah, so sorry I missed the earlier thing. Believe it or not, the theory experiment divide is not just something that exists in physics, but exists in computer science as well. So there's a lot of, I guess, mileage to be mined in the gap between the theoretical side of computer science, which talks about things like computational complexity, and the more experimental side of computer science, which is more like what machine learning and deep learning is like. And in particular, theoretical computer science, when they talk about computational complexity, are almost always talking about worst case complexity, because in general, it's very difficult to even define average case complexity. And so one should often be scared away if someone tells you that a problem is NP harder in some even more ludicrously large complexity class, because that's often a worst case result. And so that's a situation in which machine learning can be useful. And if one wants to be particularly ambitious, one could maybe even think about using machine learning to define a notion of average case complexity, because the way in which you generate your samples in machine learning could be the way, the distribution, if you like, with which respect you are attempting to define your notion of average case complexity. And I think that this is a notion that could be very useful in the physics context, because it would be very surprising to me if fundamentally uncomputable or extremely high complexity instances of problems appeared naturally in physics. And so ruling out those specific instances and knowing when those instances can be ruled out for certain types of problems may be a very interesting way of generating new constraints and paradigms that limit the kinds of physics questions that we answer by limiting the kinds of math instances that we use to generate our random samples.
Thank you very much. This is precisely what I had in mind when I wrote, and can the complexity tell us something about the vacuum selection process? So are there are only cases realized in string theory that are decidable or easy to compute? You're completely right, and many problems that are NP complete or X space complete even are solved approximately on a daily basis. For example, the turbulent salesman problem is solved by Uber and other companies every day. But yeah, so if the answer is indeed yes, all the equations that you get out of string theory are not worst case complexity, but are easier to solve, so that the universe could solve them or could solve them in 13.7 billion years, that's great. Or if the answer is no, it cannot be solved quickly, it cannot even be solved approximately quickly, so maybe the universe is still searching for the solution. I mean, of course, if it's related to consistency, this cannot be true. And that's, I think, the distinction that Bordy was aiming at. But yeah, you might ask, sort of, is the problem solvable approximately even approximately quickly, or is there no chance? Is solving the approximate solution as hard as solving the fundamental problem itself?
But I also wanted to point out briefly that if the inverse of what I'm saying is true, it has profound consequences. So in the context of the work that you and Jim did on Diophantine equations, suppose that we found that some provably undecidable instance, of which there are known many families of, is embedded into string theory, and that somehow nature naturally solved or came to some near solution to this provably undecidable problem. If that's the case, then I think that that has actually potentially profound implications to what it means for string theory, that there is actually some undecidable mathematics, not even high complexity class, but provably undecidable mathematics at the core of it. And if that could be demonstrated or falsified, I think if it's falsified, it would go along with what everyone believes, but if it could be demonstrated, then I think it would dramatically change some of the questions that we ask at the foundations of strings.
Yeah, that idea is certainly out there. I mean, even defining the quantum gravity as a sum over four-dimensional triangulations is in some sense undecidable, because it's surprisingly, it's hard, it's undecidable whether a triangulation is a manifold. But yeah, definitely there's this kind of trying to work with physics on these foundational level, which again, many people have tried over the years. And I especially quantum mechanics, some other foundations for quantum mechanics. I mean, it's again, so many people have tried, but I think it's right. There's some deep thing to learn there.
Could you maybe just summarize for most? I suspect that some people like me don't know exactly what these undecidable things are and what we are talking about. It looks very esoteric, that there are equations that we cannot decide. Can someone give a brief summary for the layman of what are these mysterious equations? That
so you
cannot just plug in mathematics and check if they are true or not.
So there are, so when you talk about complexity, there are different classes where you can say how hard is actually to solve a problem. The simplest or the easiest class of problems is in P. So this means you can solve it in polynomial time, or you can verify a solution in polynomial time, but problems in this class P you can actually solve in polynomial time, like inverting a matrix, for example. Then there's the next class, this is NP, and this is short for non-deterministic polynomial. So these problems you can verify in polynomial time. So if somebody tells you this is a solution to the problem, you can actually check and say, yes, that's true. But you cannot necessarily find the solution very quickly. And it's a millennium problem, so if you want $1 million, you can show that or disprove that P equals NP. Then there are even harder problems. Lara mentioned, for example, Gribner basis computations. These are X-space complete. So this means you cannot, so this particular problem you cannot even solve, you cannot even check the solution in polynomial time. So if somebody tells you this is the answer, and you would have to compute it yourself to check it. And then sort of the highest level is a problem of decidable, like any decidable problem. You don't care how much time you spend on solving it. You can spend as long as you want, but you can eventually find an answer to this. And then it was sort of proven that there exist problems that cannot even be decided. So there are problems where you cannot devise any algorithm or any Turing machine, meaning any algorithm, that actually can tell you in a finite amount of time whether or not this problem has a solution. And the first problem was the halting problem. And this just asks, can you write a program that decides, given any input, whether this program will halt, will come to a stop, or will run forever? And you can prove that this is undecidable, this problem, by feeding this program to itself. And then you can run something like a Cantor's diagonal argument to show that, that this is actually fundamentally undecidable. And Hilbert asked actually in 1900 whether Diophantine equations were also of this type. And it took 60 years until Matjazewicz, 60-something, actually proved that indeed Diophantine equations had this property that you could not decide whether they had a solution. And this is bound to the fact that you have an infinite, so you don't have a bound on the length of the solution of a Diophantine equation.
Oh, okay.
If you have a quadratic Diophantine equation, there is a bound, and you can use this to solve a quadratic Diophantine equation, but cubic, or the most general one, is actually a quartic one. You can always reduce any set of Diophantine equations to a single quartic equation. And it has been proven that these are indeed undecidable.
Okay, but I can just plug the solution and check if it's solved. I don't know if it has a solution, but if I have a guess, I check, right?
Well, right. I mean, if there is a solution, then you specify all the variables. Of course, you can check that, but it could be that there's no solution. And now how do you prove that?
Yeah, actually, if I could just interject, I thought the statement was that there were systems of Diophantine equations that did not admit a solution, but you could not prove within the axiom system of mathematics.
Yeah, that's right.
Igor just said, any finite system of Diophantine equations in integer coefficients make a countable list of all possible solutions.
I think you are breaking up, right? Is it not just for me?
Lara, your last comment broke up.
Sorry, did I break up there? Or am I back?
You're back now.
Yeah, I'm sorry. All I was saying is, isn't the correct statement that there are Diophantine equation systems that do not admit a solution, but you cannot prove it within the axiom system? Whereas if there is a solution, you can always make a countable list of possible solutions and you will always reach it in finite time.
Yeah, yes.
Okay. So undecidable basically is only relevant when there's no solution. So I don't think that if string theory is solving it, it would fit into that category, because it would be a solution which could always be reached in finite time by simply counting all the possible solutions.
No, there's no bound. You cannot derive a bound for when you would find a solution, so you wouldn't know.
Absolutely.
When.
No, there's no bound on how long it will take, but for any given.
And the gauge invariance and equivalences also make this complicated. As you know, like the problem of whether two four manifolds are homeomorphic is undecidable because the word problem for their fundamental groups is undecidable. So if your problem is not just to find a solution, but to understand the gauge equivalences, you again have a problem.
Right. I'm just saying if the equations of string theory are a finite system of Diophantine equations and it has a solution, you can always find that in finite time, but it's unbounded how long.
I'm sorry, I would like to move to Ling Lin because he is not asking questions. And then let's close the formal part of the discussion and we can continue a little bit more informally. But let's move to.
So I also have a very naive question. So, I mean, I don't really see exactly why we would contribute to the universe the property that it has to solve a problem in any given complexity class like a human would. But suppose that is true, could it mean, for example, that the fact that we find Diophantine equations in string theory that are of the form NP complete or any other higher complexity class, that maybe we do not have a fundamental description of the theory? So, or flipped it around, could it mean that if you had a complete microscopic description, UV complete description of your theory, then basically all the valid solutions would be in P, and the fact that we don't see that solution or cannot verify them in our given understanding is just a reflection of our ignorance of the full theory.
Yeah, so of course it is a conjecture. It's underlying the thing that the universe is bound by complexity. So you're assuming that whatever the universe does to find a minimum or whatever its physical laws is that it's running, it's an algorithm, and as such it's bound to obey the laws of mathematics or of complexity. So if that's not true, of course, then you could say, okay, so the universe can just do whatever it wants. It can solve NP problems in P, but many people actually believe that it cannot. So if you assume that is true, then you can go the next step and ask what does it imply? And of course you might say, okay, the universe probably has access to a quantum computer, so it can solve problems that you can solve quickly in a quantum computer. So it's maybe okay if it solves something in complexity class BQP, which is the analog of P. But then there are still problems, sort of a problem that's NP complete by. This is not proven, but everybody I talk to believes this, that so NP is not equal to BQP either. People believe that P is not equal to NP, and people also believe that all these complexity classes are different. So problem, you cannot even solve it fast.
If one tries to make this discussion precise, of course, the other thing you should start by saying is that complexity class, a single problem doesn't sit in a complexity class. It's a series of problems, and it's the asymptotic difficulty, the function of how hard the problem is with respect to some measure of the size of the problem. And so if we're talking about finding a universe in string theory, that's not a problem of complexity theory per se. but because that is a problem. But definitely the problems look like they sit in natural complexity classes, where if you say I could have flux vacua with the number of fluxes becoming arbitrarily large, then it would be in this NP hard class. That was the sort of result that F and I got. But yeah, I think at this point exploratory work of kind of using complexity to motivate very different ideas that just looking at the laws might not have suggested to you. I think that's the point where we can open our minds and liberate ourselves. So
can I just ask a very basic another question related to this? I mean, is there an known instance of, say, an effective theory whose vacuum solution to whatever you want to know is more complex than a more fundamental description of that system? Say, I don't know, maybe some effective theory, for example, of QCD, and then you use QCD.
The basic physical example of these hard problems is just you're given some very complicated potential function and you're looking for its global minimum. And that's pretty generally NP hard or very hard in some sense problem. Of course, if it's only one potential, you can't use, strictly speaking, the language NP, but that is the canonical hard problem already in physics for a very long time. And so there's a lot has been said about that, and that covers probably 80% of what we're talking about in this discussion. And then to go beyond that, again, I think the papers that are out there, it's not like we made strong conclusions, but we did try to explain these distinctions and give ideas for the questions that you can ask.
I mean, let me let me thank you, Fabian and Mike, and we can continue for a few more minutes. But I think I would like really to thank Fabian and Mike for a very nice discussion. And we can, of course, continue with more informal questions for a little bit more. And that's after all, the purpose of these discussions, to be relaxed. So, but thank you again for moderating this. And the official part now is over. So if you want to leave, if I need to leave, everything is okay.
So with this undecidability thing, Mike, didn't we have a discussion about this a long time ago where like this word problem, as you reviewed, is true, like it's undecidable. However, say you realize that as the fundamental group of a manifold in dimension 4 or higher, where it applies, where this issue applies. Well, now take that as your target space for string theory, let the manifold expand with time so it's a good solution and so on. It seemed like there were topology changing processes that don't conserve that homotopy. Right?
Yeah, I think the strict concept of manifold is, of course, not the right one for string.
Right. So in other words, the idea being that in that case, the physics didn't ask the undecidable question.
I think that would be the guide at the moment. The reasonable conjecture is that physics is not solving what we think of as undecidable problems. But of course, it's still a fruitful kind of question to think about.
I wanted to briefly to Ling's question. Something that kind of answers the question, that kind of is an example of what you're asking about, is ADS-CFT, right? Because while it is technically, that's technically not a true statement, because in some sense, if I wanted to compute some quantity on the CFT, and I gave myself all possible knowledge of the methods associated with the CFT, then the fast method would be to do the bulk equivalent and then translate it via the dictionary. Let's say that I did a dumber thing, and I didn't know that my CFT had a holographic dual, and I tried to compute the quantity directly in the CFT. That would be much less efficient. And so in some sense, ADS-CFT and dualities are an example of situations that do what you say. But there, it's not really like one or the other theory is more fundamental in some sense. It's more that like the duality transformation is encoding a lot of information in and of itself. And so I wouldn't privilege one of those two descriptions as being the more fundamental description, but rather I would just say that.
Well, let me emphasize what was just said, which is that a problem which really would be very, a discovery that would be very exciting would be, again, to find a problem where, say, on the one side of a duality, the computational problem looks NP hard or hard, and then on the dual side, it looks easy. I mean, definitely there could be such things, and that could be very illuminating.
Yeah, so I also wanted to answer this to Ling before. So if the way you prove that a certain system is in a certain complexity class is usually done by a reduction. So you reduce the problem to a different problem from which you know what the complexity is. So if you now can use a duality or like ADS CFT correspondence or whatever in order to map your problem from ADS to CFT in polynomial time, then by definition, and the problem is solvable, let's say, on the ADS side or on the CFT side in polynomial time, this would prove that the problem is actually in P. So the art or the name of the game is actually to find these maps from a problem where you don't know the complexity onto a different problem. And then if this map is in polynomial time, you can solve this thing in polynomial time, then you have solved the entire thing in polynomial time. So this would be fantastic if you could use sort of a physics-inspired way of finding these maps and proving for some problems for which a complexity class is not known that they are in P, let's say.
Right, but for example, in your Diophantine equation paper, suppose that actually there is a description where it says that, where it's manifest that basically all these equations are redundant, and in fact the solution or the answer you wanted to get by solving this equation is just 42. Wouldn't the original question of asking how hard is it to solve the set of equations just then be in ignorance of what the actual fundamental physics is, say? So, or said differently, if the universe knew about this kind of fundamental properties, then it wouldn't have to solve these Diophantine equations and be bothered by this complexity problem.
Yes,
I think that depends on if you're happy with the universe setting the value to be 42 as an initial condition, in which case, fine, you're allowed to do whatever you want as initial conditions, and then there's no dynamics to be considered. Or if you wanted it to be set by some simpler initial conditions and to have evolved to it dynamically in some way. If you're talking about something that's evolving dynamically, and if we think that the universe operates a large unitary, which can be modeled by a quantum computer with a polynomial number of circuit elements, circuit depth, then you kind of are constrained by these complexity things. But of course, you're free to not make these assumptions, or you're free to be happy with certain parameters being set as initial conditions. And if you're happy with the setting certain things as initial conditions, kind of without explanation, then yes, you can get around a lot of these complexity theoretic concerns. There are also specific instances, say you're not interested in the evolution of a quantity of a foundational concept in the universe, but you're interested in something more simpler, like the evolution of like a spin glass Hamiltonian or something from some fixed initial state, which you can fix in your lab. Well, then I would certainly be surprised if that spin glass Hamiltonian in its adiabatic cooling down or whatever was able to find a ground state in polynomial time if the form of the Hamiltonian was a worst case instance of an NP-hard problem. And so it really depends on what kinds of physics questions you're interested in asking and what assumptions you're interested in allowing yourself to make from the beginning.
I think this will be better to continue on Slack. It's becoming a very focused discussion, and that's precisely the type of discussion that on Slack it's perfect because people are asking for references and so on. Then it's really a perfect venue to just make sure that we don't lose all these references. So let's please thank Mike and Fabian and conclude this informal discussion and reconvene tomorrow. Yeah. See you all.
Peter?
Yes.
Sorry. Will you copy the questions into Slack, or should people just ask again in Slack?
No, people just ask again. Yeah. Please ask again the questions on Slack. Yeah, the ones that were not discussed. Yeah.